Beneath Jupiter's ancient surface, hidden under a frozen shell thicker than Earth's tallest mountains, lies an ocean containing more water than all of Earth's seas combined. This isn't speculation, it's measured fact. Ganymede, the largest moon in our solar system, harbors a secret that transforms everything we thought we knew about where life might exist beyond Earth. In 1610, Galileo pointed his primitive telescope toward Jupiter and discovered 4 bright points of light orbiting the giant planet. He had no idea one of them contained an ocean. For centuries later, we've sent spacecraft past Ganymede, mapped its magnetic field, and measured its gravitational pull with extreme precision. The data tells an astonishing story. Deep beneath ice that would crush any submarine we've ever built, liquid water moves in currents we're only beginning to understand. Ganymede is massive. At 5,268 kilometers across, it's larger than Mercury. If it orbited the Sun instead of Jupiter, we'd call it a planet without hesitation. But size alone doesn't make it remarkable. What matters is the structure we've detected beneath that scarred, ancient surface. Layer upon layer of ice and water, stacked like a cosmic sandwich, each zone distinct in temperature, pressure, and composition. The surface ice isn't uniform. Roughly 40% is ancient, dark terrain covered in impact craters that have accumulated over billions of years. The rest is younger, brighter, scored with grooves and ridges that reveal a violent tectonic past. Something powerful resurfaced large portions of Ganymede, and that something came from within. The ice didn't just crack. It moved. Plates shifted. Entire regions were rebuilt by forces we're still trying to explain. Scientists first suspected an ocean in the 1970s, but suspicion isn't proof. The breakthrough came from Galileo, the spacecraft, not the astronomer. Between 1995 and 2003, this robotic explorer made 6 close flybys of Ganymede, gathering magnetic field data that changed the game entirely. Ganymede generates its own magnetic field, the only moon in the solar system known to do so. That field interacts with Jupiter's powerful magnetosphere in ways that reveal what's hidden below. When Galileo's magnetometer detected variations in Ganymede's field, researchers noticed something unexpected. The patterns suggested electrical currents flowing beneath the surface. Salty water conducts electricity. Pure ice does not. The data pointed unmistakably toward a subsurface ocean rich in dissolved salts. Multiple independent studies confirmed it. Ganymede has liquid water, and lots of it. How much water are we talking about? Conservative estimates suggest the ocean contains more water than Earth's Atlantic, Pacific, Indian, Arctic, and Southern oceans combined. Some models push that figure even higher. The ocean might be 100 kilometers deep, possibly more, sandwiched between layers of ice in a configuration nothing like what we see on Earth. Temperature becomes strange at those depths. Near the surface, ice reaches temperatures around -160 degrees Celsius, cold enough to shatter steel. But pressure changes everything as you descend. The weight of overlying ice creates heat through compression. Radioactive decay in Ganymede's rocky core adds more warmth. Tidal flexing from Jupiter's gravity generates additional energy as the moon's shape distorts slightly during its orbit. All these factors combine to keep water liquid despite being farther from the Sun than any ocean in our immediate cosmic neighborhood. The structure is layered in ways that challenge our understanding of planetary interiors. Scientists propose multiple distinct zones. The top layer is solid ice, perhaps 150 kilometers thick. Below that, the ocean. Beneath the ocean, another ice layer, but this ice forms under such extreme pressure that it becomes Ice 3, Ice V, or even Ice 6, exotic crystalline structures that only exist under conditions we can barely replicate in laboratories. These high-pressure ices are denser than water, so they sink, creating an inverted world where ice floats below liquid, not above it. At the very bottom sits Ganymede's rocky core, probably similar in composition to Earth's mantle but much smaller. This core might still be warm enough to drive hydrothermal activity. On Earth, hydrothermal vents pump minerals and heat into the deep ocean, creating oases of life in absolute darkness. Could similar processes operate on Ganymede? We don't know. But the possibility exists. Jupiter's influence on Ganymede cannot be overstated. The planet's gravity doesn't just hold the moon in orbit. It squeezes it. Ganymede's orbit isn't perfectly circular, so the strength of Jupiter's gravitational pull varies throughout each 7-day orbit. This variation flexes Ganymede's interior like a stress ball being repeatedly squeezed and released. That flexing generates heat, the same process that powers Io's spectacular volcanism and maintains Europa's subsurface ocean. But Ganymede's tidal heating is gentler than Europa's. Europa orbits closer to Jupiter and experiences far more intense flexing. Ganymede sits farther out, in a more stable orbit, receiving just enough tidal energy to maintain liquid water without the violent geological activity that resurfaces Europa constantly. This might actually be an advantage. A calmer environment could be more conducive to complex chemistry, perhaps even biology. The magnetic field discovery revealed something else. Ganymede's field is surprisingly strong, about 1% the strength of Earth's field. That might not sound impressive, but for a moon, it's extraordinary. The field originates from a metallic core, probably iron or iron-nickel, that remains partially molten. A dynamo operates inside Ganymede, circulating liquid metal and generating magnetism through the same basic process that protects Earth from solar radiation. This magnetic field creates a miniature magnetosphere around Ganymede, a protective bubble carved out of Jupiter's much larger magnetic environment. When Ganymede passes through different regions of Jupiter's magnetosphere, the interaction changes. Scientists use these variations to probe what lies beneath the ice. The ocean's salty water conducts electrical currents that alter the magnetic field in detectable ways. It's like using magnetism to see through hundreds of kilometers of ice without drilling a single hole. The composition of that ocean remains uncertain. We know it contains dissolved salts, but which salts? Sodium chloride, like Earth's oceans? Magnesium sulfate? Some exotic mixture we've never encountered? Spectroscopic observations of Ganymede's surface show evidence of various salts and minerals, including what might be hydrated salts pushed up from below through cracks in the ice. These surface deposits offer tantalizing clues about the ocean's chemistry, but they're just hints. We won't know the ocean's true composition until we sample it directly. Sampling that ocean presents extraordinary challenges. The ice shell is thicker than any ice we've drilled through on Earth. Antarctica's deepest ice cores reach about 3.5 kilometers. Ganymede's ice might be 50 times thicker. Drilling through that much ice would require technology we haven't developed yet, power sources that don't exist, and mission durations that stretch decades. Alternative approaches exist. Perhaps we could target thinner regions where the ice is fractured or where warm upwellings have thinned the shell. Maybe we could send a probe through one of the cracks visible on the surface, assuming those cracks penetrate deep enough. Or we might analyze material ejected from the subsurface by impacts or cryovolcanic activity. Each method has drawbacks, but they're being studied seriously. The surface itself tells stories about what lies beneath. Those parallel grooves and ridges covering the brighter terrain formed through tectonic processes. Ganymede's ice shell fractured and shifted, driven by forces from below. Some regions show evidence of past cryovolcanism, where liquid water or slushy ice erupted onto the surface, freezing instantly in the vacuum of space. These features are old, billions of years in some cases, but they prove the interior was once geologically active. The question is whether that activity continues today. Recent observations suggest it might. The Hubble Space Telescope detected evidence of water vapor plumes erupting from Ganymede's surface, similar to the plumes Enceladus shoots into space from its south polar region. If confirmed, these plumes would be game-changing. They'd provide direct samples of subsurface material without requiring us to land or drill. A spacecraft could fly through the plumes, collect particles, and analyze their composition. We'd learn about the ocean's chemistry, search for organic molecules, and potentially detect signs of biological activity, all without touching the surface. The plume evidence isn't conclusive yet. The signal is subtle, and alternative explanations exist. But if Ganymede does have active plumes, it joins Europa and Enceladus in a select group of ocean worlds that occasionally expose their hidden seas to space. This would make Ganymede a prime target for future missions designed to search for life beyond Earth. Understanding Ganymede's ocean requires understanding its history. The Moon formed roughly 4.5 billion years ago from the disk of gas and dust surrounding the infant Jupiter. Early in its history, Ganymede was probably much warmer. Radioactive decay and impact heating from late-stage bombardment would have created conditions warm enough to melt ice throughout the interior. The Moon might have been entirely liquid at some point, with a global magma ocean overlying a water ocean of staggering depth. As Ganymede cooled, it differentiated. Heavier rocky material sank to form the core. Lighter ices rose toward the surface. Water separated from rock, creating distinct layers. The cooling continued, but never reached the point where the entire Moon froze solid. Tidal heating from Jupiter and residual heat from radioactive decay kept the interior warm enough to maintain liquid water, even as the surface froze into the icy shell we observe today. That surface has been modified countless times. The dark, cratered terrain preserves Ganymede's ancient face, a record of impacts stretching back billions of years. The bright, grooved terrain is younger, perhaps 1 to 2 billion years old, created when the ice shell fractured and new ice flooded the surface. What triggered this resurfacing event? Possibly a period of enhanced tidal heating when Ganymede's orbit shifted slightly. Or perhaps a massive impact disturbed the ice shell enough to trigger widespread tectonic activity. The grooves themselves are puzzling. They run parallel for hundreds of kilometers, creating patterns that suggest systematic stress across the entire ice shell. Some researchers think the grooves formed as the ice expanded during freezing, creating tension that cracked the surface. Others propose they're the result of tectonic plates sliding past each other, similar to transform faults on Earth. The truth might involve both processes working together in ways we don't yet understand. What makes Ganymede's ocean potentially habitable? 3 factors stand out. First, liquid water, the universal solvent necessary for chemistry as we know it. Second, chemical energy sources, possibly including hydrothermal vents if the rocky core remains active. Third, time, billions of years for complex chemistry to evolve and potentially produce something we'd recognize as life. That third factor is crucial. Life on Earth didn't appear overnight. It took hundreds of millions of years for chemistry to cross the threshold into biology. Ganymede's ocean has existed for most of the solar system's history. If conditions have remained stable, that's an enormous window for biological processes to develop. Of course, stability doesn't guarantee life. It only provides the opportunity. Earth's ocean spent billions of years churning with chemistry before producing the first cells. And even after life emerged, it remained simple for most of Earth's history. Complex organisms, the kind that build structures or move purposefully, arrived remarkably late. On Ganymede, we're searching for something far more modest, evidence that chemistry has become organized, that molecules have learned to replicate, that energy flows through systems we could call metabolic. The search faces immediate obstacles. Ganymede's ocean lies beneath potentially 150 kilometers of ice. No drill exists that could penetrate that depth in reasonable time. No submarine could reach those depths and return data. We're forced into indirect methods, analyzing the surface for clues about what lies below, studying how the magnetic field behaves, watching for changes that might indicate activity deep within. But there's a faster approach. If Ganymede truly has water plumes erupting through the ice, we bypass the barrier entirely. A spacecraft flying through those plumes would sample ocean material directly. Instruments could detect organic molecules, measure salinity, identify chemical signatures that might indicate biological processes. We'd essentially be tasting Ganymede's ocean without ever landing. NASA and ESA are already planning missions that could make this happen. The Europa Clipper, launching in the 2020s, will study Jupiter's moons during multiple flybys. While its primary target is Europa, it will also observe Ganymede, searching for plume activity and mapping the magnetic field in greater detail. The JUICE mission, led by ESA, will spend years studying Ganymede specifically, eventually entering orbit around the Moon itself. JUICE carries instruments designed to peer through the ice using radar, to measure the thickness of different layers, to map variations in the gravitational field that might reveal ocean currents below. These missions won't answer every question. They're reconnaissance, not final proof. But they'll narrow the possibilities. They'll tell us where the ice is thinnest, where tidal heating concentrates, where future landers should aim. They're setting the stage for something more ambitious, a mission that actually touches Ganymede's surface and drills into the ice. Drilling on Ganymede presents challenges Earth's polar expeditions never faced. Temperatures hover around -160 degrees Celsius. There's no atmosphere to provide pressure or distribute heat. Solar power is weak this far from the sun. Any drill would need to carry its own energy source, probably a radioisotope generator, and melt through ice that's harder than concrete at those temperatures. The drill would need to operate autonomously, without real-time control from Earth. Radio signals take 40 minutes to travel between Jupiter and our planet, making remote piloting impossible. Every decision, every adjustment, would need to happen on site, guided by artificial intelligence capable of responding to unexpected conditions. Assuming we overcome those obstacles, what happens when the drill reaches liquid water? The bit punches through the final meters of ice and suddenly encounters resistance-free fluid. Sensors detect the transition. The drill stops advancing. A probe deploys, a small autonomous vehicle designed to separate from the drill string and swim freely in the ocean below. It carries cameras, though visible light penetrates only meters in these dark waters. It carries chemical sensors to taste the ocean's composition. It carries sonar to map the underside of the ice and detect objects in the surrounding water. And it carries life detection instruments, devices designed to recognize patterns that biology creates, organic molecules arranged in ways chemistry alone wouldn't produce. This isn't science fiction. Engineers have already built prototypes. They've tested autonomous underwater vehicles beneath Antarctic ice, demonstrating that machines can navigate and collect samples in environments humans will never visit. The technology exists. What's missing is the funding, the political will, and the decades of patience required to send these systems to another world. Why go to such extraordinary lengths? Because Ganymede represents a test case for a much larger question. If life can arise in an ocean sealed beneath ice, isolated from sunlight, dependent entirely on chemical energy from hydrothermal vents, then life might be common throughout the universe. Most planets don't orbit their stars in the narrow habitable zone where liquid water can exist on the surface. But countless moons orbit giant planets, experiencing tidal heating, maintaining subsurface oceans regardless of how far they are from their star. Ganymede-like worlds might outnumber Earth-like worlds by orders of magnitude. Finding life on Ganymede would fundamentally shift how we think about biology's place in the cosmos. It would suggest that wherever liquid water persists for geological time, life finds a way to emerge. The universe suddenly becomes much more alive, even if that life hides beneath frozen surfaces, invisible to telescopes, detectable only through patient exploration. The implications extend beyond biology. Ganymede's ocean, if inhabited, would represent a second origin of life in our solar system. Earth's life shares a common ancestor. Every organism, from bacteria to blue whales, descended from the same primordial cell. We're all one family, variations on a single theme. But life on Ganymede, if it exists, would have started independently. Its chemistry might use different molecules. Its cells might have different structures. Its metabolism might run on different reactions. Comparing Earth life to Ganymede life would reveal which aspects of biology are universal and which are accidents of our particular history. There's also the possibility that Ganymede's ocean contains nothing alive at all. That the chemistry never crossed the threshold, that the conditions weren't quite right, that life requires something we haven't identified yet. This outcome would be scientifically valuable too. It would tell us that liquid water and chemical energy aren't sufficient. That life requires additional factors we need to understand before we can predict where else it might arise. Every null result narrows the search, eliminating possibilities, focusing attention on what truly matters. Ganymede's future depends partly on Jupiter. The giant planet's gravity dominates the entire system. Tidal forces that keep Ganymede's ocean liquid also create stress throughout the Jovian system. Jupiter's moons interact gravitationally, their orbits shifting subtly over millions of years. These orbital changes affect how much tidal heating each moon experiences. Ganymede might be warming or cooling depending on these long-term cycles. The ocean could be expanding or contracting. The ice shell might be thickening or thinning. We're seeing a snapshot of a dynamic system, one that changes on timescales far longer than human civilization has existed. Looking billions of years forward, Ganymede's fate is tied to the Sun. Our star is slowly brightening. In roughly 1 billion years, it will be hot enough that Earth's oceans begin to evaporate. The habitable zone will shift outward. By the time the Sun becomes a red giant, perhaps 5 billion years from now, it will expand dramatically, possibly engulfing the inner planets entirely. Jupiter's orbit will be warm enough that Ganymede's ice shell melts completely. The Moon might briefly have a surface ocean, liquid water exposed to space, before the Sun's evolution continues and everything boils away. But that's distant speculation. Right now, Ganymede orbits Jupiter much as it has for billions of years. Its surface remains locked in frozen silence. Its ocean, if inhabited, contains life that has never seen a star, never experienced seasons, never known anything beyond the crushing pressure and absolute darkness of its submerged world. And yet, that life, if it exists, would be our cosmic cousin, proof that the universe creates biology wherever conditions allow, that we're not alone in finding ways to persist and adapt and thrive. The next steps are clear. We need to return to Ganymede with better instruments. We need to map the ice shell's thickness precisely. We need to confirm whether plumes are erupting. We need to identify the best drilling sites. And eventually, we need to send a drill, punch through that ice, and taste the ocean that has remained hidden since the solar system's birth. Each mission builds on the last. Each discovery raises new questions. The process is slow, frustratingly slow for those eager for answers. But it's also methodical, accumulating evidence piece by piece, building a case that will eventually become undeniable. Ganymede doesn't care whether we study it or not. The Moon will continue its orbit, its ocean will continue to slosh beneath the ice, its magnetic field will continue to deflect Jupiter's radiation. But we care, because understanding Ganymede means understanding how common habitable environments might be throughout the galaxy. It means learning whether life is a cosmic accident that happened once, here on Earth, or an inevitable consequence of chemistry given the right conditions and enough time. That question drives everything we do in space, every mission we plan, every instrument we build. Ganymede's story matters because it rewrites what we thought we knew about where life can exist. For most of human history, habitability meant one thing: being near a star at just the right distance. Not too hot, not too cold. The Goldilocks zone. Earth sits comfortably within that zone, receiving sunlight that keeps water liquid on the surface. That seemed like the requirement. No sunlight, no warmth, no life. Ganymede ignores that rule completely. It orbits 5 times farther from the Sun than Earth does. Sunlight there is faint, barely more than moonlight from our perspective. Surface temperatures hover around -160 degrees Celsius. By traditional standards, Ganymede should be a frozen wasteland, utterly sterile. Yet beneath that frozen exterior lies an ocean larger than all of Earth's oceans combined, kept liquid not by sunlight but by gravitational friction. The rules changed. Habitability no longer requires proximity to a star. It requires energy, and energy comes from multiple sources. This realization transforms how we think about the galaxy. Current estimates suggest hundreds of billions of planets exist in the Milky Way alone. Most orbit too far from their stars to have surface liquid water. We used to dismiss those worlds as uninteresting, too cold to matter. But if tidal heating can maintain subsurface oceans, then billions of frozen worlds suddenly become potential habitats. Ice becomes a protective shell rather than a barrier. Darkness becomes normal rather than fatal. The number of potentially habitable environments in the galaxy might be orders of magnitude higher than we previously calculated. Europa taught us this lesson first. It's smaller than Ganymede, closer to Jupiter, and experiences even more intense tidal heating. Its ice shell might be only 15 to 25 kilometers thick, potentially thin enough that drilling becomes realistic with current technology. Europa's ocean might be in direct contact with a rocky seafloor, creating conditions similar to Earth's hydrothermal vents. Those vents on Earth support ecosystems that thrive without sunlight, using chemical energy instead. If Europa has similar vents, it might have ecosystems too. But Ganymede offers something Europa doesn't: stability. Europa's surface is young, constantly resurfacing from geological activity. Its ice shell might be churning, cycling material between the surface and the ocean on relatively short timescales. That's good for delivering nutrients but chaotic for any life trying to establish itself. Ganymede's surface is ancient, some regions dating back billions of years. The ice shell appears thicker, more stable. The ocean beneath might be calmer, less disturbed. Life, if it exists, has had billions of years to develop in relatively stable conditions. That matters enormously. Consider Earth's history. Single-celled organisms appeared relatively quickly, within the first billion years after the planet cooled enough to have liquid water. But complex life took far longer. Multicellular organisms didn't emerge until roughly 600 million years ago. Large animals appeared only in the last half-billion years. Intelligence required even more time. Evolution isn't just about having the right ingredients. It needs time to experiment, to try countless variations, to stumble upon solutions that work. Ganymede has had that time. If its ocean formed during the solar system's early days, life there has had 4 billion years to evolve. What might 4 billion years of evolution produce in an alien ocean? We have no idea. That's the honest answer. Earth's oceans contain everything from microscopic bacteria to blue whales, from simple sponges to intelligent octopuses. Evolution explores countless paths, finding solutions we'd never imagine. An alien ocean isolated from Earth's evolutionary history would follow its own trajectory, shaped by different pressures, different chemistry, different constraints. The organisms there, if they exist, might share some basic principles with Earth life. They'd need to extract energy from their environment, maintain their internal chemistry, reproduce. But the details could be utterly foreign. Imagine organisms that navigate by sensing magnetic fields directly, creatures that communicate through electrical signals in ways far more sophisticated than Earth's electric fish. Perhaps something analogous to plants but using chemical energy from hydrothermal vents instead of sunlight, creating the base of a food chain. Predators that hunt in absolute darkness using senses we can't comprehend. Maybe colonial organisms, vast networks of interconnected cells functioning as single entities, stretching across kilometers of ocean floor. Or nothing like any of those things. Evolution is creative in ways that constantly surprise us even when studying Earth's own biosphere. The chemical composition of Ganymede's ocean adds another layer of complexity. Earth's oceans are salty, dominated by sodium chloride. Ganymede's ocean might have different salts, possibly magnesium sulfate or other compounds. The pH could be different. The pressure at the ocean floor would be immense, potentially several hundred times Earth's atmospheric pressure. Organisms there would need to function under those conditions. They'd have no concept of low pressure, no evolutionary history of dealing with anything but crushing weight. Bring them to the surface and they'd likely die instantly, cells rupturing from the pressure drop. We'd need to maintain samples at depth, study them in specialized chambers, never letting them experience what we consider normal conditions. Temperature poses another question. Earth's deep oceans are cold but not frozen, typically around 2 to 4 degrees Celsius. Ganymede's ocean temperature depends on how much heat reaches it. Near the ice shell, it's probably just above freezing, close to 0 Celsius. Near the ocean floor, if hydrothermal vents exist, temperatures could spike dramatically. Earth's vents can reach hundreds of degrees Celsius. Water remains liquid under pressure at those temperatures. Organisms on Earth thrive in these extreme environments. Ganymede might have similar temperature gradients, creating diverse habitats within the same ocean. Cold-adapted organisms near the ice, heat-loving extremophiles near vents, and everything in between. Salinity affects what can dissolve in water. Different salts change water's properties, how it conducts electricity, how it freezes, how molecules move through it. Life would adapt to whatever chemistry exists there, evolving proteins and cell membranes suited to that specific environment. We can't simply transplant Earth organisms to Ganymede's ocean and expect them to survive. The chemistry would be wrong. But native organisms, if they exist, would be perfectly suited to their home, finding our ocean as alien and hostile as we'd find theirs. Energy sources drive everything. On Earth, sunlight powers most ecosystems directly or indirectly. Remove the sun and Earth's biosphere would collapse within years. Ganymede never had that dependence. Its energy budget relies on tidal heating and possibly radioactive decay in the rocky core. That's a limited energy supply compared to sunlight. Earth receives roughly 174 petawatts of solar energy. Ganymede's tidal heating probably delivers far less, maybe a few terawatts at most. That limits how much biomass the ocean can support. An ecosystem there would be sparse compared to Earth's teeming oceans. Fewer organisms, spread over vast distances, competing for limited chemical energy. Life, but not abundant life. Survival, but on the edge. This scarcity might actually favor certain evolutionary paths. On Earth, competition drives arms races, predators evolving better hunting skills, prey evolving better defenses. But in energy-poor environments, cooperation sometimes wins over competition. Organisms might evolve symbiotic relationships, sharing resources, supporting each other's metabolism. We see this on Earth in extreme environments. Lichens are partnerships between fungi and algae. Deep-sea tube worms host bacteria that process chemicals from hydrothermal vents. Ganymedes organisms might take cooperation even further, creating integrated systems that blur the line between individual and colony. Then there's the question of complexity. Does low energy availability limit how complex organisms can become? Large brains require enormous energy. Human brains consume roughly 20% of our total energy budget despite being only 2% of our body mass. Intelligence is expensive. In Ganymedes' ocean, that cost might be prohibitive. Evolution might favor simple, efficient organisms over complex, energy-hungry ones. Intelligence might never emerge, not because it's impossible but because it's not worth the energy investment. Or perhaps intelligence evolves differently there, taking forms that don't require massive energy consumption. Distributed intelligence across colonies, simple individual units that collectively make complex decisions. We assume intelligence looks like human brains. It doesn't have to. Time becomes fascinating when discussing Ganymedes' potential biosphere. Earth's organisms evolved alongside a changing planet. Continents shifted, climates changed, ice ages came and went. Mass extinctions wiped out dominant species, allowing new lineages to emerge. Evolution responds to change. But Ganymedes' ocean might be remarkably stable. No seasons, no day-night cycle, no continental drift affecting ocean currents. Temperature and chemistry might vary little over millions of years. In such stable conditions, evolution might slow. Once organisms adapt well to their environment, there's less pressure to change. We might find living fossils, organisms essentially unchanged for billions of years because their environment never demanded innovation. Or perhaps stability allows evolution to explore other directions. Without constant environmental upheaval, evolution might focus on optimization rather than adaptation. Organisms becoming incrementally more efficient at extracting energy, processing nutrients, reproducing. Refinement over time rather than dramatic shifts. The result would be organisms exquisitely tuned to their environment but unable to cope with even slight changes. Specialists rather than generalists. That creates vulnerability. If something disrupts Ganymedes' ocean, a massive impact delivering heat, a change in Jupiter's tidal forces, the ecosystem might collapse entirely, unable to adapt quickly enough. We're speculating, building hypotheses from limited data. That's necessary at this stage. We can't know what exists on Ganymede until we look. But we can make educated guesses based on physics, chemistry, and biology. We can identify what's possible, what's probable, what's unlikely. Those guesses guide mission planning, helping us decide where to look, what instruments to bring, what measurements matter most. Every mission updates our understanding, confirms some guesses, disproves others, raises new questions we hadn't considered. Europa offers a different scenario, another frozen moon hiding an ocean, but with critical differences. It orbits closer to Jupiter than Ganymede, experiencing stronger tidal heating. That means more energy available for life, potentially more active geology on the ocean floor. Europa's ice shell might be thinner, perhaps only 10 to 15 kilometers in some regions. Thinner ice changes the game entirely. With less ice overhead, more radiation from Jupiter penetrates deeper. Radiation breaks apart water molecules at the surface, creating oxidants, chemicals that can participate in biological reactions. Some of those oxidants might work their way down through cracks and fractures, mixing into the ocean below. That influx represents a different energy source, one independent of hydrothermal vents. Earth's early oceans lacked oxygen for billions of years. Life evolved without it, using other chemical pathways. When photosynthetic organisms finally started producing oxygen, it changed everything, enabling more efficient metabolism, more complex organisms, larger bodies. Europa's ocean might skip the waiting period. Oxidants from the surface could provide that efficiency boost from the start, allowing life to evolve along different trajectories than Earth's early biosphere. Europa's surface shows strange features, reddish-brown streaks and patches staining the ice. Spectroscopy suggests those colors come from salts, sulfates, and organic compounds brought up from below. The ice isn't static. It churns, cycles, brings deep material to the surface, sends surface material down. That exchange creates possibilities. If life exists in Europa's ocean, evidence might reach the surface eventually, locked in ice we could sample without drilling through kilometers of frozen water. NASA's Europa Clipper mission, launching soon, will study those surface features in detail, mapping the ice shell's thickness, measuring the ocean's salinity, searching for plumes of water vapor erupting through cracks. The Hubble Space Telescope spotted potential plumes back in 2012 and 2016, geysers shooting water hundreds of kilometers above the surface. If those plumes are real and consistent, a spacecraft could fly through them, collecting samples directly from the subsurface ocean without landing. Analyzing those samples for organic molecules, for chemical signatures inconsistent with purely geological processes, for anything suggesting biological activity. That's the dream scenario, finding life without the engineering nightmare of drilling through ice in low gravity on a radiation-blasted moon. But plumes are unpredictable. They might not erupt when we're watching. They might not contain material from deep enough to include biological signatures. We might fly through them and find only water vapor and ice crystals, learning nothing about what lies below. Still, it's worth trying. The payoff, if successful, justifies the risk. Then there's Enceladus, Saturn's tiny moon, barely 500 kilometers across. Too small for significant radioactive heating, too far from Saturn for strong tidal forces. By all rights, it should be frozen solid, geologically dead. Yet it's not. In 2005, Cassini detected massive plumes erupting from cracks near Enceladus's south pole, shooting water vapor, ice particles, and organic molecules into space. Those plumes feed Saturn's E-ring, a faint ring of ice particles orbiting the planet. Enceladus is active, spectacularly so, despite having no obvious reason to be. The best explanation involves tidal heating, but in a subtle form. Enceladus orbits Saturn in resonance with other moons, gravitational interactions that slightly alter its orbit over time. Those orbital changes generate just enough tidal flexing to keep a subsurface ocean liquid, at least beneath the south polar region. The ocean might be relatively small, perhaps confined to a layer beneath the southern hemisphere rather than encircling the entire moon. But it's there, and it's in direct contact with space through those cracks, essentially offering free samples to any spacecraft passing by. Cassini flew through Enceladus's plumes multiple times, analyzing their composition. Water vapor, as expected. Salts, indicating the ocean is salty. Molecular hydrogen, suggesting hydrothermal activity on the ocean floor where hot water reacts with rock. Organic molecules, simple ones like methane, but also more complex carbon compounds. Everything needed for life, delivered directly into space where we can study it. We've already sampled Enceladus's ocean, at least partially. We just haven't analyzed the samples thoroughly enough yet. Future missions could do better. A dedicated Enceladus orbiter could fly through the plumes repeatedly, collecting particles, measuring their composition with high-precision instruments. We could search for amino acids, the building blocks of proteins. For lipids, which form cell membranes. For nucleotides, the components of DNA and RNA. For anything that screams biology rather than chemistry. Detection wouldn't be simple. Organic molecules exist in space independent of life. Meteorites contain amino acids formed through non-biological processes. We'd need to identify patterns, ratios of molecules, specific configurations that make sense only in biological contexts. Left-handed versus right-handed amino acids, for example. Life on Earth uses exclusively left-handed amino acids in proteins, even though both forms exist naturally. Finding a strong preference for one-handedness in Enceladus samples would raise serious questions. Or we could look for complexity. Random chemistry produces simple molecules. Biology produces complex ones, polymers, chains of repeating units with specific sequences. DNA is a polymer. So are proteins. Finding long-chain molecules with non-random sequences would be compelling evidence, not definitive proof, but enough to shift the conversation from "might life exist" to "how do we confirm it exists?" Titan, Saturn's largest moon, presents an entirely different puzzle. It's the only moon in the solar system with a thick atmosphere, denser than Earth's, composed primarily of nitrogen with a few percent methane. That methane shouldn't be there. Sunlight breaks methane apart, converting it to more complex hydrocarbons. Without a continuous source, Titan's atmospheric methane should disappear within tens of millions of years. Yet it's still there, suggesting active replenishment from Titan's interior. Titan's surface temperature hovers around -179 degrees Celsius, cold enough that water ice behaves like rock, hard and unyielding. Liquid water can't exist on the surface. But liquid methane can. Titan has lakes, rivers, and seas of liquid methane and ethane, a hydrological cycle running on hydrocarbons instead of water. Methane rains from clouds, flows across the surface, collects in basins, evaporates back into the atmosphere. It's alien yet strangely familiar. Could life exist in liquid methane? Water-based life seems impossible at those temperatures. Biochemistry as we know it relies on water's unique properties, its ability to dissolve many substances, its role in biological reactions. Methane doesn't share those properties. It's a poor solvent, doesn't participate in the same kinds of reactions. Life in methane lakes would require completely different chemistry, different molecular structures, different energy sources. Some scientists propose hypothetical organisms with cell membranes made from compounds that remain flexible at cryogenic temperatures, metabolisms based on reactions between hydrogen and acetylene rather than oxygen and glucose. These organisms would be slow, unimaginably slow, their chemistry proceeding at rates millions of times slower than Earth life. They might take centuries to reproduce, millennia to evolve noticeable changes. But slow doesn't mean impossible. Titan also hides a subsurface ocean, this one made of water mixed with ammonia, buried beneath an ice shell perhaps 100 kilometers thick. That ocean wouldn't host methane-based life, but conventional water-based organisms might thrive there, similar to what we expect on Europa or Enceladus. Titan could potentially host two completely separate biospheres, one in surface methane lakes, another in the deep water ocean, neither aware of the other's existence. Testing these ideas requires landing on Titan, sampling the lakes, analyzing their chemistry. NASA's Dragonfly mission, scheduled to launch in the 2030s, will do exactly that. It's a rotorcraft, essentially a drone, designed to fly through Titan's thick atmosphere, landing at multiple sites, collecting samples, searching for organic molecules and chemical patterns that might indicate biology. Finding life in Titan's methane lakes would revolutionize biology more than finding it on Europa. Europa's ocean resembles Earth's early seas closely enough that life there might operate on similar principles. Titan's surface environment has no Earth analog. Life there would represent a genuinely independent origin, proving that biology isn't limited to water, that the universe might harbor forms of life we haven't imagined yet. Mars complicates the discussion. It's not an ocean world now, but it was once. Billions of years ago, Mars had rivers, lakes, possibly even a northern ocean. Liquid water flowed across the surface under a thicker atmosphere. That Mars could have hosted life, might still host remnants of that ancient biosphere in subsurface aquifers or deep rock formations. Recent discoveries strengthen that possibility. Orbital radar detected what appears to be a large reservoir of liquid water beneath Mars's south polar ice cap, kept liquid by salts that lower water's freezing point. If confirmed, that reservoir could harbor microbial life, organisms surviving in isolation since Mars's surface dried out billions of years ago. Mars also shows seasonal variations in atmospheric methane, concentrations rising and falling in patterns that don't match simple geological explanations. On Earth, methane comes primarily from biological sources, produced by microorganisms in oxygen-poor environments. Martian methane could have biological origins, microbes living underground, releasing methane that seeps to the surface. Or it could come from geological processes, reactions between water and rock that happen to produce methane. We don't know yet. Distinguishing between biological and geological methane requires isotope analysis, measuring the ratios of different carbon isotopes in the methane molecules. Biological processes prefer lighter isotopes, creating characteristic ratios. Future Mars missions will carry instruments capable of that analysis, potentially answering whether Mars's methane hints at hidden life. Venus seems like a terrible candidate for life. Surface temperatures exceed 460 degrees Celsius, hot enough to melt lead. Atmospheric pressure at the surface equals that found nearly a kilometer underwater on Earth. The atmosphere is mostly carbon dioxide with clouds of sulfuric acid. Nothing lives there, surely. But Venus's upper atmosphere, 50 to 60 kilometers above the scorched surface, offers more hospitable conditions. Temperature and pressure there resemble Earth's surface. The clouds contain water droplets, though mixed with sulfuric acid. Some microorganisms on Earth, extremophiles living in acid mine drainage, tolerate similarly harsh chemistry. Could microbes drift through Venus's clouds, floating in the relatively mild upper atmosphere, avoiding the hellish surface below? In 2020, scientists detected phosphine in Venus's atmosphere, a gas that on Earth is produced almost exclusively by anaerobic microbes. Phosphine shouldn't persist in Venus's atmosphere, it should react with other compounds and break down quickly. Its presence suggests active production from some source. Biological production would explain it, though geological processes might also be responsible. The detection sparked intense debate, subsequent observations yielded conflicting results, and the question remains unresolved. Looking for life beyond Earth isn't just about finding microbes in ice or gas signatures in distant atmospheres. It's about understanding whether biology is common or rare, whether Earth represents a cosmic fluke or an inevitable outcome when conditions align. Every ocean world, every atmospheric anomaly, every unexplained chemical signature adds evidence to one side of that fundamental question. The search methods keep evolving. Early approaches assumed alien life would resemble Earth life closely, using the same chemistry, the same energy sources, the same molecular building blocks. Modern astrobiology thinks broader. Life might use different solvents, different genetic molecules, different metabolic pathways. Methane could replace water. Silicon might substitute for carbon. Genetic information could be stored in molecules we haven't considered. This flexibility makes detection harder but more interesting. Biosignatures, the signs life leaves behind, fall into several categories. Atmospheric biosignatures include gases that don't belong, oxygen accumulating where it shouldn't, methane appearing in suspicious patterns, phosphine showing up without clear geological sources. These gases react with other atmospheric compounds, breaking down over time. Their persistence means something keeps producing them. Surface biosignatures include patterns visible from space, regular seasonal changes in color suggesting vegetation cycles, reflectance spectra matching chlorophyll or similar pigments. Temporal biosignatures involve changes over time, day-night variations in atmospheric chemistry, seasonal fluctuations in gas concentrations, patterns that match biological rhythms rather than simple physics. Each type has limitations. Geology mimics biology frustratingly well. Volcanoes produce gases that resemble metabolic waste. Mineral reactions create compounds that look biological. Seasonal temperature changes drive chemical cycles that mirror life's rhythms. Distinguishing biology from geology requires multiple lines of evidence, combinations of signals that together become harder to explain without invoking life. The James Webb Space Telescope changed the game for atmospheric analysis. Its infrared instruments can detect molecular signatures in exoplanet atmospheres during transits, when planets pass in front of their stars. Starlight filters through the planet's atmosphere, certain wavelengths get absorbed by atmospheric molecules, and the resulting spectrum reveals what's present. Webb can detect water vapor, carbon dioxide, methane, ammonia, and more complex organic molecules. Finding oxygen and methane together would be significant. Those gases react with each other, so their coexistence suggests continuous production from some active source. But even that wouldn't prove life conclusively. Jupiter's moon Io has a thin oxygen atmosphere produced entirely by geological processes, radiation breaking apart water molecules frozen on the surface. Methane appears in many planetary atmospheres from purely chemical reactions. The combination becomes interesting, especially if accompanied by other biosignatures, seasonal variations, or unexplained ratios between different isotopes. Searching ocean worlds requires different strategies. We can't directly observe their buried seas. Instead, we look for indirect evidence, plumes of water vapor erupting through surface ice, chemical analysis of that vapor, detection of organic molecules or unusual isotope ratios. Enceladus makes this relatively easy. Its geysers spray ocean water into space where spacecraft can fly through and analyze it. Europa will be harder. Its ice shell is thicker, plumes less frequent, but still potentially detectable. Future missions will carry more sophisticated instruments. Europa Clipper, launching in the 2020s, will conduct dozens of close flybys, using ice-penetrating radar to map the ocean's depth and salinity, analyzing any plume material it encounters, measuring the thickness and structure of the ice shell. If conditions look promising, a follow-up mission might attempt to land, drill through the ice, and deploy a submarine into the ocean below. That mission is decades away, requiring technology that doesn't exist yet, but the concept drives current planning. The technical challenges are immense. Europa's radiation environment is lethal. Jupiter's powerful magnetic field traps charged particles that bombard the Moon's surface. Any lander would need heavy shielding, limiting how long it could operate. Drilling through potentially tens of kilometers of ice requires enormous energy, autonomous operation without real-time control from Earth, and mechanisms that can handle unknown ice compositions and temperatures. The submarine would need to function in complete darkness, navigate without GPS, avoid obstacles it can't see, and operate for months or years on limited power. These aren't problems that stop the mission, they're engineering challenges that get solved incrementally. Each generation of spacecraft pushes capabilities further. Perseverance on Mars carries instruments that earlier rovers couldn't have supported. Webb's mirror deployment, unfolding in space with terrifying precision, seemed impossible when first proposed. Technology advances, budgets fluctuate, but the trajectory points toward increasingly ambitious missions. Finding microbial life would answer one question while raising dozens more. How did it originate? Does it use DNA or something else? How does it metabolize? What's its evolutionary history? Is it related to Earth life, perhaps spread between planets by meteorite impacts, or did it arise independently? That last question matters enormously. One genesis of life in our solar system could be coincidence. Two independent origins would suggest life emerges readily when conditions permit, implying a universe full of biology. Panspermia, the idea that life spreads between worlds, has scientific support. Meteorite impacts can blast rocks into space, some eventually landing on other planets. We found Martian meteorites on Earth, rocks blasted off Mars by ancient impacts that drifted through space before falling here. The journey takes thousands to millions of years, but microbes can survive that, forming dormant spores that withstand radiation, vacuum, and extreme cold. If Earth life originated on Mars and spread here, or vice versa, finding Martian microbes might reveal them as distant cousins of terrestrial organisms, sharing the same genetic code and basic chemistry. Testing that hypothesis requires sequencing alien DNA, if it has DNA, comparing its structure to Earth life, looking for similarities too specific to arise independently. If Martian life uses the same 20 amino acids, the same 4 DNA bases, the same genetic code translating base sequences into proteins, common origin becomes likely. If it uses completely different molecules, independent origin is certain. The philosophical implications cut deep. Religions and philosophies have grappled with humanity's place in the universe for millennia. Finding alien life, even microbes, shifts those discussions fundamentally. We're not unique. Biology isn't a miracle exclusive to Earth. The universe makes life when given the chance. That realization could unify humanity around our shared biological heritage or fracture existing worldviews that place humans at creation's center. History suggests both reactions will occur simultaneously, different cultures and belief systems integrating the discovery in different ways. Science fiction imagined first contact as dramatic, flying saucers landing on the White House lawn, radio signals from distant civilizations. Reality will probably be subtler, a chemical signature in an exoplanet's atmosphere that takes years to confirm, a microscopic fossil in a Martian rock sample, organic molecules in Europa's ocean that match no known geological process. The discovery won't happen in a single moment but through accumulating evidence that gradually shifts scientific consensus. And what if we find nothing? What if Mars is sterile, Europa's ocean empty, Titan's lakes purely chemical? That answer matters too. It would suggest life requires specific conditions we haven't identified, that Earth's combination of factors is rarer than we thought. The galaxy might be full of potentially habitable worlds that remain lifeless because some crucial ingredient is missing. That wouldn't prove we're alone, the universe is too vast, but it would suggest loneliness is possible, that consciousness might be precious because it's rare. Current evidence leans toward optimism. Organic molecules appear everywhere we look, in comets, asteroids, interstellar clouds, even in the atmospheres of planets where they can't support life. The chemistry of life isn't exotic, it's common. Water, once thought rare, turns out to be abundant, locked in ice throughout the outer solar system, probably common around other stars. Energy sources exist anywhere geology stays active: tidal heating, radioactive decay, chemical gradients between different rock types. The ingredients are widespread. Whether those ingredients combine into biology remains unknown. Chemistry becoming life requires specific conditions we're still mapping. Temperature must fall within certain ranges. Too cold and reactions stop, too hot and complex molecules break apart. Liquid solvent is necessary, probably water, though alternatives might work. Energy flow must be steady and sustained, not sporadic bursts. Concentration mechanisms need to exist, ways to accumulate organic molecules rather than letting them drift apart. Protection from radiation helps, thick atmospheres or deep waters shielding fragile chemistry from destructive high-energy particles. Earth had all those conditions simultaneously. Did Mars? Does Europa? The uncertainty drives exploration. Every mission returns data that refines our understanding, narrows the possibilities, points toward where life is most likely. Negative results inform as much as positive ones, each sterile world teaching us what conditions aren't sufficient, helping identify what additional factors matter. The timeline stretches across decades. Sample return from Mars won't happen until the 2030s. Europa exploration extends into the 2040s. Titan submarine missions, if they happen, lie further still. Breakthrough discoveries could accelerate everything. Finding clear biosignatures might trigger urgent follow-up missions with compressed timelines. Or progress might slow, budgets tighten, priorities shift, and the search extends across centuries rather than decades. What remains certain is that the search continues. Humans seem compelled to explore, to push boundaries, to answer fundamental questions about existence. Whether life exists elsewhere ranks among the most fundamental questions we can ask. The answer, whatever it is, reshapes how we understand our place in the cosmos. Finding life beyond Earth wouldn't just answer whether we're alone. It would fundamentally alter how we understand biology itself. Every organism we've studied shares the same basic architecture: DNA, RNA, proteins built from the same 20 amino acids, cells with similar structures. That's not because it's the only way to build life, but because everything alive today descends from a single origin point roughly 4 billion years ago. We've been studying variations on one theme, different arrangements of the same fundamental components. A second genesis would show us an entirely different approach to the problem of being alive. Consider what Martian life might teach us. If we find microbes in subsurface water, the first question becomes how similar are they to Earth organisms? If they use DNA, that's either remarkable convergence, the same solution emerging independently, or evidence of panspermia, life transferring between planets on meteorites. Mars and Earth have exchanged material constantly throughout their histories. Impacts blast rocks into space, some eventually falling onto the other planet. Microbes could survive that journey, protected inside rock from radiation and vacuum. If Martian life shares our genetic code, we'd need to determine whether Mars seeded Earth, Earth seeded Mars, or both were seeded from elsewhere. The implications multiply rapidly. But what if Martian biochemistry is completely different? Different genetic molecules, different amino acids, different cellular organization. That would prove life isn't locked into one configuration, that chemistry can solve the problem of self-replication and metabolism through multiple pathways. Every difference would reveal something fundamental about what life requires versus what's merely one option among many. Does all life need cells, or could some function as connected networks without clear boundaries? Must genetic information be stored in double helix structures, or would other shapes work? The variations would illuminate the core principles underlying all biology. Europa's ocean presents different possibilities. If life exists there, it evolved in darkness, powered entirely by chemical energy rather than sunlight. Earth has similar ecosystems around hydrothermal vents, entire communities thriving on chemicals rather than photosynthesis. But those ecosystems exist alongside photosynthetic life, sharing the same ocean, likely descending from the same origin. Europa's life, if it exists, would have developed independently in perpetual darkness, never knowing sunlight, possibly never developing anything resembling plants. The food chain would start with chemosynthetic microbes and build upward from there. How complex could such an ecosystem become without the energy abundance photosynthesis provides? The energy question matters enormously. Photosynthesis captures sunlight directly, providing massive energy input that drives Earth's biosphere. Chemical energy from geology offers far less, limiting how much biomass an ecosystem can support. Europa's ocean might contain only sparse microbial populations scattered around hydrothermal vents, nothing more complex because insufficient energy exists for larger organisms. Or perhaps life there discovered methods we haven't imagined, ways to extract energy more efficiently, to build complexity with less power. The possibility remains open until we explore. Titan raises even stranger questions. If life exists in liquid methane at -179 Celsius, it's operating on completely alien chemistry. Water-based biochemistry relies on specific properties, how water molecules interact, how they dissolve certain substances while excluding others, how they remain liquid across a temperature range suitable for complex reactions. Methane has different properties entirely. Life using methane as solvent would need different molecules, different reaction pathways, different cellular structures if it has cells at all. We can barely imagine what such organisms would resemble. They might not even be recognizable as life initially, their metabolism so slow and alien that distinguishing biology from geology requires years of study. Each potential discovery carries philosophical weight beyond the scientific. Confirming we're not alone eliminates one form of cosmic loneliness while potentially introducing another. If we find only microbes, simple organisms that never evolved complexity, we'd know life exists elsewhere but might still be alone as conscious beings. The galaxy could be full of bacterial worlds but empty of minds, civilizations, anyone to communicate with. That's simultaneously comforting and isolating, proof that Earth isn't unique in hosting life but confirmation that intelligence might be. The cultural impact would unfold gradually rather than explosively. Religious traditions would adapt as they always have when new information emerges. Some would see divine creation extending beyond Earth, life as something the universe was designed to produce abundantly. Others might view Earth as specially blessed, the only place where God's creation achieved consciousness. Most would probably integrate the discovery into existing frameworks without fundamental disruption. History shows humans are remarkably good at absorbing paradigm shifts while maintaining continuity with the past. Science would transform more dramatically. Astrobiology would shift from theoretical to empirical, from asking whether life exists elsewhere to studying how it works. New fields would emerge, comparative biochemistry examining different solutions to biological problems, xenobiology studying organisms with fundamentally different architecture, ecosystems analysis comparing Earth communities to alien ones. The questions multiply endlessly. How does evolution operate under different conditions? Do alien ecosystems show similar patterns of predator-prey relationships, symbiosis, competition? Does complexity emerge through similar stages everywhere or follow completely different paths? The practical applications might surprise us. Studying organisms adapted to extreme conditions often reveals useful chemistry. Enzymes that function in boiling water now enable DNA analysis techniques. Microbes that survive intense radiation inform medical treatments. Life from Europa might show us how to operate in low-energy environments, relevant for long-duration space missions. Titan organisms could teach us chemistry that works at extremely low temperatures, potentially revolutionizing refrigeration technology or cryogenics. You can't predict what studying alien biology might enable because the discoveries themselves are unpredictable. Search strategies continue evolving. Next-generation telescopes will examine exoplanet atmospheres in unprecedented detail, looking for chemical signatures that suggest biological activity. Oxygen combined with methane creates disequilibrium. The gases react and destroy each other unless something continuously produces them. On Earth, that something is life, photosynthesis making oxygen while bacteria produce methane. Finding that combination around distant stars would warrant intense scrutiny, though geological processes might create similar patterns without biology. The challenge lies in distinguishing life from clever geology across light years of distance. Sample return missions represent the gold standard, bringing material back to Earth where sophisticated laboratories can analyze it thoroughly. Mars sample return launches in the early 2030s, collecting rocks that might contain fossilized microbes or chemical traces of ancient life. Those samples will be studied for decades, examined by technologies that don't exist yet, potentially preserving evidence until analysis methods become sophisticated enough to detect what we currently miss. The same rocks might be reanalyzed by scientists in 2100 using techniques we can't imagine today. The timeline for discovery remains uncertain. It could happen next year, a Martian rover stumbling across clear biosignatures in an unexpected location. Or it might take centuries, requiring technology we haven't developed, missions to destinations we haven't reached. The search itself drives progress regardless of outcome. Building instruments sensitive enough to detect alien life requires advancing multiple technologies simultaneously, better sensors, more sophisticated analysis techniques, improved propulsion for reaching distant targets. Those advances benefit other fields, medical diagnostics, materials science, environmental monitoring. The search pays dividends even before finding anything. What happens if we discover not just life but intelligence? That possibility seems remote within our solar system. No evidence suggests conscious beings exist on Mars or Europa. But the galaxy contains billions of stars, billions of planets, vast distances we've barely begun exploring. If intelligent life exists, we might detect their signals, radio transmissions, or other electromagnetic evidence of technological civilization. Or perhaps they're quiet, either deliberately avoiding detection or simply not broadcasting. The space between stars is enormous, signals weaken with distance, making detection challenging even if civilizations exist. Contact with intelligent aliens would raise questions we can barely formulate. How do you communicate across species that evolved independently, with no shared reference points, possibly no common sensory experience? Mathematics might provide a starting point, universal patterns that any technological civilization would recognize. But moving beyond basic concepts to actual communication requires bridging gaps we've never encountered. Human languages evolve together, sharing deep structure even when superficially different. Alien languages might operate on completely different principles, perhaps not using sound at all, maybe based on chemical signals or visual patterns or something we haven't conceived. The discovery of any life beyond Earth, whether microbial or intelligent, simple or complex, would mark a threshold in human history. We've become the species that learned we're not alone, that answered one of the oldest questions our ancestors asked while staring at stars. That knowledge changes how we see ourselves, our planet, our future. Earth stops being the only known living world and becomes one example among many. Our biology stops being the only known solution and becomes one variation on a theme that plays out across the cosmos. Right now, we exist in uncertainty, not knowing whether life is common or rare, whether the universe teems with biology or whether Earth represents a singular miracle. That uncertainty drives the search forward, propels missions to Mars and Europa and Titan, motivates scientists to keep looking, to keep testing, to keep pushing the boundaries of what we know. The answer waits somewhere in the data we haven't collected yet, in the samples we haven't analyzed, on the worlds we haven't explored. And every mission, every discovery, every new piece of evidence brings us closer to knowing whether we're alone or whether life, in all its strange and wonderful forms, fills the universe around us. The search for life beyond Earth isn't just about finding microbes in ice or detecting unusual gases in distant atmospheres. It's about understanding whether we're witnessing something unique or something inevitable. Every ocean world we study, every atmospheric anomaly we investigate, every chemical signature we can't explain adds weight to one side of that question. Ganymede orbits Jupiter exactly as it has for billions of years. Its ocean sloshes beneath ice that has remained frozen since the solar system's youth. The magnetic field deflects radiation. Tidal forces squeeze the interior rhythmically. None of this changes whether we look or not. The moon exists independent of our curiosity. But we look anyway because understanding Ganymede means understanding how common habitable environments might be throughout the galaxy. The missions we're planning won't answer everything. Europa Clipper will map the ice shell and search for plumes but won't drill through to the ocean. JUICE will orbit Ganymede and measure its gravitational field but won't deploy submarines into the depths. These are reconnaissance missions, gathering data that will inform what comes next. They'll tell us where the ice is thinnest, where tidal heating concentrates, where future landers should aim. They're setting the stage for something more ambitious, missions that actually touch these frozen surfaces and taste the oceans below. That next generation of exploration lies decades away. The technology needs refinement. The funding requires political will that fluctuates with election cycles. The engineering challenges demand solutions we're still developing. But the trajectory is clear. We're moving from observation to investigation, from studying these worlds from afar to directly sampling what they hide. Whether Ganymede harbors life remains unknown. The ocean exists, that's confirmed. Whether chemistry there crossed the threshold into biology depends on factors we're still mapping. But the possibility alone justifies the search. If life arose independently in Jupiter's system, if organisms exist that never saw sunlight, that evolved in darkness powered by tidal forces and chemical gradients, then the universe becomes fundamentally different than we imagined. Life stops being Earth's miracle and becomes the cosmos doing what it does when conditions align. And if we find nothing, if Ganymede's ocean proves sterile despite billions of years and all the necessary ingredients, that answer teaches us something too. It reveals that liquid water and chemical energy aren't sufficient, that life requires additional factors we haven't identified. The search continues either way, moving to Europa, to Enceladus, to Titan, to exoplanets around distant stars. Each investigation refines our understanding, narrows the possibilities, points toward where life is most likely. The answer exists whether we find it or not. Somewhere in the frozen depths of Ganymede or the radiation-blasted ice of Europa or the methane lakes of Titan or the atmospheres of worlds we haven't reached yet, the universe has already decided whether biology emerges readily or remains vanishingly rare. Our searching doesn't change that reality. determines when we learn what's already true. 4.2 light years. That's the distance to our nearest stellar neighbor, Proxima Centauri. In cosmic terms, it's practically next door. In human terms, it's an almost incomprehensible void. And orbiting that dim red star is a world that might harbor the answer to humanity's oldest question: are we alone? On August 24, 2016, scientists announced something extraordinary. They'd found a planet circling Proxima Centauri, tucked right inside the habitable zone where liquid water could exist. The media exploded with headlines about our nearest potentially habitable neighbor. But here's what most of those stories missed: this world might be hiding something far darker than anyone initially realized. Proxima Centauri b sits closer to its star than Mercury does to our Sun. It completes an orbit every 11 days, and despite being in the habitable zone, the conditions there might be so extreme, so utterly hostile, that the very concept of life becomes almost laughable. Let me show you why this discovery changed everything we thought we knew about habitable worlds. The story begins with a star that's been burning for billions of years, yet you'd never see it with your naked eye from Earth. Proxima Centauri is a red dwarf, a stellar ember that glows with barely 1/6 the temperature of our Sun. Its diameter? About 1/7 that of our home star, roughly 1.5 times Jupiter's width. Pack that mass into such a small volume and you get something remarkable: a mean density of 47 grams per cubic centimeter. Compare that to the Sun's density of just 1.4 grams per cubic centimeter. Red dwarfs are the universe's ultimate survivors. While our Sun will burn through its hydrogen fuel in roughly 5 billion years, red dwarfs like Proxima Centauri can keep fusing hydrogen for trillions of years. They're the cosmic equivalent of marathon runners, burning slow and steady while more massive stars sprint through their fuel and die young. But longevity comes with a price. The detection of Proxima Centauri b wasn't accomplished through direct observation. You can't simply point a telescope at the system and snap a photo. The star outshines its planet by a factor of 10 million to 1. Instead, scientists used something called radial velocity measurements. Picture this: as a planet orbits its star, it doesn't just circle around a stationary object. Both planet and star orbit their common center of mass. The star wobbles ever so slightly, pulled by the planet's gravity. That wobble shows up in the star's light. As Proxima Centauri moves toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, the light shifts toward red. These shifts are incredibly tiny, measured in meters per second. The Pale Red Dot Project spent years carefully measuring these subtle changes in Proxima Centauri's light, filtering out the noise, accounting for the star's own variability. When the data finally came together, it revealed an unmistakable signal. A planet with a minimum mass of 1.06 Earth masses, orbiting every 11.2 days at a distance of about 0.05 astronomical units. The excitement was immediate and global. Here was a terrestrial world, roughly Earth size, orbiting in the habitable zone of the closest star to our own. The implications seemed staggering. If life could exist there, we might actually be able to study it within our lifetimes, or at least within the lifetimes of our children or grandchildren. But let's talk about what reaching Proxima Centauri b would actually require. 4.2 light years translates to about 40 trillion kilometers. Our fastest spacecraft, Voyager 1, currently travels at 17 kilometers per second. Sounds fast until you do the math: 73,000 years to reach Proxima Centauri. That's longer than recorded human history. The New Horizons probe, which gave us those stunning images of Pluto, moves at 58,000 kilometers per hour. Still wouldn't get there for 80,000 years. Even theoretical fusion drives, the kind that might be possible within the next century, would need 36 years to make the journey. The Breakthrough Starshot initiative has proposed something more radical: ultra-lightweight probes with light sails, accelerated by powerful ground-based lasers to 20% the speed of light. At that velocity, the trip would take just over 20 years. 20 years to send a probe. Another 4 years for the signal to return to Earth. A generation-spanning project just to get our first close look at this world. And what would we find when we got there? The planet orbits 20 times closer to Proxima Centauri than Earth orbits the Sun. That tight orbit is necessary because red dwarfs emit far less energy than Sun-like stars. Despite this proximity, Proxima Centauri b receives only about 65% of the solar energy that Earth receives. Its equilibrium temperature, the temperature it would have without an atmosphere, sits at around -39 degrees Celsius. Cold. But potentially not too cold if the planet has the right atmospheric composition. A thick atmosphere with sufficient greenhouse gases could trap enough heat to maintain liquid water on the surface. Scientists have run countless climate models, feeding in different variables, varying amounts of water, carbon dioxide, nitrogen. The results span a remarkable range of possibilities. In some simulations, the planet is completely frozen, a snowball world where ice covers every surface. In others, it hosts a global ocean, dark and deep. Some models produce what researchers call an eyeball Earth, where one region of perpetual daylight stays warm enough for liquid water while the rest of the planet remains frozen. Picture a circular zone of habitability, surrounded by glacial wasteland. These different outcomes depend critically on factors we can't yet measure. How thick is the atmosphere? What's it made of? Is there water at all? The uncertainty in the planet's mass adds another layer of complexity. Radial velocity measurements can only tell us the minimum mass because they depend on how the planet's orbit is tilted relative to our line of sight. If we're looking at the orbit edge on, we see the full wobble. If we're looking at it more face-on, the wobble appears smaller, and the planet could be more massive than it appears. Current estimates suggest Proxima Centauri b has a minimum mass of 1.06 Earth masses. But if the orbit is tilted at 47 degrees, coplanar with the star's rotation, the true mass would be closer to 1.44 Earth masses. That difference matters. A more massive planet would have stronger gravity, potentially holding on to its atmosphere more effectively. Or it might simply be a larger world with different geological activity. The formation history of this planet remains murky. Proxima Centauri itself might have been captured by the Alpha Centauri system, meaning it could be younger or older than its stellar companions, which are roughly 5 billion years old. If Proxima Centauri b formed in its current orbit, it would have experienced a hellish early environment. During the star's pre-main sequence phase, when it was much brighter and hotter, the habitable zone would have been farther out. For potentially 180 million years, the planet would have been too close to its star for water to exist as a liquid. Any water present would have evaporated into steam, which ultraviolet radiation would then split into hydrogen and oxygen. The hydrogen, being light, would escape to space. The oxygen might remain, but without hydrogen to bond with, there's no way to recreate water. This scenario resembles what scientists believe happened to Venus. Our sister planet likely had oceans early in its history. A runaway greenhouse effect boiled them away, leaving behind the toxic, superheated world we see today. Could Proxima Centauri b have suffered the same fate? The question of water loss leads us deeper into the planet's potential history. Models suggest the planet might have lost at least one Earth ocean's worth of water during its early years. Some estimates push that number much higher. Without water, the prospects for life dim considerably. But water loss isn't the only concern. There's another problem, one that cuts to the heart of whether this world could ever support life as we understand it. It involves the star's behavior, the planet's atmosphere, and a process of destruction that plays out over millions of years. This problem doesn't announce itself with dramatic headlines, but its implications might be even more devastating than simple water loss. Understanding this threat requires us to look more carefully at what happens when a planet orbits so close to its star, experiencing forces that Earth never encounters. The problem starts with tidal locking. When a planet orbits close enough to its star, gravitational forces act like brakes on its rotation. Over time, these forces slow the planet's spin until one side permanently faces the star while the other remains in perpetual darkness. Earth experiences a milder version of this effect with our moon, which always shows us the same face. The tidal force Proxima Centauri exerts on its planet is 939 times stronger than what the Sun exerts on Earth. That's not a force you can resist. Picture standing on Proxima Centauri B's surface. If you're on the day side, the star never moves in the sky. It hangs there, fixed, casting its dim red light across a landscape that never sees sunset. Walk to the other hemisphere and you enter permanent night, where stars will overhead in their familiar patterns but your own sun never rises. Between these extremes lies the terminator, the boundary zone where day meets night, where the star sits perpetually on the horizon. The consequences extend far beyond strange lighting. On the day side, temperatures soar as the star's radiation pummels the same hemisphere without pause. On the night side, temperatures plunge. Without the cycle of day and night to distribute heat, the planet develops extreme temperature gradients. Climate models suggest the day side could be hot enough to boil water while the night side freezes solid. Between these zones, violent winds would rage as air masses rush from hot to cold, trying desperately to equalize the temperature difference. But here's where things get strange. The night side wouldn't just be cold. It could become a graveyard for the atmosphere itself. As air cools, molecules slow down and lose energy. Cool them enough and gases begin to condense. Carbon dioxide, a common atmospheric component, freezes at -78 degrees Celsius. On a tidally locked world with no heat arriving on the night side, CO2 could literally fall out of the sky as snow, accumulating in massive glaciers of dry ice. The atmosphere would gradually migrate from the night side to the day side, thinning until the planet's air pressure drops to near vacuum levels. Unless something intervenes. A thick enough atmosphere could save the planet through heat transport. Air warmed on the day side would rise, flow toward the night side, cool, and sink, creating massive circulation cells that carry heat around the planet. Earth does this with its Hadley cells, the atmospheric circulation pattern that drives our trade winds. Proxima Centauri b would need something similar, but far more powerful. Climate models that simulate this scenario produce what scientists call an eyeball Earth. Picture a planet mostly covered in ice, with one circular region on the day side where temperatures stay above freezing. From space, it would look like an eye staring back at you, a warm pupil of liquid water surrounded by a white iris of ice. The terminator zone, that band between day and night, might offer the most stable conditions. Not too hot, not too cold. If life exists on this world, it might cling to this narrow strip. Yet tidal locking creates another problem that doesn't announce itself immediately. It concerns magnetic fields. Earth's magnetic field arises from our planet's rotation. As Earth spins, the liquid iron in its outer core churns and flows, generating electrical currents. These currents produce the magnetic field that shields us from solar wind and cosmic radiation. It's a dynamo powered by rotation. Proxima Centauri b rotates once every 11 days, synchronous with its orbit. That's slow. Extremely slow compared to Earth's 24-hour day. The question becomes whether such sluggish rotation can maintain a dynamo. Some models suggest it can't. Without rapid rotation, the currents in the planet's core might not achieve the organization needed to generate a strong magnetic field. Other factors complicate this further. Tidal heating from the star's gravitational pull could warm the planet's interior, potentially disrupting the precise conditions needed for a magnetic dynamo to operate. No magnetic field means no shield. And without a shield, the planet faces the full fury of its star. Proxima Centauri isn't a quiet, stable star like our Sun. It's a flare star, and the distinction matters enormously. Our Sun produces flares occasionally, brief eruptions of energy that can disrupt satellites and power grids. These events make headlines when they occur. Proxima Centauri produces similar events not once in a century, but multiple times per day. Some of these flares are among the most powerful ever recorded in our galaxy. On May 1, 2019, astronomers observed Proxima Centauri suddenly brighten. Over just 7 seconds, the star's ultraviolet output increased by a factor of 14,000. Jets of plasma erupted outward, carrying energy equivalent to 100 times the most powerful flares our Sun produces. The event lasted briefly, but its effects would ripple through the entire planetary system. 50 hours of observations using the Atacama Large Millimeter Array detected 463 separate flare events. Not over years. Over 50 hours. The flares ranged in energy from 10 to the 24th power ergs to 10 to the 27th power ergs. Each lasted between 3 and 16 seconds. The planet orbiting this star faces a barrage of high-energy radiation that makes Earth's environment look gentle by comparison. What happens when such radiation hits a planetary atmosphere? The atmosphere doesn't simply absorb it. High-energy ultraviolet photons carry enough energy to break molecular bonds. When UV light strikes a water molecule, it can split it apart into hydrogen and oxygen. The hydrogen, being light, escapes to space. The oxygen might remain, but without hydrogen to combine with, you can't remake water. Over time, the planet's water inventory decreases, molecule by molecule, until the oceans vanish. Nitrogen faces a similar threat. On Earth, nitrogen makes up 78% of our atmosphere. It's an inert background gas that provides atmospheric pressure and moderates temperature. But nitrogen isn't immune to escape. During periods of intense atmospheric loss, escaping hydrogen atoms can collide with heavier nitrogen atoms and drag them along through a process called hydrodynamic escape. Models suggest that several bars of nitrogen, enough to create an Earth-like atmospheric pressure, could be lost in just a few million years. NASA scientists ran a simulation. They placed Earth in Proxima Centauri B's orbit and watched what happened. The model showed Earth's atmosphere being stripped away 10,000 times faster than it loses atmosphere in its actual orbit around the Sun. 10,000 times faster. At that rate, an Earth-like atmosphere wouldn't last 10 million years. The planet would be left bare. The early history of Proxima Centauri B makes this scenario even more likely. During its pre-main sequence phase, before the star settled into stable hydrogen fusion, Proxima Centauri was much brighter and hotter. Its habitable zone lay farther out. If the planet formed in its current orbit, it would have spent approximately 180 million years too close to the star for water to remain liquid. Any water present would have boiled away. The resulting steam would have been broken apart by ultraviolet radiation, and the hydrogen would have escaped to space. This is the runaway greenhouse effect, the same process that transformed Venus from a potentially habitable world into the hellscape we observe today. Venus likely had oceans early in its history. The greenhouse effect boiled them away. The water split into hydrogen and oxygen. The hydrogen escaped. Now Venus has a thick atmosphere of carbon dioxide, surface temperatures hot enough to melt lead, and not a drop of water anywhere. Could Proxima Centauri B be our nearest cosmic neighbor and simultaneously a dead world, stripped of its water before life ever had a chance to begin? The evidence points uncomfortably in that direction. Yet some possibilities remain. Perhaps the planet formed farther out and migrated inward after the star stabilized. Perhaps it had such an enormous initial water inventory that some survived despite massive losses. Perhaps a thick hydrogen envelope protected the planet during its early years, a scenario called the habitable evaporated core hypothesis. These scenarios require specific conditions, fortunate circumstances, a series of events that had to unfold in precisely the right order. The odds don't look favorable. But the universe is vast, and improbable things happen. The question becomes whether we can determine what actually occurred without going there, without directly observing this world that remains hidden in its star's glare. Observing this planet presents a challenge unlike almost any other in astronomy. Proxima Centauri outshines Proxima Centauri b by a factor of 10 million. 10 million to 1. The planet's reflected light drowns completely in the star's overwhelming glare. We can't see it directly. We know it exists only because its gravity tugs on Proxima Centauri as it orbits, creating a tiny wobble detectable through precise measurements of the star's spectrum. This wobble shifts the star's light toward the blue when the planet pulls it toward us, and toward the red when it pulls away. From these shifts, we calculate the planet's mass and orbit. But we learn nothing about its surface, its atmosphere, or whether water exists anywhere on it. The James Webb Space Telescope represents our best current hope for breaking through this observational barrier. Webb's infrared capabilities could detect heat signatures from the planet's surface, revealing temperature patterns that would tell us whether an atmosphere exists and how efficiently it transports heat. If the planet is tidally locked, the day side should be significantly warmer than the night side. Measuring this temperature difference would confirm the lock and provide crucial information about atmospheric thickness. A thin atmosphere can't move heat effectively. A thick one creates more uniform temperatures across the surface. The difference between these scenarios means the difference between a lifeless rock and a potentially habitable world. But here's the technical problem. Even Webb can't easily separate the planet's faint infrared glow from the star's light. The angular separation between Proxima Centauri and Proxima Centauri b, as seen from Earth, is incredibly small. Specialized techniques using coronagraphs or star shades, which block the star's light while allowing the planet's light through, might work. These methods have been used successfully on other exoplanets, but Proxima Centauri b presents unique difficulties because of its proximity to its host star. Future ground-based telescopes offer another approach. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter. This enormous light-gathering power, combined with adaptive optics that correct for atmospheric distortion, could achieve the contrast ratio necessary to directly image Proxima Centauri b. Direct imaging would allow spectroscopy, the analysis of light at different wavelengths to identify specific molecules in the planet's atmosphere. Water vapor, carbon dioxide, oxygen, methane. Each leaves a distinct fingerprint in the spectrum. Finding these molecules would transform our understanding of the planet's condition. Spectroscopy could reveal something unexpected. An oxygen-rich atmosphere on Proxima Centauri b wouldn't necessarily indicate life. On Earth, oxygen comes primarily from photosynthesis, making it a potential biosignature. But on a planet that lost its water through atmospheric stripping, oxygen could accumulate as a byproduct of water destruction. UV radiation splits water molecules. Hydrogen escapes. Oxygen, being heavier, remains behind. Over billions of years, this process could create an oxygen-rich atmosphere on a completely dead world. Scientists call this a false positive, a biosignature that doesn't actually indicate biology. Distinguishing between biological and abiological oxygen requires detecting other molecules simultaneously. Methane alongside oxygen suggests life, because these gases react with each other and shouldn't coexist unless something continuously produces them. The atmospheric models paint wildly different possible pictures of this world. If Proxima Centauri b is tidally locked with a thin atmosphere, most scenarios show an eyeball Earth configuration. One side faces the star perpetually. The intense radiation heats this region, potentially keeping a circular area of liquid water surrounded by ice that extends toward the night side. The night side itself remains frozen, possibly covered in thick ice sheets or even frozen nitrogen and carbon dioxide. The terminator, the boundary between day and night, might be the only temperate zone, a narrow ring where temperatures allow liquid water and where life, if it exists, would cluster. But this assumes the planet has water at all. The alternative scenario depicts something far bleaker. If atmospheric escape stripped away the oceans during the planet's early history, Proxima Centauri b might resemble Mars, a cold desert world with a thin atmosphere insufficient to support liquid water at any temperature. Surface pressure matters critically here. Water can't remain liquid below a certain atmospheric pressure regardless of temperature. On Mars, with surface pressure less than 1% of Earth's, liquid water is impossible except in the deepest depressions. If Proxima Centauri b lost most of its atmosphere, it lost the ability to host surface water even if some water ice remains underground. Another possibility involves a thick carbon dioxide atmosphere similar to Venus. If the planet retained significant volatiles but lost its water, carbon dioxide released from volcanic activity over billions of years could build up, creating a dense greenhouse atmosphere. Surface temperatures on such a world would be extreme, potentially reaching several hundred degrees Celsius. The pressure at the surface could be tens or even hundreds of times Earth's atmospheric pressure. This scenario creates a planet within the habitable zone by distance but rendered uninhabitable by its own atmospheric evolution. The magnetic field question adds another layer of uncertainty. Earth's magnetic field, generated by a dynamo in its liquid iron outer core, shields our atmosphere from the solar wind. Proxima Centauri b's rotation rate matters enormously for magnetic field generation. If the planet is tidally locked, rotating once every 11.2 days, this slow rotation might be insufficient to drive a dynamo. Without a magnetic field, the stellar wind hits the atmosphere directly. Charged particles strip away atmospheric molecules through a process called sputtering. The stellar wind at Proxima Centauri b's orbital distance is estimated to be 10 to 1,000 times denser than the solar wind at Earth's orbit. The pressure is roughly 10,000 times greater. This relentless bombardment, sustained over billions of years, would erode any atmosphere that isn't protected by a magnetic field or continuously replenished by volcanic outgassing. But rotation isn't the only factor determining magnetic field strength. Some planets generate fields through alternative mechanisms. Tidal heating, if the planet's orbit is slightly eccentric, could keep the interior molten and convecting even without fast rotation. Jupiter's moon Io demonstrates this principle. Io has intense volcanic activity driven entirely by tidal heating from Jupiter's gravity. If Proxima Centauri b experiences similar tidal forces, its interior might remain hot enough to generate a magnetic field despite slow rotation. This would provide crucial protection for any atmosphere. The uncertainty surrounding all these factors makes prediction nearly impossible. We're dealing with a system where every parameter influences every other parameter. The presence or absence of water affects atmospheric composition, which affects greenhouse heating, which affects temperature distribution, which affects whether water can remain liquid. The magnetic field affects atmospheric retention, which affects pressure, which affects whether liquid water is possible. The planet's formation history affects its initial volatile inventory, which affects everything that follows. We're trying to solve an equation with dozens of unknowns. What we need is direct observation. Not models, not simulations, but actual data from the planet itself. The technology to obtain this data is developing rapidly. Within the next decade, new telescopes and instruments will come online with capabilities specifically designed for characterizing nearby rocky exoplanets. Proxima Centauri b will be among the first targets. These observations won't be easy. Even with the best instruments, extracting a planetary signal from the overwhelming stellar glare requires sophisticated data processing and long observation times. But the payoff justifies the effort. Confirming the presence or absence of an atmosphere, detecting specific molecules, measuring surface temperature. Each piece of data narrows the range of possibilities and brings us closer to understanding what this world actually looks like. There's also the possibility of detecting technosignatures, signs of technology if an advanced civilization exists there. Radio telescopes have searched for artificial signals from Proxima Centauri. So far, they've found nothing. But absence of evidence isn't evidence of absence. A civilization using technologies we haven't imagined wouldn't produce the radio signatures we're looking for. Or perhaps they exist but aren't broadcasting. Or perhaps they existed in the past and are now gone. Or perhaps they never arose at all because the planet's conditions proved too hostile for complex life to develop. The distance to Proxima Centauri, while vast by human standards, is tantalizingly close in cosmic terms. 4.2 light-years. If we could send a probe there, traveling at 20% light speed as proposed by the Breakthrough Starshot initiative, it would arrive in approximately 21 years. The engineering challenges are immense. Accelerating a spacecraft to that velocity requires lasers far more powerful than anything currently built. The probe would need to be incredibly small and light, essentially a computer chip with a light sail. It couldn't carry much scientific equipment. And it couldn't slow down upon arrival, meaning it would have only a brief window to gather data as it flew past at tremendous speed. But imagine what that flyby could reveal. Direct images of the planet's surface. Measurements of its magnetic field. Spectroscopic analysis of its atmosphere from close range. Confirmation of whether oceans exist. Detection of biological or geological activity. 21 years to reach it. 21 more for the data to return to Earth. 42 years total. Long by human timescales, but achievable within a single lifetime. The people who launch such a mission could live to see its results. Until we actually visit Proxima Centauri b, however, all this remains theoretical. The reality check comes when you consider the sheer engineering difficulty of getting there. Even Breakthrough Starshot, the most ambitious proposal currently under serious consideration, faces challenges that make building the James Webb Space Telescope look straightforward. You need a laser array powerful enough to accelerate a gram-scale spacecraft to 60 million meters per second. That's not just powerful. It's apocalyptically powerful. The combined laser output would need to reach something like 50 to 100 gigawatts, focused with extraordinary precision onto a sail measuring only a few meters across. At full power, this laser system would be visible from Proxima Centauri itself. An alien civilization there with telescopes pointed our way would see a bright flash from Earth lasting several minutes as the acceleration phase completed. They'd know something had just been launched toward them. The spacecraft itself couldn't carry much instrumentation. At those velocities, hitting a dust grain delivers energy equivalent to an exploding hand grenade. The craft needs shielding, but shielding adds mass, and mass is the enemy of acceleration. Every gram counts. You're essentially trying to pack scientific instruments, power systems, communication equipment, and shielding into something weighing less than a postage stamp. And there's no slowing down. The craft would scream past Proxima Centauri b at 20% light speed, crossing the entire planetary system in minutes. Whatever data gets collected must be transmitted back to Earth during that brief window, across 4.2 light-years of space, using a transmitter powered by something smaller than your phone. The technical problems multiply the more you examine them. Interstellar space isn't empty. It contains hydrogen atoms, maybe 1 per cubic centimeter. At 20% light speed, those atoms hit with the energy of radiation. The accumulated dose over 4.2 light-years would destroy most electronics unless heavily shielded, which again adds mass. Cosmic rays present another hazard. High-energy particles from distant supernovae and active galactic nuclei constantly bombard the spacecraft. One unlucky hit to a critical component ends the mission. With such a tiny craft, redundancy is nearly impossible. Then there's aiming. At 20% light speed, the spacecraft crosses the distance to the Moon in about 6 seconds. A targeting error of 1 degree means missing Proxima Centauri b by millions of kilometers. Course corrections during flight require propulsion systems, which add mass and complexity. The laser acceleration phase must be extraordinarily precise. Communication presents its own nightmare. The data transmission from the flyby travels back to Earth at light speed, taking 4.2 years to arrive. The signal strength decreases with the square of distance. By the time it reaches Earth, the received power is measured in attawatts. That's 10 to the negative 18th watts. Detecting it requires enormous receiving antennas and signal processing techniques that filter the spacecraft's transmission from the ocean of cosmic radio noise. Despite all this, breakthrough starshot remains the most plausible method for reaching Proxima Centauri b within a human lifetime. The alternatives are worse. Chemical rockets are hopeless. The tyranny of the rocket equation makes interstellar travel impossible with chemical propulsion. You'd need more fuel than exists in the solar system to reach even a small fraction of light speed. Nuclear propulsion helps, but not enough. Project Daedalus, designed in the 1970s, proposed using fusion rockets to reach Barnard's star. The spacecraft would have massed 50,000 tons, mostly fuel, and required technology we still don't have 50 years later. It could reach 12% light speed, making the trip to Proxima Centauri in about 36 years. But building it requires mining helium, free from Jupiter's atmosphere, and assembling the craft in orbit. The project would cost trillions and take decades of preparation. Antimatter propulsion offers better efficiency but faces the problem that antimatter doesn't exist naturally. Every gram must be manufactured in particle accelerators. Current production rates measure in nanograms per year. Scaling up to the quantities needed for interstellar flight would require energy production far beyond current global capacity. Generation ships avoid the speed problem by accepting the journey will take thousands of years. You build a self-sustaining habitat, launch it on a slow trajectory, and the descendants of the original crew arrive at the destination. This creates biological and social problems that make the engineering look simple. How do you maintain genetic diversity in a population of a few thousand over hundreds of generations? How do you preserve knowledge and purpose across millennia? What happens when the ship arrives and the inhabitants have evolved a completely different culture with no memory of why the journey began? Each propulsion method hits fundamental limits. Physics doesn't provide obvious solutions. We can't manipulate spacetime to create wormholes or warp drives. Those concepts remain firmly in the realm of speculation, requiring exotic matter with negative mass or energy densities that might not exist. So for the foreseeable future, Proxima Centauri b remains out of reach. We can observe it with telescopes. We might eventually send tiny probes. But human visitors? That requires either revolutionary breakthroughs in physics or a commitment to multi-generational projects that our civilization hasn't demonstrated the stability to undertake. Which brings us back to the question of what we're actually observing. Without direct investigation, how certain can we be about conditions at Proxima Centauri b? The answer is we can't be certain at all. We're making educated guesses based on limited data. The planet's mass comes from radial velocity measurements that only give minimum values. Its radius is unknown because it doesn't transit. The atmospheric composition is completely unconstrained. The surface conditions are modeled, not measured. Different research teams using different assumptions produce wildly different conclusions. One study finds the planet could maintain liquid water on its surface. Another concludes it's a desiccated rock stripped of volatiles billions of years ago. A third suggests it's an ocean world with no land masses. A fourth proposes it's completely frozen. They're all working from the same observational data. The divergence comes from different choices about unknown parameters. How much water did the planet start with? How strong is its magnetic field? What's the atmospheric composition? How efficient is heat transport from dayside to nightside? Each assumption cascades through the models, producing dramatically different outcomes. Change one parameter and a habitable world becomes a frozen wasteland. Change another and the frozen wasteland becomes a scorched desert. This isn't sloppy science. It's the reality of studying a world you can't directly observe. You build models based on physics and chemistry, plug in the parameters you know, make reasonable guesses about the parameters you don't know, and see what comes out. Then you try different guesses and see how much the results change. What emerges is a probability distribution rather than a single answer. Proxima Centauri b might be habitable. It might be completely hostile. The observations we have don't definitively exclude either possibility. The situation improves as telescope technology advances. Instruments coming online over the next decade will directly image nearby exoplanets, separating their light from their host stars. Spectroscopy of that light reveals atmospheric composition. The presence of water vapor, oxygen, methane, carbon dioxide, each molecule leaves distinctive absorption lines in the spectrum. But even spectroscopy has limits. Detecting biosignatures requires more than just finding oxygen. Oxygen can be produced by non-biological processes. Ultraviolet radiation splits water molecules, releasing oxygen that accumulates if the planet lacks a mechanism to remove it. A lifeless world stripped of its oceans could have an oxygen-rich atmosphere, mimicking the signature of a living planet. True confirmation requires detecting combinations of gases that wouldn't coexist without life maintaining them. On Earth, oxygen and methane react with each other. They only persist together because biological processes continuously replenish both. Finding that combination on Proxima Centauri b would be compelling evidence for life. The observations won't be easy or quick. Extracting a planetary spectrum from stellar glare requires long integration times and sophisticated data processing. Early attempts will have large error bars. Confirming the presence of specific molecules takes multiple observations with different instruments to rule out false positives. And that's assuming the planet has an atmosphere thick enough to produce detectable spectral features. If stellar activity stripped away most of the atmosphere millions of years ago, there might not be enough gas left to characterize. The timeline stretches across decades. Even if the James Webb Space Telescope begins characterizing Proxima Centauri B's atmosphere tomorrow, confirming habitability or proving its absence requires accumulating enough data to be statistically certain. One observation isn't enough. You need repeated measurements across different wavelengths, different orbital phases, different stellar activity states. Each observation campaign takes months to schedule, execute, and analyze. The scientific process moves deliberately because mistakes are costly. Announce the detection of a biosignature and later discover it was instrumental noise or contamination, and credibility evaporates. The standards for extraordinary claims remain appropriately high. But here's what makes Proxima Centauri B uniquely frustrating compared to other exoplanets. Its proximity should make it easier to study. For light years is nothing in astronomical terms. The planet's light should be readily accessible to our most powerful instruments. Except it's not. Proxima Centauri itself becomes the obstacle. The star's variability creates noise that drowns out the planetary signal. During flare events, extracting anything about the planet becomes nearly impossible. The electromagnetic screaming of the star overwhelms every detector. Between flares, the star's baseline variability still fluctuates enough to complicate measurements. Imagine trying to photograph a firefly next to a strobe light. That's the observational challenge in simplified form. Distance also eliminates certain investigation methods entirely. We're not sending probes to Proxima Centauri B. Not with current technology. Not with near-future technology. Not within any timeframe relevant to current civilization. The Voyager spacecraft, humanity's most distant emissaries, travel at about 17 kilometers per second. At that velocity, reaching Proxima Centauri takes over 73,000 years. Proposals for faster propulsion exist. Nuclear pulse propulsion. Fusion drives. Antimatter rockets. Each faces engineering challenges that remain theoretical. The Breakthrough Starshot initiative proposes light sails accelerated by ground-based lasers to 20% light speed. That reduces transit time to roughly 20 years. But the engineering obstacles are immense. The sail must survive acceleration forces that would vaporize conventional materials. The laser array requires power generation exceeding most nations' total output. And deceleration upon arrival has no proposed solution. A probe traveling at 20% light speed doesn't stop when it reaches the target. It flashes through the system in hours, gathering data at a rate that might fill a few hard drives before disappearing back into interstellar space. So we're left with remote sensing, telescopes, spectroscopy, inference from physics. Which brings us to perhaps the strangest aspect of the entire situation. Everything we know about potentially the most important planet humanity has ever discovered comes from watching a star wobble. The planet itself has never been directly observed. Every specification, every model, every conclusion derives from how Proxima Centauri moves in response to gravitational tugs. The Doppler method measures velocity changes as the star moves toward and away from Earth. Those velocity changes imply a mass. The timing of those changes implies an orbital period. The orbital period implies a distance. The distance combined with stellar luminosity implies a temperature. Every step introduces uncertainty. Every inference rests on assumptions. Consider what happens if one fundamental assumption is wrong. Current models assume Proxima Centauri B is a rocky planet like Earth or Mars. But what if it's not? What if it formed as a mini-Neptune with a massive hydrogen envelope? The radial velocity measurements would look identical. A hydrogen-rich world in Proxima Centauri's habitable zone presents completely different prospects for life. The surface, if it exists, would be buried under thousands of kilometers of atmospheric pressure. No liquid water. No rocky substrate for chemistry. Just compression and heat increasing with depth until rock becomes fluid. Or what if the planet formed elsewhere and migrated inward? Planetary migration is common in solar system formation. Worlds don't necessarily stay where they form. Jupiter probably formed farther from the Sun and moved inward before reversing course. If Proxima Centauri be formed in the outer system and drifted toward the star, it could have started with a very different volatile inventory than a planet that formed in place. Migration scenarios affect everything. Water content, atmospheric composition, internal structure. A migrated planet might have captured more water during formation than a locally formed one. Or it might have had its atmosphere stripped during the migration process itself as it passed through regions of intense stellar radiation. The point isn't that any specific alternative is more likely. The point is that multiple scenarios fit the available data. Until direct observation constrains the possibilities, uncertainty dominates. This matters more than it might seem. Public discussion of Proxima Centauri b often treats habitability as a binary question. Either the planet supports life or it doesn't. Reality is messier. Habitability exists on a spectrum. A planet might be marginally habitable. Habitable in the past but not now. Habitable only in specific regions. Habitable but lifeless because life never arose. Each outcome has different implications. Take the scenario where Proxima Centauri b once had liquid water but lost it billions of years ago. That world teaches us about atmospheric escape mechanisms around red dwarfs. It provides data on how stellar radiation interacts with planetary magnetospheres. It constrains models of water loss that apply to thousands of other exoplanets. Scientifically valuable, even if disappointing for those hoping to find life. Now consider the alternative where Proxima Centauri b currently maintains liquid water on its surface despite stellar activity. That would revolutionize our understanding of habitability. It would mean planets can thrive in radiation environments we previously considered sterilizing. The habitable zone concept would need revision. The number of potentially life-bearing worlds in the galaxy increases by orders of magnitude. You see the stakes. This isn't just about one planet. It's about calibrating our expectations for billions of others. Red dwarfs comprise about 75% of all stars in the Milky Way. If their planets can be habitable despite intense stellar activity, the universe becomes far more hospitable to life. If they can't, potentially habitable real estate shrinks dramatically. Proxima Centauri b is the test case. The nearest example. The one we'll characterize first. Whatever we learn there propagates through all subsequent exoplanet research. The waiting is difficult. When the discovery was announced in 2016, excitement peaked immediately. News coverage treated the finding as a potential second Earth. Headlines implied we'd found humanity's future home. Public expectation raced ahead of scientific reality. Then the follow-up studies emerged. The radiation environment looked hostile. Atmospheric stripping seemed likely. Models suggested the planet might be tidally locked, complicating habitability. Enthusiasm cooled. Not because the planet became less interesting scientifically, but because the simple narrative collapsed under detailed scrutiny. What remains is something more complex and ultimately more fascinating than the initial story. Proxima Centauri b might be habitable. The conditions allowing that habitability would differ dramatically from Earth. Life there, if it exists, would face challenges terrestrial organisms never encountered. The evolutionary paths would diverge from anything in our biosphere. Understanding those differences matters more than finding a cosmic twin. Earth-like planets are interesting because they're familiar. Alien worlds are interesting because they expand our conception of what's possible. A habitable planet around Proxima Centauri wouldn't be Earth-like in any meaningful sense. It would be Proxima-like. A product of its specific environment, adapted to its specific challenges, existing under conditions we're still learning to model. That world, if we ever characterize it properly, teaches us what life looks like when it evolves under a red sun. When stellar flares are routine rather than catastrophic. When one hemisphere never sees night and the other never sees day. When the concept of seasons doesn't exist because orbital periods last 11 days. The question isn't whether we find life there. The question is whether we'd recognize it if we did. Recognition requires frameworks. Categories we've already defined. When scientists search for biosignatures in exoplanet atmospheres, they look for specific molecular combinations. Oxygen and methane together. Phosphine in unusual concentrations. Molecules that shouldn't coexist in equilibrium chemistry but do when life mediates the reactions. Those searches assume biochemistry operates similarly everywhere. Carbon-based metabolism. Water as a solvent. Energy gradients life can exploit through familiar pathways. But what if Proxima Centauri b developed something fundamentally different? Not just exotic biochemistry using different solvents or elements, but information processing systems we wouldn't classify as alive using terrestrial definitions. The philosophical problem deepens when you consider detection methods. We search for what we know to search for. Oxygen in an atmosphere stands out because Earth's oxygen comes almost entirely from photosynthesis. But Proxima Centauri b could have oxygen from photolysis, water molecules broken apart by intense UV radiation, leaving oxygen behind without any biological input. That oxygen-rich atmosphere might look like a biosignature when it actually signals the opposite. A dead world that lost its water. Similarly, methane on Earth mostly comes from biological sources. On Proxima Centauri b, geological processes could produce methane through serpentinization, where water reacts with iron-rich rocks. Or atmospheric chemistry under different radiation conditions could generate methane abiotically. The same molecule, completely different origin. This ambiguity isn't just academic. It determines how we interpret observations. When James Webb Space Telescope finally captures a spectrum of Proxima Centauri b's atmosphere, assuming it has one, those spectral lines represent our only data. We build entire narratives around molecular signatures, but the story we tell depends entirely on our assumptions about what those signatures mean. False positives haunt exoplanet research. Venus looked potentially habitable before we understood its atmospheric chemistry. Mars appeared to have seasonal vegetation changes that turned out to be dust storms. Even Earth, if observed from interstellar distances during certain geological epochs, might not show obvious biosignatures. The early Earth had life but no oxygen. An alien civilization searching for habitable worlds might have dismissed our planet as sterile for its first 2 billion years. The inverse problem also exists. False negatives. Life that doesn't produce detectable atmospheric signatures. Subsurface biospheres. Organisms that metabolize in ways that don't leave obvious chemical fingerprints. An ocean world with life confined to hydrothermal vents wouldn't necessarily show biosignatures in atmospheric spectra. We'd categorize it as barren when it actually teems with complex ecosystems. Proxima Centauri b could harbor life we'd never detect remotely. Imagine organisms adapted to survive in cracks within tidally heated rocks. Or microbial communities living in briny underground aquifers, insulated from the radiation-blasted surface. These scenarios are biologically plausible. Earth's deep biosphere extends kilometers underground, comprising a significant fraction of our planet's total biomass. But you'd never know it existed by analyzing atmospheric composition from space. The detection problem becomes even more complicated when you consider non-biological complexity. Could Proxima Centauri b have something that processes information and responds to environmental conditions without being alive in any sense we'd recognize? Autocatalytic chemical networks that maintain themselves far from equilibrium. Mineral systems with emergent organizational properties. Phenomena that blur the boundary between chemistry and biology without crossing it. These aren't idle speculations. They're questions about the limits of our conceptual framework. Life as we know it represents one solution to the problem of maintaining order against entropy. But the universe is large and has been running experiments for billions of years. The probability that Earth's solution is the only viable one seems vanishingly small. This brings us to the spacecraft problem. Even if we can't detect life remotely, we could potentially visit Proxima Centauri b directly. The Breakthrough Starshot initiative proposes launching thousands of tiny spacecraft accelerated by ground-based lasers to 20% light speed. At that velocity, the journey takes just over 20 years. 20 years sounds manageable. A mission launched today could return data within a human lifetime. But the engineering challenges are staggering. The spacecraft would need to survive interstellar space for 2 decades, endure particle impacts at relativistic speeds, and function perfectly upon arrival without any possibility of repair or recalibration. And here's the critical limitation. At 20% light speed, you can't slow down. These wouldn't be orbiters or landers. They'd be flyby probes, screaming past Proxima Centauri b at 60,000 kilometers per second, collecting data during a brief window lasting minutes or possibly seconds. Then continuing into interstellar space forever. The data return would be extraordinary even from a flyby. Direct imaging of the planet's surface. Atmospheric composition measurements. Magnetic field detection. Particle environment characterization. Questions that would take decades to answer with telescopes could be resolved definitively in minutes. But a flyby can't search for life comprehensively. Can't orbit to study different regions. Can't descend to the surface to analyze soil chemistry. Can't drill through ice to sample subsurface oceans. The spacecraft either detects obvious signatures during its brief passage or the question remains unanswered. More sophisticated missions would require deceleration upon arrival. That changes everything. The mass budget explodes. Carrying enough fuel to slow from 20% light speed back to orbital velocities makes the spacecraft too massive to accelerate in the first place. Nuclear pulse propulsion might work, but the engineering becomes fantastically complex. Project Daedalus, designed in the 1970s, proposed a fusion-powered starship that could reach nearby stars within a human lifetime. The spacecraft would mass 54,000 tons, mostly fuel, and use controlled thermonuclear explosions for propulsion. Modern recalculations suggest a modified Daedalus could reach Proxima Centauri in about 36 years. 36 years from launch to arrival. Another 4 years for signals to return to Earth at light speed. A mission launched today would return its first results around 2065. Within the lifetime of people currently alive, barely. The generational question looms. Would civilization maintain interest in a mission spanning 4 decades? Would the scientists who designed it still be alive when data arrives? Would humanity even remember launching it by the time results come back? Historical precedent suggests maybe. Voyager 1 launched in 1977. It's still transmitting data 48 years later. New Horizons launched in 2006, reached Pluto in 2015, and continues exploring the Kuiper Belt. We've demonstrated the ability to maintain missions across decades when the scientific payoff justifies the investment. But those missions explored our own solar system. Proxima Centauri b exists in another star system entirely. The psychological distance matters. It's not ours. It's fundamentally alien territory. The emotional investment differs from exploring planets that orbit our own sun. Yet the scientific justification couldn't be stronger. Every question about exoplanet habitability, atmospheric evolution, and the prevalence of life in the universe comes into sharper focus with data from Proxima Centauri b. It's the calibration point. The ground truth. The one exoplanet close enough to study in detail within foreseeable technological capabilities. The alternative is waiting for better telescopes, larger mirrors, more sensitive instruments, space-based interferometers. Each generation of observatory provides more detailed atmospheric spectra. Eventually we might resolve surface features directly. But remote observation always leaves ambiguities. Always requires inference. Always depends on assumptions about atmospheric chemistry and planetary conditions. Only a spacecraft provides certainty. Direct measurement. Unambiguous data. The difference between believing a planet has water vapor in its atmosphere and actually detecting that vapor with instruments physically present in the planet's vicinity. So we face a choice. Commit resources to an interstellar mission knowing the returns won't arrive for decades. Or continue improving remote observation capabilities, accepting the limitations inherent in analyzing starlight filtered through a distant atmosphere. The decision reveals something about our species. Are we patient enough to plant seeds we won't harvest? Willing to invest in knowledge that benefits future generations more than ourselves? Or do we demand immediate returns, relegating interstellar exploration to Sunday when it's easier? Proxima Centauri b doesn't care about our timeline. It orbits its star every 11 days regardless of whether we're watching. If it has life, that life evolved without waiting for humanity's permission. If it's barren, those empty landscapes exist independent of our curiosity. The planet represents a test. Not of habitability, but of human ambition. Whether we're content to wonder from a distance or willing to close the gap between speculation and knowledge. Whether the nearest potentially habitable world beyond our solar system remains forever a subject of astronomical study or becomes a destination. Right now it's a data point. A planet detected through the wobble it induces in its star's motion. A mass estimate. An orbital period. A position in the habitable zone. Numbers in a database alongside thousands of other exoplanets. But it could become more than that. The first extrasolar world we visit. The place where we discover whether habitable means inhabited. The planet that teaches us what life looks like when it evolves under a red sun's violent gaze. Everything depends on what we choose to do with the knowledge that it's there, waiting, just 4.2 light-years away. So here we are, standing on Earth, staring outward at a world that sits closer to us than any other star system, yet might as well exist in another universe entirely. Proxima Centauri b occupies this strange position in human consciousness. Close enough to feel relevant. Far enough to remain fundamentally unknowable with current technology. The dark secret wasn't what we expected when the discovery was announced in 2016. Headlines proclaimed a potential second Earth. The reality proved far more nuanced and considerably more hostile. A planet bombarded by radiation that would strip Earth's atmosphere in geologic heartbeats. Flares that erupt not once per century but multiple times daily. Stellar wind pressure 10,000 times what Earth experiences. Tidal forces 900 times stronger than what the Sun exerts on our world. These aren't minor complications. They're fundamental challenges to the very concept of habitability around red dwarf stars. And red dwarfs comprise 3/4 of all stars in the galaxy. If their planets can't maintain atmospheres, can't retain water, can't develop protective magnetic fields, then the universe becomes a much lonelier place than we hoped. But the story doesn't end with hostility. It deepens. Because Proxima Centauri b might have survived anyway. Might have maintained its atmosphere through some combination of factors we haven't fully modeled. Might have enough volcanic outgassing to replenish what stellar activity strips away. Might possess a magnetic field generated through mechanisms we don't yet understand. Might host liquid water in protected regions even while the rest of the surface freezes or burns. The uncertainty isn't a failure of science. It's the current state of knowledge about a world we've never directly observed. Every model depends on assumptions about parameters we can't measure. Change those assumptions and a frozen wasteland becomes a habitable ocean world. Change them again and the ocean world becomes a desiccated rock. What makes this frustrating is that the planet sits right there. 4.2 light-years. The nearest star system. If habitability exists anywhere beyond our solar system that we could potentially verify within a human lifetime, it's there. Yet it might as well be in another galaxy given our current propulsion capabilities. The telescope observations coming online over the next decade will help. James Webb Space Telescope can characterize atmospheric heat transport if the planet has a thick enough atmosphere. Ground-based extremely large telescopes might achieve the contrast ratios needed for direct imaging. Spectroscopy could reveal molecular signatures that indicate water vapor, oxygen, methane, carbon dioxide. But spectroscopy has limits. Finding oxygen doesn't necessarily mean finding life. Oxygen accumulates on dead worlds that lost their water through photolysis. The oxygen remains after hydrogen escapes, creating a false biosignature. Distinguishing between biological and abiological oxygen requires detecting multiple gases simultaneously in combinations that shouldn't coexist without life maintaining them. The observations take time. Years of data collection. Statistical analysis to separate signal from noise. Repeated measurements to rule out instrumental artifacts. The scientific process moves deliberately because mistakes destroy credibility. You don't announce the detection of life on the nearest exoplanet unless you're absolutely certain. Meanwhile, the planet continues its 11-day orbit, indifferent to human curiosity. If life exists there, it evolved under conditions Earth never experienced. Organisms adapted to stellar flares as routine environmental features rather than catastrophic events. Biochemistry operating under intense UV radiation. Ecosystems confined to narrow habitable zones between frozen nightsides and scorched daysides. We wouldn't recognize that life immediately. Our biosignature searches assume Earth-like chemistry. Oxygen from photosynthesis. Methane from biological processes. But Proxima life might use completely different metabolic pathways. Might not produce the molecular signatures we're searching for. Might exist in environments we'd classify as uninhabitable using terrestrial standards. The spacecraft option remains theoretical. Breakthrough Starshot could launch probes within decades if the engineering challenges get solved. 21 years to reach Proxima Centauri at 20% light speed. Another 4 years for data to return. A mission spanning a generation but achievable within a human lifetime. Yet even that requires revolutionary technology. Laser arrays powerful enough to accelerate gram-scale spacecraft to relativistic velocities. Materials that survive interstellar particle impacts. Communication systems that transmit across light years using power measured in milliwatts. Navigation precise enough to thread a target the size of Earth from 4 trillion kilometers away. And for what? A flyby lasting minutes. No deceleration. No orbit. No landing. Just a brief window to gather data before the probe continues into interstellar space forever. Better than nothing. Better than pure speculation. But still frustratingly incomplete. The more sophisticated missions that could orbit Proxima Centauri B, study it properly, search for life comprehensively, require propulsion systems that don't exist. Fusion drives. Antimatter rockets. Technologies that remain theoretical decades after their initial proposal. The engineering challenges compound. The timeline stretch to centuries. The resources required exceed anything humanity has collectively attempted. So we're left waiting. Watching from afar with increasingly sophisticated instruments. Building models that diverge wildly depending on assumptions. Hoping the next generation of telescopes reveals something definitive. Knowing that even definitive observations leave room for interpretation. Proxima Centauri B represents both promise and limitation. Promise that habitable worlds might exist at stellar distances we could theoretically reach. Limitation that even the closest exoplanet remains functionally inaccessible with current technology. It's the planet that should answer our questions about habitability around red dwarfs, but instead raises more questions than it resolves. The dark secret turns out to be uncertainty itself. We found a world in the habitable zone of the nearest star and discovered we can't determine whether it's actually habitable. Can't confirm whether it has water. Can't verify whether its atmosphere survived stellar bombardment. Can't detect whether life arose there despite the hostile conditions. And perhaps that's appropriate. The universe doesn't owe us easy answers. Doesn't arrange itself for human convenience. Proxima Centauri B exists in the state it exists regardless of whether we understand it. Our ignorance reflects the limitations of our perspective, not any deficiency in the planet itself. The coming decades will narrow the uncertainty. Better instruments. More detailed models. Eventually direct observation through spacecraft if we commit the resources. But even then, even with data from probes that actually visit the system, ambiguities will remain. Life might hide in subsurface oceans we can't sample. Might operate through biochemistry we don't recognize. Might have existed in the past and left traces we can't interpret. The search for life beyond Earth always involved confronting these ambiguities. Proxima Centauri b makes them immediate and tangible because the world sits close enough to feel within reach. It's the exoplanet that should be easiest to characterize and instead proves most frustrating precisely because of its proximity. We know it's there. We know roughly what it is. We just can't determine the details that matter most. So the planet remains what it's always been. A world orbiting a red dwarf star 4.2 light-years away. Potentially habitable. Possibly hostile. Definitely alien. The closest exoplanet to Earth and simultaneously one of the most mysterious. Not because we lack interest or capability, but because the universe maintains its secrets even when they're practically in our cosmic backyard. That's the real lesson. Distance isn't measured only in light-years. It's measured in technological capability, observational precision, and the fundamental difficulty of understanding worlds we can't visit. Proxima Centauri b taught us that proximity doesn't equal accessibility. That nearby doesn't mean knowable. That the closest potentially habitable world beyond our solar system remains profoundly alien despite being our nearest neighbor. The dark secret wasn't about the planet. It was about us. About the limits of what we can know from here. About how much remains unknown even when we're looking at the closest possible target. About how the universe resists easy categorization no matter how sophisticated our instruments become. Proxima Centauri b will reveal its secrets eventually. Through better telescopes or visiting spacecraft or some technology we haven't invented yet. But it will reveal them on its own timeline, not ours. And when those secrets finally emerge, they'll probably raise more questions than they answer. Because that's how exploration works. Each answer opens new uncertainties. Each discovery reveals deeper mysteries. The planet spins through its 11-day orbit, lit by the dim red glow of its ancient star, maintaining whatever secrets it holds. Waiting for us to develop the capability to truly see it. Or perhaps indifferent to whether we ever do. Either way, it's there. The closest alien world. Still hiding its dark secret. Still waiting. "96% of all marine life vanished in less than 100,000 years. Earth became a graveyard. This wasn't the asteroid that killed the dinosaurs. This happened 200 million years earlier, and it was worse. Much worse. Welcome to the Permian-Triassic extinction event, the moment life on Earth nearly ended forever. Around 252 million years ago, something catastrophic unfolded. The planet didn't just experience a bad day or a rough century. It endured geological violence on a scale that makes every other extinction look modest by comparison. When paleontologists first began piecing together what happened at the boundary between the Permian and Triassic periods, they uncovered something deeply unsettling. The fossil record showed a world teeming with complexity and diversity, then suddenly, almost nothing. Scientists call it the Great Dying, and that name barely captures the horror. Imagine walking through a forest where every tree stands dead and silent. Picture oceans where fish float lifeless at the surface as far as the eye can see. Envision continents where the very soil turns toxic and rivers run thick with decay. That was Earth during this extinction. Life didn't just take a hit. It got obliterated from nearly every ecosystem simultaneously. The numbers tell a story that's hard to grasp emotionally. 81% of marine species disappeared. 70% of terrestrial vertebrates went extinct. Even insects, those notoriously resilient survivors, lost entire orders. Trilobites, ancient armored creatures that had crawled across ocean floors for over 250 million years, vanished completely. Coral reefs, which had built intricate underwater cities for eons, collapsed so thoroughly that reef building stopped for 14 million years. Forests died en masse. The planet's green lungs simply gave out. What makes this extinction truly terrifying isn't just the scale. It's the speed. Early estimates suggested the dying unfolded over millions of years, giving species time to adapt or migrate. As dating methods improved, that timeline collapsed. Recent research indicates the main pulse of extinction occurred in perhaps 60,000 years. Some scientists argue it happened even faster, in as little as 8,000 years. On geological timescales, that's instantaneous. Evolution, which needs time to work its magic, couldn't keep pace. But here's what really happened before everything fell apart. The Permian period was a time of strange beauty. All of Earth's continents had merged into a single massive landmass called Pangaea. This supercontinent stretched from pole to pole, creating climates and ecosystems unlike anything we see today. The interior regions, thousands of kilometers from any ocean, became vast deserts where temperatures swung between blistering heat and bone-chilling cold. Coastal areas supported diverse life, but the heart of Pangaea was brutal. Life had adapted remarkably well to these conditions. Synapsids, the ancestors of mammals, dominated the land. Creatures like Dimetrodon, with its distinctive sail-like back, prowled as apex predators. Massive herbivores such as mosechops grazed in herds. In the oceans, biodiversity exploded. Brachiopods, ancient shellfish unrelated to modern clams, covered the seafloor in dense colonies. Ammonoids, spiral-shelled relatives of squid, hunted through the water column. Sea scorpions, some reaching over 2 meters in length, ruled as marine predators. The planet hummed with activity. Forests of seed ferns and conifers spread across habitable zones. Insects had diversified into countless forms. Complex food webs connected every ecosystem. Earth wasn't paradise, but it was stable, functioning, alive. Species had found their niches and settled into patterns that could have continued indefinitely. Then Siberia began to tear itself apart. Deep beneath what is now central Russia, something unprecedented started happening. Magma from the mantle began forcing its way toward the surface on a scale the planet had rarely witnessed. This wasn't a single volcano preparing to erupt. This was the formation of what geologists call a large igneous province, specifically the Siberian Traps. The name sounds almost quaint until you understand what it represents. The Siberian Traps eruptions continued for roughly 2 million years, spanning the Permian-Triassic boundary itself. During that time, volcanic activity covered an area larger than modern Europe with layer upon layer of basaltic lava. In some regions, the lava piled up over 3 kilometers thick. The volume of material ejected makes Yellowstone look insignificant. One researcher described it perfectly: it's literally a singular event in Earth's history. It's a monster. It makes Yellowstone look like the head of a pin. But the lava itself wasn't the main killer. As magma rose through Earth's crust, it encountered vast deposits of coal, salt, and limestone. These sedimentary layers had accumulated over hundreds of millions of years, locking away enormous quantities of carbon and other elements. When superheated magma cooked through these deposits, it triggered chemical reactions that released catastrophic amounts of gases into the atmosphere. Carbon dioxide poured out in volumes that defy easy comprehension. Scientists estimate the eruptions released 100,000 billion metric tons of CO2. That number is so large it becomes abstract. To put it in perspective, modern human civilization releases about 10 billion metric tons of carbon dioxide annually. The Siberian traps, over their active period, released the equivalent of 10,000 years of current human emissions every single year. The atmospheric concentration of CO2 didn't just rise. It exploded to 13 times pre-extinction levels. The greenhouse effect kicked in with unprecedented force. Global temperatures began climbing rapidly, rising by 6 to 10 degrees Celsius within a geological eye blink. Polar ice disappeared. Tundra ecosystems vanished as temperate conditions spread to the highest latitudes. The tropics, already warm, became furnaces where few organisms could function. Along with carbon dioxide came sulfur dioxide. When released in massive quantities, SO2 reacts with water vapor to form sulfuric acid. Acid rain began falling across the planet. Soils turned toxic. Lakes and rivers acidified. Plants struggled to photosynthesize as their leaves became damaged. The very chemistry of rain, normally a source of life, turned destructive. Ocean chemistry shifted in equally devastating ways. As atmospheric CO2 levels soared, the oceans absorbed enormous quantities of it. When CO2 dissolves in seawater, it forms carbonic acid, lowering the pH and making the water more acidic. Organisms that built calcium carbonate shells and skeletons, including most reef-building corals, brachiopods, and many plankton species, found themselves in an impossible situation. The chemical reactions needed to construct their protective structures simply stopped working efficiently. Warming oceans created another lethal problem. Water holds less dissolved oxygen at higher temperatures. As the seas warmed, oxygen levels dropped. Simultaneously, the warming disrupted ocean circulation patterns. Normally, cold water sinks at the poles and travels along the ocean floor toward the equator, carrying oxygen to deep waters. As polar temperatures rose, this circulation weakened. Deep ocean zones became oxygen-starved, creating what scientists call anoxic conditions. In some regions, conditions deteriorated even further into euxenia, where waters become not just oxygen-poor but actively toxic with hydrogen sulfide. This nasty compound, which smells like rotten eggs, is produced by certain bacteria thriving in oxygen-free environments. Pulses of hydrogen sulfide-rich water may have risen to the surface, poisoning marine life and even releasing toxic gas into the atmosphere. Recent research has added another layer to this catastrophe. Scientists studying oxygen isotopes in fossilized conodont teeth, tiny extinct eel-like creatures, discovered something unexpected about temperature patterns. Normally, Earth maintains strong temperature gradients between the equator and poles. During the Permian-Triassic extinction, these gradients collapsed. Temperatures became remarkably uniform across latitudes. The culprit appears to be mega El Niño events. Today's El Niño brings temporary warming to the Pacific and disrupts weather globally for a year or two. During the extinction, similar but far more intense events persisted for decades or even centuries. These mega El Niños created positive feedback loops. Warming intensified, which triggered more warming, which caused more disruption. Species simply couldn't adapt to climate patterns that refused to stabilize. On land, vegetation began dying on a massive scale. The fossil record reveals something called a fungal spike, elevated levels of fungal remains in rock layers corresponding to the extinction boundary. When scientists find this pattern, it indicates forests dying faster than they can decompose normally. Fungi thrive on dead organic matter, and suddenly they had more food than they could process. Nearly all the world's trees died. Dense gymnosperm woodlands that had covered high-latitude regions disappeared. The Glossopteris flora, seed ferns that dominated southern continents, collapsed around 370,000 years before the actual boundary. Their demise shows up indirectly in geological records through an abrupt change in river patterns. When rooted plants die off, rivers transform from meandering systems with stable banks into braided systems that constantly shift and erode. As forests vanished, one of Earth's primary carbon sinks disappeared with them. Plants pull CO2 from the atmosphere through photosynthesis. When the plant biosphere collapsed, this crucial mechanism for regulating atmospheric carbon stopped functioning. The planet lost its ability to naturally counteract the ongoing volcanic emissions. Carbon dioxide accumulated even faster, accelerating warming in a vicious cycle. The extinction didn't happen uniformly. Geographic patterns reveal crucial information about the kill mechanisms. High-latitude species, particularly those in polar regions, suffered the worst losses. Near-complete extinction struck these areas. Tropical species fared somewhat better, though still experiencing catastrophic losses. This pattern makes sense when you consider the combined effects of temperature and oxygen. Marine organisms have specific thermal tolerances and oxygen requirements. As water warmed, their metabolism sped up, increasing their oxygen demands precisely when available oxygen was dropping. For species already living near their thermal limits, there was nowhere to go. Polar species couldn't migrate toward cooler waters because those waters no longer existed. The extinction unfolded in pulses. Evidence suggests 1 to 3 distinct phases when death rates spiked. Some species made it through the first wave only to succumb during subsequent crises. This pattern hints at multiple triggers or cascading effects where initial impacts created conditions that generated additional disasters. What happened next would determine whether life on Earth could recover, or whether the planet would remain a desolate wasteland for millions of years. The mechanisms of death were clear enough, but survival would prove far more mysterious. In the oceans, survivors faced a world transformed beyond recognition. The water itself had become hostile. Hydrogen sulfide, that rotten egg smell you associate with swamps and sewage, now permeated vast stretches of ocean. Under normal conditions, oxygen-breathing bacteria dominate marine ecosystems. When oxygen disappears, different microbes take over. Anaerobic bacteria produce hydrogen sulfide as a metabolic byproduct. During the Permian-Triassic extinction, hydrogen sulfide levels rose so high that the gas didn't just stay dissolved in deep water. It bubbled up to the surface and escaped into the atmosphere. Imagine swimming in an ocean that smells like 1,000 rotten eggs. That's not even the worst part. Hydrogen sulfide is toxic to most complex life. It interferes with cellular respiration, essentially poisoning organisms from the inside. Marine creatures that managed to survive warming and oxygen depletion now had to contend with water that was actively poisonous. The geological record preserves evidence of these euxinic conditions, oxygen-free waters rich in hydrogen sulfide, in rock formations worldwide. Black shales containing high concentrations of pyrite, fool's gold, mark these deadly zones. But certain organisms found ways to persist. The survivors weren't random. Research examining 4 critical factors revealed patterns in who lived and who died. Position in the water column mattered enormously. Bottom-dwelling organisms, those living directly in sediment, suffered catastrophic losses. Creatures called bioturbators, animals that burrow through seafloor sediments mixing nutrients and oxygen, nearly vanished. The loss of this mixed sedimentary layer appears in the geological record as a stark boundary. Below it, sediments show signs of active life. Above it, nothing but undisturbed layers. Shell mineralization determined survival odds. Organisms with heavily calcified shells, thick protective armor built from calcium carbonate, died in disproportionate numbers. The problem was ocean acidification. As atmospheric CO2 dissolved into seawater, it formed carbonic acid. This lowered ocean pH, making it harder for creatures to extract calcium carbonate from water and build shells. Organisms that relied on thick shells for protection found themselves unable to maintain their defenses. Their shells literally began dissolving. Creatures with lighter calcification fared better. Brachiopods, ancient shellfish that superficially resemble clams, experienced massive losses. But the species that survived generally had thinner shells and more active control over their internal circulation. They possessed elaborate gas exchange mechanisms that let them extract oxygen more efficiently from oxygen-poor water. Simple breathing apparatuses became death sentences. Species diversity within a genus also predicted survival. Groups with many closely related species distributed across different environments had better odds. If one species went extinct, related forms might survive elsewhere and later repopulate empty habitats. Groups with just one or two species in limited ranges disappeared completely when their specific environment collapsed. Sensitivity to acidification was the final critical factor. Some organisms simply couldn't tolerate pH changes. Others showed remarkable resilience. The survivors weren't necessarily stronger or more complex. They were flexible. Generalist species that could eat various foods, tolerate different temperatures, and adapt their behavior had advantages specialists lacked. On land, the picture was equally grim but followed different rules. 8 entire orders of insects vanished. Think about that. Not just species or genera, but whole orders, taxonomic groups representing millions of years of evolutionary divergence. Modern insects are incredibly diverse, with over 1 million described species. The Permian-Triassic extinction wiped out fundamental branches of the insect family tree that had existed since the Carboniferous. 2/3 of tetrapod families disappeared. These were the dominant land animals, the synapsids, and early reptiles that had ruled terrestrial ecosystems for tens of millions of years. Massive herbivores that browsed on vegetation, apex predators with saber-like teeth, all gone. The speed of this collapse is what makes it so striking. These weren't species teetering on the edge of extinction before the catastrophe hit. Many were abundant and widespread right up until the boundary. Trilobites, those iconic armored arthropods that had crawled across seafloors for over 250 million years, finally met their end. They'd survived 4 previous mass extinctions. They'd adapted to countless environmental changes. They'd diversified into thousands of species occupying every marine niche imaginable. None of it mattered. The Permian-Triassic extinction erased them completely. Reef building stopped. For 14 million years afterward, no significant reef structures formed in shallow seas. Reefs are biodiversity hotspots, complex three-dimensional habitats that support enormous numbers of species. When reefs disappeared, they took their dependent ecosystems with them. The absence of reefs in early Triassic oceans reveals just how thoroughly marine ecosystems had collapsed. The basic ecological architecture that supports diverse life was gone. Tabulate and rugose corals, the primary reef builders of the Paleozoic, went extinct. Modern coral reefs are built by scleractinian corals, a completely different group that evolved later. The reefs we know today aren't descendants of Permian reefs. They're new constructions built by new organisms that emerged millions of years after the catastrophe. So what actually survived? The list is surprisingly short and decidedly unglamorous. Small terrestrial vertebrates made it through, particularly those that could burrow underground or shelter in crevices. Body size had become a liability. Large animals need more food, more oxygen, more stable conditions. When all three became scarce simultaneously, being small and undemanding became the ultimate survival strategy. Certain fish lineages persisted, mostly small-bodied forms that could tolerate low oxygen. Sharks, surprisingly, came through relatively intact. Their cartilaginous skeletons required less calcium than bony fish, giving them an edge as ocean chemistry shifted. They could also regulate their internal salt balance more effectively, helping them cope with changing ocean chemistry. Amphibians showed remarkable resilience. Their ability to breathe through their skin supplemented lung capacity, allowing them to extract oxygen from both air and water. Many could also enter dormant states during harsh conditions, essentially waiting out the worst phases. Some amphibian lineages that made it through the extinction would later give rise to the ancestors of modern frogs and salamanders. Early reptiles, particularly small insectivorous forms, survived in decent numbers. Their scaly skin reduced water loss, crucial as climates became more arid. Their eggs with protective shells didn't require standing water, allowing them to reproduce away from increasingly hostile aquatic environments. These survivors formed the foundation for the later radiation of reptiles during the Triassic, eventually leading to dinosaurs. But the real story of survival belongs to organisms you wouldn't expect. Lystrosaurus, a dicynodont about the size of a pig, became the most abundant land vertebrate in the early Triassic. Before the extinction, Lystrosaurus was just one of many synapsid species. Afterward, it accounted for roughly 90% of terrestrial vertebrate fossils. Not because it was superior, but because almost everything else had died. This phenomenon has a name: disaster taxa. These are species that explode in abundance immediately after mass extinctions, not through competitive superiority but through sheer lack of competition. Lystrosaurus didn't outcompete other species. It simply inherited an empty planet. The fossil record from the early Triassic shows something bizarre. Before the extinction, communities varied dramatically from place to place. Different continents hosted different species adapted to local conditions. After the extinction, the same handful of species appeared everywhere. Fossils from South Africa look nearly identical to those from Antarctica, Russia, and China. The entire planet became monotonous. Scientists use a striking analogy. If someone asked you today where to find kangaroos, you'd say Australia. Now imagine a catastrophe occurred and suddenly kangaroos showed up in North America, Europe, Asia, everywhere. That's essentially what happened in the early Triassic. Geographic barriers that normally keep species separated became meaningless because so few species remained. Marine environments showed the same pattern. A few disaster taxa, mostly small bivalves and simple brachiopods, dominated oceans worldwide. Species that previously existed only in specific regions suddenly had global distributions. Not through dispersal or migration, but because everything else had vanished, leaving them alone on an empty stage. The survivors weren't thriving. They were persisting in a world that remained fundamentally unstable for millions of years after the initial extinction pulses. Atmospheric carbon dioxide levels continued climbing, driven by ongoing volcanic activity in Siberia. The Siberian traps weren't a single explosive event like later asteroid impacts. They represented sustained eruption over roughly 2 million years, with peak activity coinciding precisely with the extinction boundary. Magma punched through coal deposits and organic-rich sediments, essentially cooking them and releasing massive quantities of greenhouse gases. Not just carbon dioxide, but methane, a far more potent warming agent. Temperature records preserved in ancient tooth enamel tell a brutal story. Conodonts, tiny eel-like creatures with mineralized teeth, left behind a thermal archive. Their oxygen isotope ratios reveal that global temperatures spiked by 6 to 10 degrees Celsius. That doesn't sound catastrophic until you realize this warming happened over perhaps 100,000 years. For evolution, that's instantaneous. Species adapted to stable climates over millions of years suddenly faced conditions that changed faster than genetics could respond. But raw temperature increase wasn't the primary killer. Recent research identified something far more insidious. The warming triggered mega El Niño events, climate oscillations that make modern El Niños look gentle. These weren't temporary disruptions lasting months. They persisted for years, possibly decades at a time. Temperature gradients between equator and poles collapsed. Tropical heat spread toward high latitudes. Species that had evolved for cooler environments found themselves trapped in zones that became lethally hot. Here's where the cascade accelerated. Plants began dying on a massive scale. Not just individual trees, but entire forest ecosystems. The fossil record shows something called a fungal spike, elevated levels of fungal spores appearing globally in sediments right at the extinction boundary. Fungi decompose dead organic matter. Their explosion in abundance means one thing. The world's forests were dying faster than normal decay processes could handle. When forests collapsed, the planet lost its primary carbon sink. Living plants pull CO2 from the atmosphere through photosynthesis, storing it in wood and soil. Dead plants stop removing carbon. Worse, their decomposition releases stored carbon back into the atmosphere. The Siberian traps kept pumping out greenhouse gases while Earth's biological systems for removing those gases shut down. Positive feedback loop. Warming killed plants, dead plants meant more atmospheric carbon meant more warming. On land, river systems changed character completely. Meandering rivers, which require vegetation to stabilize their banks, transformed into braided channels that shifted and wandered. Without plant roots holding soil in place, erosion accelerated. Sediments clogged waterways. The landscape itself became unstable. Marine environments faced a different horror. Warmer water holds less dissolved oxygen. Basic chemistry. As ocean temperatures climbed, oxygen concentrations dropped. Simultaneously, marine animals' metabolism sped up in the heat, requiring more oxygen precisely when less became available. Researchers modeled this lethal combination using modern species' oxygen requirements. The results matched fossil distributions with eerie precision. Species living in cold polar waters, where oxygen demands were already high, went extinct almost completely. Tropical species fared slightly better, already adapted to warmer, lower oxygen conditions. But even tropical oceans reached thresholds where metabolism outpaced oxygen supply. Animals essentially suffocated in warming water. The ocean's circulation system began breaking down. Normally, cold polar water sinks and flows toward the equator along the seafloor, while warm tropical water moves poleward at the surface. This thermohaline circulation acts like a planetary conveyor belt, distributing heat and nutrients. As temperature gradients flattened, circulation weakened. Deep ocean zones became stagnant. Stagnant water turns anoxic. Without circulation bringing fresh oxygen to depth, deep ocean zones essentially died. Anaerobic bacteria took over, producing hydrogen sulfide, the same compound that gives rotten eggs their smell. Except this wasn't a small pocket of decay. Vast stretches of deep ocean became toxic. Some researchers suggest hydrogen sulfide periodically bubbled to the surface, poisoning shallow waters and even escaping into the atmosphere. Ocean acidification compounded every other problem. When CO2 dissolves in seawater, it forms carbonic acid. The more atmospheric CO2, the more acidic oceans become. Calcium carbonate, the material organisms use to build shells and skeletons, dissolves in acidic water. Species that had protected themselves with armor for hundreds of millions of years suddenly found their defenses literally dissolving. Trilobites, ancient arthropods that had survived previous extinction events, vanished entirely. They'd existed for over 270 million years, weathering countless environmental changes. The Permian-Triassic event erased them permanently. Coral reefs, those complex ecosystems supporting thousands of species, collapsed globally. It would take 14 million years before reef-building organisms recovered enough to construct similar structures. On land, insects suffered their only known mass extinction. 8 entire orders disappeared. Insects typically survive environmental catastrophes because of their small size, rapid reproduction, and ability to exploit diverse food sources. Not this time. Even organisms at the base of food webs couldn't find refuge. What makes the Permian-Triassic extinction uniquely devastating isn't just the raw percentage of species lost. It's the complete disruption of ecological functioning. Previous mass extinctions removed many species but left ecosystem structures largely intact. This event shattered those structures. Food webs didn't just simplify. They collapsed to nearly nothing and had to rebuild from scratch. The aftermath persisted for an almost incomprehensible duration. 5 to 6 million years of continued environmental instability. Survivors that managed to establish populations faced repeated setbacks as climate continued oscillating wildly. Carbon cycle perturbations, oxygen fluctuations, temperature spikes. Communities would begin recovering, then get knocked back by another pulse of environmental chaos. This explains why disaster taxa dominated for so long. Normal competitive dynamics couldn't operate. Ecosystems never achieved enough stability for complex food webs to re-establish. Lystrosaurus wasn't necessarily better adapted than other organisms. It just happened to survive the initial extinction and could tolerate the ongoing instability. In a stable environment, more specialized species would have outcompeted. In perpetual crisis, being generalized and tolerant meant everything. Terrestrial ecosystems took 30 million years to fully recover. Not recover to pre-extinction diversity, that never happened. Many ecological roles that existed before the Permian-Triassic boundary remained empty permanently. But 30 million years before ecosystems achieved new stable configurations, before food webs became complex again, before the planet hosted comparable biodiversity. Marine ecosystems showed similar timescales. Shallow marine communities recovered somewhat faster, within 5 to 10 million years. But deep ocean ecosystems and complex trophic structures took up to 50 million years. The extinction didn't just reset Earth's biological clock. It fundamentally altered what was possible. Why did this extinction exceed all others in severity? The Siberian traps erupted at a uniquely vulnerable moment in Earth's history. Pangaea, the supercontinent, had just formed. Land masses concentrated in one area reduced total coastline length, eliminating shallow marine habitats that typically serve as refuges during environmental stress. Continental interiors, far from ocean's moderating influence, experienced extreme temperature swings. Species had fewer options for geographic escape. The volcanism itself reached unprecedented scales. Individual eruptions weren't necessarily larger than other volcanic events, but the duration and total volume exceeded anything else in the Phanerozoic record. 2 million years of sustained eruption. No previous volcanic episode approached that timescale. The planet's environmental systems couldn't buffer or absorb the continuous input of greenhouse gases. Most critically, the extinction occurred faster than recovery mechanisms could operate. Normal extinction events, even severe ones, happen slowly enough that evolution fills empty niches relatively quickly. The Permian-Triassic event compressed catastrophic environmental change into a window too narrow for adaptive responses. Species either possessed pre-existing traits allowing survival or they died. No time for evolution to generate new solutions. Understanding how thoroughly the planet broke during this event makes the survival of any lineage remarkable. Every living organism today, from bacteria to blue whales, descends from something that made it through those 5 million years of hell. Our own distant ancestors, small cynodont synapsids barely distinguishable from other survivors, persisted when 90% of life could not. The Permian-Triassic extinction wasn't merely Earth's deadliest event. It represented the closest life has come to complete extinction since complex organisms evolved. A few more degrees of warming, a bit more ocean acidification, slightly longer duration of environmental chaos, and perhaps nothing would have survived. Yet that scenario nearly happened. And the mechanisms that pushed Earth toward complete biosphere collapse reveal patterns that operate across all mass extinctions. The kill mechanisms during the Permian-Triassic weren't random. They formed an interconnected cascade where each environmental change amplified the next. Understanding this cascade explains why the extinction exceeded all others in lethality. Start with the oceans. Marine ecosystems experienced a transition from oxygenated to anoxic-euxinic conditions across most of the globe. Anoxic means depleted of oxygen. Euxinic means not only oxygen depleted but saturated with hydrogen sulfide. Seawater became actively toxic. This wasn't uniform. Different ocean basins showed regional variability in timing and intensity, but the overall pattern held. Decreased ocean ventilation coincided with rapidly rising temperatures. The combination proved lethal. Here's why. As water temperature increases, its capacity to hold dissolved oxygen decreases. Basic chemistry. Warmer water physically cannot contain as much oxygen as cooler water. At the same time, warmer temperatures increase metabolic rates in marine animals. Their bodies require more oxygen precisely when less is available. Research combining models of ocean conditions with animal metabolism and paleoceanographic records demonstrates this thermal oxygen squeeze killed most marine life. Species couldn't breathe. Their physiology demanded oxygen levels the environment could no longer provide. The geographic pattern of extinction confirms this mechanism. High-latitude species, especially those with high oxygen demands, were nearly completely wiped out. Polar regions, traditionally cooler and oxygen-rich, warmed dramatically. Animals evolved for cold, oxygen-rich water suddenly faced warm, oxygen-poor conditions. No evolutionary pathway existed from their current physiology to what survival required. Tropical species fared slightly better. Not because tropical waters remained cool or oxygen-rich, they didn't. But tropical organisms already possessed adaptations for warmer temperatures and lower oxygen. Their baseline tolerance was higher. Many still died, but survival rates exceeded those at higher latitudes. The fossil record shows species distribution before the extinction. Then, at the boundary, diversity collapses. The geographic signature matches what models predict for warming-driven oxygen loss. Theory and evidence align perfectly. But oxygen depletion alone doesn't explain the hydrogen sulfide. That requires understanding what happens when oceans stop mixing properly. Normal ocean circulation brings oxygen-rich surface water down into the depths. Upwelling brings nutrient-rich deep water to the surface. This constant mixing maintains oxygen levels throughout the water column and prevents toxic compounds from accumulating. During the Permian-Triassic, warming disrupted this circulation. Temperature differences between surface and deep water decreased. Without strong temperature gradients, the physical engine driving ocean mixing weakened. Stratification increased. Surface water stopped sinking. Deep water stopped rising. In stagnant deep waters, oxygen ran out quickly as bacteria consumed it, decomposing organic matter. Once oxygen disappeared, anaerobic bacteria took over. These organisms produce hydrogen sulfide as a metabolic byproduct. In oxygenated water, other bacteria consume hydrogen sulfide, keeping it in check. Without oxygen, nothing stops hydrogen sulfide accumulation. Concentrations built up over thousands of years. Eventually, hydrogen sulfide saturated deep waters. Then it began rising toward the surface. Some researchers suggest hydrogen sulfide breached the ocean surface, releasing toxic gas into the atmosphere. Others think it remained dissolved but created a toxic layer throughout much of the ocean's depth. Either scenario meant death for most marine organisms. Hydrogen sulfide is directly toxic. It interferes with cellular respiration. Animals swimming through euxinic waters were essentially swimming through poison. The loss of marine species reached 96%. Nearly everything died. The extinction rate wasn't gradual. Bioturbators, organisms that churn through seafloor sediments, were extremely severely affected. The loss of the sedimentary mixed layer in many marine facies shows that animals stopped disturbing the seafloor. Nothing was left to dig, burrow, or mix sediments. The ocean floor became a dead zone. Reef building stopped for 14 million years. Shallow seas, typically refuges during environmental stress, offered no protection. Marine animals in reefs and shallow waters were especially hard hit. The structures that had provided habitat for millions of years simply ceased to exist. Specific groups that had dominated oceans for hundreds of millions of years vanished entirely. Trilobites, survivors of multiple previous mass extinctions, finally went extinct. They'd existed for over 250 million years. The Permian-Triassic boundary ended them. Tabulate and rugose corals disappeared. Blastoid echinoderms, graptolites, eurypterids, acanthodians, placoderms, all gone. The extinction primarily affected organisms with calcium carbonate skeletons, especially those reliant on stable CO2 levels to produce their skeletons. Ocean acidification from dissolved atmospheric CO2 made skeleton construction impossible. Carbonate chemistry shifted beyond what these organisms could tolerate. Research identified 4 factors most essential to survival. Where in the water organisms lived. The mineralization of their shells. Species diversity within their genus. Sensitivity to acidification. Surviving groups generally had active control of circulation, elaborate gas exchange mechanisms, and light calcification. Heavily calcified organisms with simpler breathing apparatuses suffered the greatest loss of species diversity. This explains why certain groups survived while others didn't. Brachiopods, corals, bryozoans, foraminifers, ostracods, all heavily calcified benthic organisms, were devastated. Meanwhile, some less calcified, more physiologically flexible groups persisted at low levels. Planktonic populations underwent fundamental change. Eukaryotic algae, which had formed the base of marine food webs, were replaced by nitrogen-fixing bacteria, green sulfur bacteria, sulfate-reducing bacteria, and prasinophytes. The entire foundation of marine ecosystems shifted from complex eukaryotic organisms to simpler prokaryotic forms. On land, the devastation followed different pathways but achieved similar totality. Recent research published in Nature Communications identified the primary cause of prolonged post-extinction warming: the collapse of tropical forests. When global forests died, carbon sequestration essentially stopped. Photosynthesis removes CO2 from the atmosphere. Plants are Earth's natural mechanism for keeping CO2 in check. When nearly all trees died, that mechanism broke. The fungal spike in Permo-Triassic rocks worldwide confirms this. Elevated levels of fungal remains with few tree pollen grains. Fungi decompose dead organic matter. A planet-wide fungal spike means a planet-wide mass of dead vegetation being broken down. Nearly all the world's trees died en masse. The Glossopteris flora that characterized high-latitude Gondwana collapsed in Australia around 370,000 years before the Permian-Triassic boundary. In western Gondwana, the timing is less constrained but still likely occurred hundreds of thousands of years before the boundary. This collapse is indirectly marked by abrupt changes in river morphology from meandering to braided river systems. Rivers change character when vegetation dies. Without root systems stabilizing banks, rivers spread out, become shallow and multi-channeled. The widespread demise of rooted plants restructured hydrology across continents. Pollen studies from East Greenland showed dense gymnosperm woodlands before the event. Then, at the boundary, those woodlands disappeared. Smaller herbaceous plants including Lycopodiophyta increased in diversity. The world shifted from forests to scrubland. From complex plant communities to pioneer species. This vegetation collapse created a feedback loop. Volcanic eruptions released CO2. Plants normally absorb that CO2. With plants dead or dying, atmospheric CO2 continued climbing unchecked. More CO2 meant more warming. More warming meant more plant death. The cycle amplified itself. This explains why super-greenhouse conditions persisted for 5 million years after the initial extinction. The planet's natural CO2 regulation system had broken. Volcanic inputs continued. Nothing removed the gas from the atmosphere at rates approaching volcanic output. Temperature climbed beyond anything Earth had experienced before or since. Scientists have used plant fossils to model a dramatic 10 degrees Celsius rise in global temperatures. On land, surface temperatures increased by 6 to 10 degrees Celsius. Too rapid for life to evolve and adapt. Evolution operates on timescales of hundreds of thousands to millions of years. The Permian-Triassic warming occurred in tens of thousands of years. No time for adaptive responses. Recent research on mega El Niño events adds another layer. The study, published in Science, shows that the collapse of temperature gradients in low and mid-latitudes was driven by prolonged, intense El Niño events far exceeding anything witnessed today. Researchers stated that essentially, it got too hot everywhere. Species were simply not equipped to adapt or evolve quickly enough. These mega El Niños created positive climate feedbacks. Incredibly warm conditions started in the tropics, then spread globally. Vegetation died back. With plants dying, Earth's CO2 removal mechanism failed, allowing continued volcanic CO2 buildup. This also explains why extinction on land occurred tens of thousands of years before extinction in the oceans. Terrestrial environments respond faster to atmospheric changes. Marine systems, with greater thermal inertia, lagged behind. But eventually, ocean warming caught up and exceeded what marine life could tolerate. Less than 1/3 of large animal species on land survived. The volcanic eruptions themselves caused immediate problems. Sulfur dioxide and carbon dioxide poisoned the air. Ash and soot blocked sunlight, preventing plant growth. Food chains collapsed from the bottom up. With little greenery to eat, herbivores died. Predators followed. The speed of terrestrial collapse reveals something crucial about ecosystem fragility. Complex food webs depend on continuous energy flow from primary producers. When photosynthesis stops, everything above that level has days to weeks before starvation. Large animals, with high energy demands, died first and fastest. Yet from this near-total devastation, life found pathways to persist. Understanding what survived and how sets up the recovery story, a process that would test the limits of biological resilience for millions of years to come. In the aftermath, what survived wasn't selected by strength or size. The winners were organisms whose traits happened to match a world nobody could have predicted. Lystrosaurus. A dicynodont therapsid about the size of a pig, with a blunt snout, barrel chest, and sprawling limbs. Before the extinction, it was one species among hundreds. After, it dominated. Fossil evidence shows that Lystrosaurus accounted for approximately 90% of terrestrial vertebrates in the earliest Triassic. 90%. Imagine walking across early Triassic landscapes and seeing nothing but variations of one creature, from horizon to horizon, across every continent. This wasn't evolutionary superiority. This was luck combined with specific physiological advantages. Lystrosaurus could dig burrows, escaping surface temperature extremes. It had a generalist diet, feeding on whatever sparse vegetation remained. Its metabolism was efficient enough to survive on minimal food. Most importantly, it reproduced quickly. Where larger predators needed years to reach maturity, Lystrosaurus populations could rebound within seasons. Scientists call these survivors disaster taxa. Species that explode in abundance immediately after catastrophic events, filling ecological space left vacant by extinctions. They're not the most advanced organisms. They're the most opportunistic, the most flexible, the most boringly successful in conditions where nothing else can compete because nothing else exists. The pattern repeated in the oceans. Marine post-extinction faunas were dominated by a handful of forms. Bivalves like Chlorea, Unionites, and Eumorphotis spread across seafloors worldwide. Conodonts Clarkina and Hendiatus became ubiquitous. The inarticulate brachiopod Lingularia, with its simple body plan and minimal calcification needs, thrived in acidified waters that killed more complex relatives. What's striking isn't that these species survived, but where they appeared. Before the extinction, marine species showed clear geographic distributions. Certain organisms lived only in specific regions, adapted to local conditions. After the boundary, that geographic structure collapsed. Species previously found only in one ocean suddenly appeared globally. Researchers describe this as cosmopolitanism, a planetary homogenization of life. The modern analogy makes it visceral. If you asked where to find kangaroos today, the answer is Australia. Now imagine a catastrophe occurs, and afterward, kangaroos appear in massive numbers across every continent. Europe, Africa, Asia, the Americas. Everywhere you look, kangaroos. That's what early Triassic oceans resembled. Fossils show communities going from richly diverse assemblages to boringly alike groups, no matter where you sample. This homogenization reveals something profound about how ecosystems collapse and rebuild. Diversity doesn't return immediately. Complex food webs with specialized niches take millions of years to re-establish. In the immediate aftermath, life reverts to simpler patterns. Generalists dominate. Specialists vanish. Ecosystems flatten into crude approximations of what existed before. But even disaster taxa faced challenges. The extinction event itself lasted perhaps 60,000 years. The aftermath persisted for 5 million. Volcanic activity didn't stop at the boundary. The Siberian traps continued erupting. Carbon cycle disruptions continued through the entire early Triassic. Communities that survived the initial extinction and began rebuilding were hit again by recurring environmental shocks. Temperature spikes. Ocean anoxia returning impulses. Acidification events. Each wave of stress interrupted recovery. Terrestrial ecosystems endured boom and bust cycles for 8 million years before stabilizing. Populations would grow, ecosystems would begin complexifying, then another environmental shock would knock everything back to simpler states. 2 steps forward, 1 step back, repeated across geological time. The low diversity of surviving vertebrates created its own problems. With few species present, ecosystems lacked redundancy. If one disaster taxon declined, nothing filled its role. Food webs remained fragile, vulnerable to any perturbation. Contrast this with pre-extinction ecosystems where multiple species performed similar functions. Lose one, others compensate. In the early Triassic, there were no backup species. Marine ecosystems faced additional constraints. Research shows that taxonomic diversity at the community level didn't recover to pre-extinction levels during the early or middle Triassic. It reached only a low plateau after each extinction pulse and remained depressed well into the late Triassic. Full ecological recovery, where complex trophic structures and diverse guilds re-established, took roughly 50 million years. That's not a typo. 50 million years. While taxonomic diversity, the raw number of species, recovered in 5 to 10 million years, true ecosystem function took 5 times longer. Having species present doesn't mean having a functioning ecosystem. You need the right species in the right roles with the right interactions. Rebuilding that structure from near zero is astonishingly slow. Why did recovery take so long? Several factors compounded. First, the carbon cycle remained disrupted. Atmospheric CO2 stayed elevated because volcanic inputs continued while biological carbon sequestration remained weak. Without dense vegetation or diverse marine plankton communities, CO2 removal rates stayed far below normal. This perpetuated greenhouse conditions, maintaining environmental stress. Second, ocean chemistry stayed hostile. Anoxic zones expanded during warm periods. Acidification events recurred whenever volcanic pulses added more CO2. Marine organisms trying to rebuild calcium carbonate structures faced repeated setbacks. Reefs didn't begin reforming until 14 million years into the Triassic. That's 14 million years without the ocean's most productive ecosystems. Third, evolutionary innovation takes time. After mass extinctions, surviving lineages diversify to fill empty niches. But evolution doesn't work instantly. Mutations arise randomly. Selection operates over generations. Beneficial traits must accumulate. New body plans must stabilize. For complex organisms with long generation times, meaningful evolutionary change requires hundreds of thousands to millions of years. The fossil record documents this slow rebuilding. Early Triassic communities show low gill diversity. Gill refers to groups of species that exploit resources in similar ways. Before the extinction, multiple species of filter feeders, multiple species of predators, multiple species of burrowers coexisted. After, each guild had one or two representatives at most. Ecosystems functioned, barely, but lacked the complexity and resilience of pre-extinction systems. Geographic patterns of recovery varied. Some regions rebounded faster than others. Studies of localized marine ecosystems, like the Paris biota in what's now Idaho, show recovery occurring in 1.3 million years. But that's recovery of basic ecosystem function, not restoration of pre-extinction diversity or complexity. These were simple communities compared to Permian reefs. On land, the situation was even more extreme. Terrestrial vertebrate fauna took 30 million years to fully recover numerically and ecologically. Not until the late Triassic did land ecosystems display the diversity and complexity seen in the Permian. That's when dinosaurs, pterosaurs, crocodiles, archosaurs, amphibians, and mammaliforms became abundant and diverse. The world we associate with the Mesozoic emerged only after 3 decades of millions of years rebuilding from near oblivion. What determined which lineages eventually diversified? The answer involves both chance and contingency. Survivors at the boundary had won the first lottery, possessing traits that allowed persistence through catastrophe. But recovery success required different traits. Flexibility in diet and habitat. Efficient reproduction. Ability to exploit newly available niches. Lineages that survived but couldn't adapt to changing conditions during recovery stagnated or went extinct in secondary waves. The early Triassic world was simultaneously empty and full. Empty of diversity, of complex ecosystems, of specialized organisms. Full of opportunity for any lineage capable of exploiting it. Disaster taxa like Lystrosaurus thrived not because they were advanced, but because they faced no competition. Remove competition, and even modest capabilities become sufficient for dominance. This dynamic explains the peculiar nature of post-extinction evolution. After major extinctions, life doesn't gradually rebuild pre-existing structures. It experiments, tries new body plans, tests different ecological strategies. Most experiments fail. Some succeed spectacularly, establishing lineages that will dominate for tens or hundreds of millions of years. The Permian-Triassic boundary marks one such turning point. The Paleozoic world, with its characteristic fauna and ecosystems, died. What emerged during the Triassic recovery was fundamentally different. New dominant groups. New ecosystem structures. New rules for who succeeds and who fails. Yet even as life slowly rebuilt, the planet itself continued changing. Continental drift proceeded. Pangaea persisted as a supercontinent but began showing signs of future fragmentation. Climate zones shifted. Ocean circulation patterns evolved. The stage was being set for the next great radiation of life, though nobody watching the barren early Triassic landscapes could have predicted what was coming. the emptiness didn't last. It couldn't. Earth operates on momentum, chemical cycles, physical processes that continue regardless of biological catastrophe. Rivers still flowed, carrying nutrients to the seas. Volcanic activity persisted, releasing gases that weathered rocks and fed primitive organisms. Solar radiation still reached the surface, driving whatever photosynthesis survived. The planet provided the raw materials. Life had to figure out what to do with them. By the Middle Triassic, about 10 to 15 million years after the extinction, something shifted. Not a sudden transformation, but a gradual acceleration in the pace of evolutionary innovation. Survivors had stabilized. Populations had grown. And now, with ecological space still largely vacant, natural selection began favoring not just survival, but expansion. Organisms that could exploit multiple food sources, that could tolerate varying conditions, that reproduced efficiently, these lineages spread rapidly across landscapes and seascapes that offered minimal resistance. On land, the synapsid lineage that would eventually produce mammals continued evolving. Cynodonts emerged, dog-sized predators and omnivores with increasingly mammal-like features. More efficient jaws. Better hearing. Possible fur. These weren't mammals yet, but they were heading that direction, experimenting with traits that would define an entire class of animals tens of millions of years later. Alongside them, early archosaurs appeared. The archosaur group would eventually split into two major branches. One leading to crocodilians. The other leading to dinosaurs and birds. In the late Triassic, dinosaurs made their entrance. Small, bipedal, unremarkable at first. Nothing about early dinosaurs suggested they would dominate terrestrial ecosystems for 160 million years. They were simply another group of reptiles trying to survive in a world still recovering from catastrophe. But they possessed certain advantages. Upright limb posture that improved locomotion efficiency. Relatively large brains for their body size. Fast growth rates. These traits didn't guarantee success, but they provided options. And in an unpredictable world, options matter. The oceans told a parallel story. Reef ecosystems, absent for 14 million years after the extinction, began rebuilding in the Middle Triassic. Not with the same organisms, those were gone, but with new reef builders. Corals returned, but different families than dominated Permian reefs. Marine reptiles diversified into the ecological roles left vacant by extinct groups. Ichthyosaurs evolved streamlined bodies for fast swimming. Plesiosaurs developed long necks for hunting in different ways. Placodonts specialized in crushing shellfish. Each group represented an evolutionary experiment, testing whether a particular body plan and lifestyle could work in post-extinction oceans. But here's what makes this recovery period so instructive. The late Triassic world looked nothing like the Permian world. Same planet, same basic physics and chemistry, completely different biological cast. Pangaea still dominated geography, but the ecosystems populating that supercontinent bore little resemblance to what came before. This reveals something fundamental about how life responds to mass extinction. Recovery isn't restoration. It's renovation. The old blueprints are discarded. New designs are tested. Most fail. A few succeed spectacularly. The late Triassic also demonstrated that recovery from mass extinction doesn't follow a smooth upward trajectory. Around 201 million years ago, Earth experienced another major extinction event at the Triassic-Jurassic boundary. Not as severe as the end Permian, but significant enough to eliminate roughly 70 to 75% of species. The cause appears linked to volcanic activity associated with the breakup of Pangaea and the opening of the Atlantic Ocean. Once again, massive carbon dioxide release. Once again, rapid climate warming. Once again, ocean acidification. Life had barely finished recovering from one catastrophe when another struck. This second extinction disproportionately affected certain groups while barely touching others. Many large amphibians vanished. Several archosaur lineages went extinct. But dinosaurs, still relatively minor players in late Triassic ecosystems, survived. And in the aftermath, with many competitors removed, dinosaurs underwent explosive diversification. By the early Jurassic, they had become the dominant large terrestrial animals. Their success wasn't inevitable. It was contingent on surviving the Triassic-Jurassic boundary while many other groups did not. What does this tell us about mass extinctions and recovery? First, that recovery timelines depend on the severity and nature of the extinction. The end Permian, with its combination of rapid warming, ocean anoxia, acid rain, and ecosystem collapse, required 10 million years for basic recovery and 30 million for full restoration of terrestrial ecosystem complexity. The Triassic-Jurassic event, less severe in its mechanisms, allowed faster rebound. Second, that which groups dominate after extinction depends partly on pre-existing traits, but largely on chance. Dinosaurs didn't dominate because they were superior to other Triassic reptiles. They dominated because they survived when others didn't, then exploited the resulting opportunities. The pattern repeats throughout Earth's history. 5 major mass extinctions punctuate the Phanerozoic Eon, each reshaping life's trajectory. The late Ordovician extinction, caused by glaciation and sea level changes. The late Devonian extinctions, possibly linked to plant evolution altering atmospheric composition. The end Permian, Earth's closest approach to complete sterilization. The Triassic-Jurassic boundary. And finally, the end Cretaceous asteroid impact that eliminated non-avian dinosaurs. Each event cleared ecological space. Each allowed previously minor groups to become dominant. Each reset the evolutionary clock, forcing life to rebuild from whatever survived. But mass extinctions aren't just destructive. They're also creative, in a brutal sense. By eliminating dominant groups, they allow innovation. Mammals remained small and ecologically marginal for 160 million years while dinosaurs dominated. Only after the end Cretaceous extinction did mammals diversify into the full range of body sizes and ecological roles. Birds, despite evolving flight during the Jurassic, remained relatively limited in diversity until after non-avian dinosaurs vanished. Remove the dominant players, and previously suppressed groups explode into vacant niches. The Paleozoic era, spanning 290 million years from the Cambrian explosion to the end Permian extinction, represents one complete cycle of this pattern. Complex life emerged. Diversified. Filled ecosystems on land and in the sea. Developed intricate food webs, specialized forms, stable communities. Then catastrophe struck. And almost everything ended. The Mesozoic era that followed, the age of dinosaurs, represents the recovery and subsequent rediversification. A new cycle with new dominant groups, new ecosystems, new rules. That cycle also ended 66 million years ago, when an asteroid impact triggered the end Cretaceous extinction. And we're living in the recovery period, the Cenozoic era, when mammals and birds occupy the roles dinosaurs once filled. Earth's biological history is therefore not a steady progression toward increasing complexity or advancement. It's a series of boom and bust cycles. Long periods of relative stability punctuated by catastrophic extinctions, followed by recovery periods when life experiments with new forms and strategies. The Permian-Triassic boundary represents the most dramatic of these transitions, the moment when life came closest to complete failure. That it didn't fail completely, that survivors persisted and eventually diversified, testifies to life's resilience. But it also reveals life's fragility. Remove too many links from an ecosystem, disrupt too many chemical cycles, push environmental conditions beyond tolerable limits, and even 290 million years of evolutionary success offers no protection. Today, we're conducting our own extinction experiment. Atmospheric carbon dioxide levels are rising faster than at any time in the past 66 million years, possibly faster than any time since the end Permian. Global temperatures are increasing. Oceans are acidifying. Species are disappearing at rates hundreds of times above background levels. We're not at Permian-Triassic severity yet, but we're moving in that direction, and we're doing it with remarkable speed. The difference is that this time, the cause isn't volcanic eruptions or asteroid impacts. It's us. A single species, Homo sapiens, is altering planetary chemistry and climate at scales previously achievable only by massive geological events. The Paleozoic era ended in fire, suffocation, and acid. What emerged from that ending was a planet fundamentally transformed, populated by organisms that would have been unrecognizable to any Permian creature. Life continued, but not the same life. Recovery occurred, but not restoration. The world moved forward, carrying scars that remain visible in the fossil record 252 million years later. That's the pattern extinction establishes. Not death of all life, but death of familiar life. Not permanent ending, but permanent transformation. The question facing us now is whether we want to be part of the next transformation, or whether we'll join the trilobites, the tabulate corals, and the glossopterous forests in the fossil record of extinct failures. Earth will continue regardless. Life will persist in some form. But which forms survive, and which vanish forever, that's being decided right now, in real time, by choices we make daily. The Paleozoic era teaches us that recovery is possible. It also teaches us that recovery takes millions of years, and what emerges looks nothing like what was lost. The Permian-Triassic extinction stands as Earth's most severe test of biological resilience, a moment when the planet approached the threshold of complete sterilization. 96% of marine species vanished. 70% of land vertebrates disappeared. Even insects, those tireless survivors of every previous catastrophe, lost entire orders to the void. The numbers become abstract at this scale, almost meaningless, until you consider what they represent. Entire evolutionary lineages, hundreds of millions of years in the making, erased in perhaps 60,000 years. What makes this extinction uniquely terrifying isn't just magnitude. It's the mechanism. A cascade of environmental failures where each problem amplified the next until the planet's life support system simply broke. Volcanic eruptions triggered warming. Warming killed forests. Dead forests meant carbon accumulated unchecked. More carbon meant more warming. Ocean circulation collapsed. Oxygen disappeared from seawater. Hydrogen sulfide saturated the depths. Temperature gradients flattened. Mega El Niño events persisted for decades. Acid rain stripped nutrients from soil. Marine creatures suffocated in warming waters while their shells dissolved in acidifying seas. The Siberian traps weren't just large. They were sustained. 2 million years of eruption, cooking through coal deposits and organic sediments, releasing greenhouse gases at rates that overwhelmed every natural buffer. The planet tried to compensate. Photosynthesis removes CO2. Weathering locks carbon in rocks. Ocean chemistry absorbs atmospheric changes. But these processes operate on timescales of hundreds of thousands to millions of years. The Siberian traps dumped carbon into the atmosphere faster than any removal mechanism could respond. Positive feedbacks took over. The climate system entered runaway mode. Life, which had spent 290 million years building complex ecosystems, watched those ecosystems collapse from the bottom up. Primary producers died first, cutting energy flow at its source. Herbivores followed within months. Predators starved soon after. Food webs didn't simplify. They shattered. What remained were fragments, disconnected survivors in a world that no longer made biological sense. Recovery took 10 million years just to restore basic ecosystem function. 30 million years passed before terrestrial vertebrate communities matched pre-extinction complexity. Marine ecosystems required 50 million years to rebuild the intricate trophic structures and specialized gills that characterized Permian oceans. Half of 100 million years. And even then, what emerged wasn't restoration of what was lost. It was something fundamentally different. New dominant groups. New ecosystem architectures. New rules for survival. The Paleozoic era, that 290 million year span from the Cambrian explosion to the end Permian catastrophe, represents one complete cycle of life's experimentation on Earth. It began with the sudden appearance of complex body plans and hard-shelled organisms. It developed through the colonization of land, the rise of forests, the evolution of flight in insects, the diversification of fish, the emergence of tetrapods. It peaked with intricate ecosystems on every continent and in every ocean, billions of organisms filling every available niche. Then it ended. Almost completely. What survived wasn't the strongest or most advanced. Lystrosaurus wasn't superior to the synapsids that vanished. Small burrowing reptiles weren't more evolved than their extinct relatives. Marine bivalves that spread globally after the extinction weren't better designed than the diverse communities they replaced. Survivors possess traits that happen to match an unpredictable catastrophe. Small size. Low energy needs. Flexible diet. Ability to tolerate unstable conditions. These weren't advantages in the stable Permian world. They became advantages only when that world burned. This reveals something crucial about extinction and survival. Success during stable times doesn't predict success during crisis. Specialists dominate when conditions remain constant. Generalists persist when everything changes. The Permian-Triassic boundary rewrote Earth's ecological rules in real time, and only organisms capable of abandoning old strategies survived to write new ones. Today, we're running a similar experiment. Atmospheric CO2 is rising at rates comparable to the end Permian, perhaps faster. Global temperatures are increasing. Ocean pH is dropping. Species are disappearing at hundreds of times the background extinction rate. We haven't reached Permian-Triassic severity, not yet, but the mechanisms look disturbingly familiar. Rapid carbon release overwhelming natural buffers. Warming triggering positive feedbacks. Ecosystems stressed beyond their adaptive capacity. The difference is agency. The Siberian traps didn't choose to erupt. Continental drift didn't decide to form Pangaea. Geological processes operated according to physics and chemistry, indifferent to biological consequences. We have choice. We understand what's happening. We can see the trajectory. Whether we change course or accelerate toward our own boundary event remains an open question. The Paleozoic era ended in the greatest catastrophe complex life has faced. What followed was millions of years of struggle, experimentation, failure, and eventual success. Life continued because a few organisms, through luck and circumstance, carried the genetic potential for recovery. Their descendants rebuilt the world, but it took longer than our species has existed. Longer than our genus has existed. Longer than our entire evolutionary family has existed. That's the timescale of true recovery from severe mass extinction. Not years or centuries. Millions of years. And what emerges looks nothing like what was lost. The Mesozoic world of dinosaurs bore no resemblance to the Permian world of synapsids. The Cenozoic world of mammals shares little with either. Each era represents a fundamentally different experiment in how to organize life on a planet. We're living in the aftermath of the last major extinction, the one that ended the dinosaurs 66 million years ago. Our existence depends on that catastrophe. Mammals remained small and marginal for 160 million years while dinosaurs dominated. Only after the end Cretaceous extinction did our ancestors diversify, grow large, explore new ecological roles. Every human alive today descended from survivors of that event. Small, burrowing, generalist mammals that persisted when 75% of species could not. The Permian-Triassic extinction reminds us that survival isn't guaranteed. Dominance offers no protection. Complexity provides no immunity. When environmental conditions shift beyond tolerable limits, evolution's timescale becomes irrelevant. Adapt instantly or die. Most die. The few that survive do so not through superiority, but through possessing traits that happen to match unpredictable new conditions. Trilobites survived 4 previous mass extinctions across 250 million years. The end Permian erased them. Tabulate and rugose corals built reefs for hundreds of millions of years. They vanished completely. Glossopterous forests covered entire continents. They collapsed in hundreds of thousands of years. Success across deep time means nothing when the planet itself transforms. So what does this mean for us? We're conducting real-time experiments in atmospheric chemistry, ocean acidification, and rapid climate change. We're removing species faster than they can evolve. We're simplifying ecosystems that took millions of years to achieve current complexity. We're testing whether human civilization can survive conditions we're creating. The Permian-Triassic extinction suggests that complex, specialized systems are vulnerable. That rapid environmental change overwhelms adaptive capacity. That recovery takes timescales measured in geological eras, not human lifetimes. But it also demonstrates that life persists. Not all life. Not familiar life. But life in some form continues. The question isn't whether Earth will survive our impacts. It will. The question is whether we'll be part of what survives, or whether we'll join the catalog of extinct experiments. Whether humans in the far future will study our fossil record and wonder what went wrong. Whether some post-human intelligence will analyze the sharp boundary in rock layers marking the Anthropocene extinction and calculate that 90% of large mammals vanished in less than 100,000 years. The Paleozoic era began with explosion and ended with annihilation. It contained 290 million years of evolutionary innovation, ecological complexity, and biological success. None of it mattered when conditions exceeded tolerance limits. What mattered was which random organisms possessed traits allowing persistence through conditions nobody could have predicted. The survivors weren't chosen by merit. They were filtered by catastrophe. We had the knowledge to avoid becoming another extinction boundary. We understand the mechanisms. We can model the outcomes. We see the trajectory. The Permian-Triassic extinction wasn't preventable. It resulted from geological processes beyond any organism's control. Our current trajectory is different. It's driven by choices, by economic systems, by political decisions, by collective action or inaction. That means it's changeable, but only if change occurs fast enough to matter. The timescale is what makes this urgent. Geological processes operate slowly. Evolution operates slowly. Recovery operates slowly. But extinction, when it comes, happens fast. The end Permian proved that. 60,000 years from stable ecosystems to near-complete collapse. On human timescales, that's incomprehensibly long. On geological timescales, it's instantaneous. We're currently operating on timescales that match extinction, not recovery. Carbon release rates approaching volcanic eruption events. Temperature change rates exceeding most of the past 66 million years. Extinction rates hundreds of times above background. The Paleozoic era teaches us that planets can recover from almost anything. But recovery looks nothing like restoration. It's transformation. The world moves forward, permanently altered, carrying scars visible for hundreds of millions of years. Life continues, but not the same life. Ecosystems function, but not the same ecosystems. The survivors build new worlds from the ruins of old ones. And those new worlds, given enough time, develop their own complexity, their own diversity, their own intricate balance. Until the next catastrophe resets everything again. That's the pattern. Stability, catastrophe, recovery, stability, catastrophe, recovery. Earth's biological history is written in these cycles. The Permian-Triassic boundary marks the most extreme transition, the closest approach to total failure. It stands as evidence that even 290 million years of evolutionary success offers no guarantee of continued existence. That life is simultaneously resilient enough to survive near-complete destruction and fragile enough to be pushed to that brink. That the difference between survival and extinction often comes down to chance, to possessing the right traits at the right moment, to being small enough, flexible enough, efficient enough to persist when everything else fails. Every living organism today carries the legacy of Permian-Triassic survivors in its DNA. Every ecosystem functions according to rules established during the long recovery. Every species alive is here because some unknown ancestor, probably small and unremarkable, made it through Earth's worst day. We're all products of that catastrophe, descendants of disaster taxa that inherited an empty planet and slowly, over millions of years, filled it with new forms of life. The question now is whether we'll be ancestors or fossils. Whether future organisms will carry our legacy forward or study our remains. Whether we'll navigate the crisis we're creating or become another cautionary tale preserved in sedimentary layers. The Paleozoic era ended in fire and suffocation. The Mesozoic era ended with asteroid impact. The Cenozoic era's ending hasn't been written yet. We're writing it now, in real time, with every choice about energy systems, land use, ocean health, atmospheric composition. The Permian-Triassic extinction shows us what's possible when planetary systems break. Whether we heed that warning determines what comes next. Deep in the frozen vacuum of space, Chunks of ancient ice and rock are hurtling toward Earth at speeds that would vaporize steel on contact. Inside them, locked within crystalline structures older than our Sun, might be the answer to humanity's oldest question. Where did we come from? For decades, scientists dismissed comets as cosmic debris. Dirty snowballs with no real significance beyond their spectacular light shows. Then something changed. When we finally caught up to these objects, when our spacecraft touched them and tasted their chemistry, we found something nobody expected. The building blocks of life itself, fully formed, perfectly preserved, waiting. This isn't speculation anymore. It's data. Hard, repeatable, undeniable data that's forcing us to rewrite the story of life on Earth. Before we had telescopes, before we understood what comets were, they terrified us. Ancient civilizations saw them as omens. Disasters written in fire across the night sky. The Romans called them hairy stars because of their streaming tails. Chinese astronomers meticulously recorded their appearances, convinced they predicted the fall of dynasties. Nobody imagined these objects might be delivering something rather than threatening it. The modern scientific view wasn't much kinder. Through most of the 20th century, comets were considered interesting but irrelevant to the story of life. They were leftovers from the solar system's formation, frozen relics that occasionally swooped through the inner planets before vanishing back into the dark. Beautiful, yes. Important to biology, not a chance. That assumption held until we started catching them. In 2004, NASA's Stardust mission did something remarkable.
Guidance is internal. Roll program initiated.
It flew through the coma of Comet Wild 2, that glowing cloud of gas and dust surrounding the nucleus, and collected samples. Not much, just microscopic particles captured in a substance called aerogel, but enough. When those samples returned to Earth 2 years later, the results stopped people in their tracks. Glycine. A simple amino acid, one of the fundamental building blocks that cells use to construct proteins. It was sitting right there in the comet dust, formed in the freezing darkness of space long before Earth even existed. That discovery opened a door. If glycine could form in comets, what else might be hiding in them? The answer came from an unlikely source. In 2014, the European Space Agency's Rosetta mission arrived at Comet 67P, a rubber duck-shaped chunk of ice about 4 kilometers across. Instead of just flying past, Rosetta stayed. It orbited for 2 years, watching the comet wake up as it approached the Sun, measuring everything it could. What Rosetta found wasn't just interesting, it was revolutionary. The comet was outgassing 16 different organic compounds, not simple molecules, but complex carbon-based structures. Formaldehyde, methanol, ethanol, amino acids, and something else. Something that made biologists sit up and pay attention. Phosphorus. An element absolutely essential for life as we know it. It forms the backbone of DNA. It's in every cell membrane. Without phosphorus, Earth-style biology simply cannot function. And here it was, streaming off a comet billions of miles from the nearest living thing. The implications were staggering. These weren't random chemicals. They were the exact ingredients you'd need to start building the machinery of life. But finding ingredients isn't the same as proving they created something. You can have flour, eggs, and sugar sitting on a counter, and they won't spontaneously become a cake. Something has to bring them together under the right conditions. Something has to do the mixing. That's where Earth's early history becomes critical. 4.5 billion years ago, our planet was a molten nightmare. Volcanic hellscape, no stable crust, certainly no oceans. Not exactly a promising environment for delicate organic chemistry. Yet somehow, within a few 100 million years, life appeared. Not gradually, not tentatively, but explosively. By 3.8 billion years ago, we have clear evidence of cellular life already thriving. That timeline has always bothered scientists. It's too fast. Earth barely had time to cool down before biology showed up. Where did all the necessary building blocks come from? How did they organize themselves so quickly? The traditional answer was that Earth made them itself. Lightning strikes in a primordial atmosphere, volcanic vents pumping out chemicals, ultraviolet radiation breaking apart simple molecules and recombining them into complex ones. The famous Miller-Urey experiment in 1953 seemed to prove this was possible. Put some basic gases in a flask, add electricity to simulate lightning, and amino acids appear. Except there's a problem. We got the atmosphere wrong. The Miller-Urey experiment used methane, ammonia, and hydrogen, a strongly reducing mixture that favors organic chemistry. But geological evidence now suggests early Earth's atmosphere was mostly carbon dioxide and nitrogen. Run the experiment with those gases and you get almost nothing. The chemistry doesn't work. So if Earth wasn't making its own organic molecules efficiently, where were they coming from? Look up. Every year, Earth sweeps through debris left behind by comets. We see it as meteor showers, beautiful streaks of light as tiny particles burn up in the atmosphere. But not everything burns. Some material makes it through, settling gently onto the surface. Modern estimates suggest Earth gains about 40,000 tons of cosmic dust annually. That's now, in a relatively clean solar system. 4 billion years ago, during the period we call the Late Heavy Bombardment, the rate was millions of times higher. Picture it. Young Earth, still cooling, oceans just beginning to condense from steam. And it's being absolutely pelted by comets and asteroids, hundreds of impacts every year, each one delivering its cargo of organic molecules. Not just simple stuff, but complex, ready-made building blocks for biochemistry. The entire planet becomes a chemistry lab being constantly restocked with new ingredients. This is where the math gets interesting. Calculate the total mass of cometary material that hit Earth during the first billion years. Factor in the concentration of organic compounds we've measured on real comets. Run the numbers and you get something shocking. Comets could have delivered more organic carbon to early Earth than the planet could possibly have made on its own. By a lot. Maybe by factors of thousands or millions. But quantity isn't everything. You also need the right delivery mechanism. Drop complex organic molecules onto a planet from space and they face a problem. They're moving at cosmic speeds, tens of kilometers per second. That kind of impact generates heat. Lots of heat. Enough to break apart most chemical bonds and destroy exactly the compounds you're trying to deliver. Except comets have a trick. They're not solid rock. They're mostly ice, mixed with dust and organics. When a comet hits an atmosphere, or even a primordial ocean, that ice acts like a cushion. It absorbs energy, vaporizes, creates a shock buffer. Calculations show that organic molecules buried inside cometary ice can survive impacts that would obliterate anything else. The ice protects its cargo all the way down. Even better, that ice itself is valuable. Early Earth needed water. Lots of water. Our planet formed close to the sun, in a region too hot for ice to condense. The water in our oceans had to come from somewhere colder. Comets fit perfectly. They're essentially giant ice cubes that formed in the outer solar system and then migrated inward. Each impact was a water delivery, bringing not just H2O but also everything dissolved in it. We can test this idea chemically. Water molecules come in different isotopes, variations with extra neutrons. The ratio of regular hydrogen to deuterium, heavy hydrogen, works like a fingerprint. Measure it in Earth's oceans and compare it to measurements from comets. If the ratios match, you found your source. The results are messy. Some comets match Earth's ratio almost perfectly. Others are way off. What this tells us is that Earth's water probably came from multiple sources. Some comets, yes, but also asteroids, and possibly some water that was trapped in the rocks that originally formed our planet. It's a mixture, which actually makes sense. 4 billion years of bombardment meant Earth was sampling everything the solar system had to offer. But we're getting ahead of ourselves. Delivering organic molecules is one thing. Getting them to organize into something alive is something else entirely. The molecules are here. They're scattered across the early Earth's surface, dissolved in the oceans, maybe concentrated in tidal pools or around hydrothermal vents. But molecules don't spontaneously decide to become alive. They need to do something first. They need to replicate. This is the central mystery. Life, at its core, is information that copies itself. DNA holds instructions. Those instructions get read, executed, and then copied to make more DNA. But DNA can't copy itself alone. It needs proteins. Enzymes that unzip the double helix, read the code, assemble new strands. Proteins are molecular machines, and they're incredibly good at their jobs. Except proteins can't make themselves either. They need DNA to encode their blueprints. You see the problem. DNA needs proteins. Proteins need DNA. It's a chicken and egg paradox, except both the chicken and the egg are microscopically small and made of carbon chains. For decades, this looked unsolvable. Then, in the 1980s, scientists discovered something that changed everything. RNA, ribonucleic acid, DNA's simpler cousin, and RNA could do something nobody expected. It could act as both information storage and enzyme. Some RNA molecules, called ribozymes, could catalyze chemical reactions, including, critically, making copies of other RNA molecules. Suddenly there's a way out of the paradox. Forget DNA and proteins for now. Start with RNA. One molecule playing both roles. An RNA world, where these versatile chains are doing all the heavy lifting. Storing information, copying themselves, maybe even catalyzing the reactions needed to build their own components. It's elegant. Almost too elegant. But does it actually work? Test it. Take RNA molecules and put them under conditions that might have existed on early Earth. See if they can evolve, adapt, replicate without any help from modern biology. Researchers have done exactly this. They've created RNA molecules that can copy other RNA strands with reasonable accuracy. They've shown that random RNA sequences, given the right environment, can develop catalytic activity through pure trial and error. The chemistry works. RNA can bootstrap itself. But there's still a massive gap between one self-replicating RNA molecule and anything we'd recognize as alive. That molecule needs protection. It needs to separate itself from the environment, create an inside and an outside. Otherwise, every molecule it makes just diffuses away into the ocean. No concentration, no organization, no evolution. This is where membranes come in. Lipids, fatty molecules with one end that loves water and another that hates it, can spontaneously form bubbles. Vesicles. little spheres with a double-layered skin that keeps the inside separate from the outside. We see this in test tubes. Mix lipids and water and they self-assemble into something that looks startlingly like a cell membrane. No instructions needed. Just physics and chemistry doing their thing. Now imagine an RNA molecule that happens to be inside one of these lipid bubbles. It's replicating, making copies of itself. Those copies are trapped inside with it. The concentration builds. Maybe some of those RNA molecules catalyze reactions that help make more lipids, growing the membrane. The bubble gets bigger. Eventually it might split, dividing into two bubbles, each carrying RNA. You've just invented cellular division without involving a single protein or DNA molecule. This isn't life yet. Not quite, but it's something that can evolve. Bubbles with better RNA that replicates faster or makes useful products, will outcompete bubbles with worse RNA. Selection pressure exists even at this primitive level. And once you have selection, evolution is inevitable. The timeline here is staggering. We're talking about processes that might have taken tens of millions of years. Maybe 100 million. The early Earth had time, lots of it, and it had variety, thousands of different environments, each running its own chemical experiments. Shallow pools heated by the sun, deep ocean vents with their chemical gradients, underground water systems percolating through mineral-rich rock. Ice formations with liquid pockets. Every one of these is a potential laboratory. What's fascinating is that you don't need everything to happen in one place. Maybe RNA replication gets figured out in one environment, membrane formation in another. Then geological processes, volcanic eruptions, tidal movements, mix everything together. Combine the solutions. Evolution doesn't follow a neat, linear path. It's messy, parallel, full of dead ends and lucky accidents. But here's what really matters. Once you have something that can replicate and evolve, even if it's incredibly primitive, you've crossed a threshold. Because evolution is brutally good at solving problems. Give it enough time and enough variation, and it will find solutions to challenges that seem impossible. Like replacing fragile RNA with more stable DNA, or developing protein synthesis to build better enzymes than ribozymes could ever be. The transition from an RNA world to the DNA protein world we have now probably happened gradually. Maybe DNA started as just a more stable way to store backup copies of important RNA sequences. Then it got better at the job. Eventually it took over information storage completely, while proteins specialized in doing the actual work. RNA got relegated to the role it plays today, messenger, translator between DNA and proteins. We can see echoes of this ancient RNA world in modern cells. Ribosomes, the molecular machines that build proteins, are made mostly of RNA. The energy currency of the cell, ATP, is basically an RNA building block with some extra phosphate groups attached. Even DNA synthesis requires RNA primers to get started. These are fossils, chemical fossils, remnants of a time when RNA did everything. But proving this all happened is hard. RNA doesn't fossilize. It's too fragile. The oldest actual fossils we have are from about 3.5 billion years ago. Stromatolites, layered rock structures built by bacterial mats. By that point, life was already sophisticated. DNA, proteins, cell walls, photosynthesis. The really interesting stuff, the origin itself, happened earlier. Maybe 4 billion years ago. Maybe even older. And it left almost no direct evidence. So we're forced to reconstruct it from clues, chemical signatures in ancient rocks, isotope ratios that suggest biological activity, computer simulations of prebiotic chemistry, lab experiments trying to recreate the conditions. Every piece of evidence is indirect, circumstantial. But they all point in the same direction. Life emerged from chemistry, not through some mysterious vital force, but through processes we can understand, replicate, and test. There's one more piece to this puzzle. One that makes the whole thing even stranger. The genetic code. The way DNA sequences get translated into amino acids, which then fold into proteins. This code is nearly universal. Bacteria use it. Plants use it. Animals use it. With tiny variations, every living thing on Earth reads DNA the same way. Which means the code was established early, probably before the last common ancestor of all life. And once it was set, it was locked in. Changing your genetic code would be like rewriting the operating system on a computer while it's running. Possible in theory, but catastrophically difficult in practice. Why this particular code? Is it optimal? Or just a frozen accident, the first solution that worked well enough? Some researchers argue it's actually pretty good at minimizing the damage from mutations. Similar codons often code for chemically similar amino acids. So if a mutation changes one letter in a codon, there's a decent chance the resulting protein still works. That's not random. That's error correction built into the system. But it's also consistent with evolution. An early, slightly error-prone genetic code that worked well enough to get life started. Then, over time, selection pressure refined it. Lineages with codes that handled errors better survived. Those with worse codes died out. What we're left with is the optimized version. Not perfect, but good enough to support the incredible diversity of life we see today. Step back and look at the full picture. 4 billion years ago, maybe earlier, Earth was a planet covered in organic chemistry experiments. Molecules delivered by comets and asteroids, synthesized in the atmosphere, cooked up around volcanic vents. RNA figuring out how to replicate. Lipids forming membranes. Everything mixing, reacting, competing. And somewhere in that chaos, a combination of molecules found a way to persist, to improve, to evolve. That combination was the first life. Not a single moment of creation, but a gradual transition from complex chemistry to simple biology. The boundary between non-living and living wasn't a line. It was a gradient. And we're still not entirely sure where exactly to draw it. Once life existed, even in its most primitive form, the rules changed. Natural selection kicked in. Not as a guiding force, but as an automatic filter. Anything that replicated more efficiently than its competitors spread. Anything less efficient vanished. No intention required. Just math playing out over deep time. The first cells were probably nothing like modern bacteria. Simpler, messier. Their membranes leaked. Their metabolism was inefficient. But they worked well enough to persist. And that's all evolution needs. A starting point. Once you have replication, variation, and selection, improvement becomes inevitable. Not planned, just statistically certain. Early Earth was divided into two broad domains: bacteria and archaea. They look superficially similar under a microscope. Single cells, no nucleus, circular DNA. But genetically, they're as different from each other as either is from us. Different membrane chemistry, different metabolic pathways, different cellular machinery. This split happened early, probably before 3.5 billion years ago. Why it happened is still debated. Maybe different environments selected for different solutions. Maybe it was just chance, two lineages drifting apart. Either way, both domains survived. Both thrived. Both are still here today. For the next 2 billion years, life stayed small. Microbial. Single cells doing their thing in the oceans, in sediments, around vents. It doesn't sound exciting, but this period was crucial. Because microbes invented almost everything: photosynthesis, respiration, nitrogen fixation, fermentation. Every major metabolic pathway we see in complex life today was pioneered by bacteria or archaea. They figured out how to extract energy from sunlight, from minerals, from organic molecules. They built the biochemical toolkit that all later life would inherit. Then, around 2.5 billion years ago, something dramatic happened. Cyanobacteria, a group of photosynthetic bacteria, started producing oxygen as a waste product. Not a little oxygen, industrial quantities, enough to fundamentally alter the planet's chemistry. This wasn't planned. Oxygen was toxic to most organisms at the time. But cyanobacteria had evolved a way to deal with it, and they thrived. Everyone else had to adapt or die. The buildup was slow at first. Oxygen reacted with dissolved iron in the oceans, forming rust that settled to the seafloor. Those deposits, called banded iron formations, are some of the richest iron ore reserves we have today. For hundreds of millions of years, the oceans soaked up the oxygen. But eventually, the iron ran out. Oxygen started accumulating in the atmosphere. This is called the Great Oxidation Event. It fundamentally restructured the biosphere. Most anaerobic organisms retreated to oxygen-free environments. Deep sediments, guts of animals, anywhere they could avoid the toxic gas. But other lineages adapted. They evolved ways to use oxygen for respiration, extracting far more energy from the same nutrients. Aerobic respiration is about 15 times more efficient than anaerobic metabolism. That's a game changer. It opened the door to larger, more complex organisms. But complexity didn't arrive immediately. For another billion years, life stayed stubbornly simple. Bacteria and archaea dominated. No multicellular organisms. No complex cells. Just microbes. Why the delay? We're not entirely sure. Maybe oxygen levels weren't high enough yet. Maybe nutrients were limiting. Maybe it just took that long for the right innovations to evolve. Evolution doesn't optimize for speed. It optimizes for survival. And single-celled life was surviving just fine. Then, around 1.5 to 2 billion years ago, something unprecedented happened. A bacterial cell got engulfed by an archaeal cell. Normally, that's dinner. But this time, the bacterial cell survived inside. It kept its own genome, its own membrane, and it started providing a service. It processed oxygen, generating energy for the host. In return, it got protection and nutrients. This wasn't cooperation. Not at first. More like a hostage situation that gradually became mutually beneficial. Over time, the bacterial cell lost most of its independence. Its genome shrank. Many of its genes migrated to the host's nucleus. But it kept its essential function: energy production. Today, we call these structures mitochondria. Every complex cell on Earth, every plant, every animal, every fungus, has them. They're the descendants of that ancient symbiotic event. Without mitochondria, complex life as we know it wouldn't exist. This wasn't a one-time fluke. It happened again with photosynthesis. An archaeal cell engulfed a cyanobacterium. Same deal. The cyanobacterium survived inside, kept photosynthesizing, became a permanent resident. Today, we call these chloroplasts. Every plant and algae has them. Two separate endosymbiotic events. Two different bacterial lineages incorporated into archaeal hosts. Both absolutely critical for the evolution of complex life. These hybrid cells are called eukaryotes. They're fundamentally different from bacteria and archaea. They have a nucleus, complex internal structures, linear chromosomes, sexual reproduction, the ability to grow large and differentiate into specialized cell types. Every organism you can see without a microscope is a eukaryote. Every tree, every insect, every fish, every human. We're all descendants of those ancient mergers. But even with eukaryotic cells, life stayed mostly single-celled for a long time. Maybe another billion years. Single eukaryotes floating around, eating bacteria, photosynthesizing. Then, gradually, some lineages started sticking together. Colonies formed. Simple at first. Just clusters of identical cells. But over time, cells within colonies began specializing. Some handled reproduction. Others handled feeding. Others provided structure. This is the origin of multicellularity. Not a sudden leap, but a gradual transition from independent cells to cooperative groups. Multicellularity evolved multiple times independently. Plants did it. Animals did it. Fungi did it. Even some bacteria and algae pulled it off. Each time, the pattern was similar. Cells stuck together, started dividing labor, became interdependent. Why? Because in certain environments, being big has advantages. You're harder to eat. You can capture more resources. You can differentiate into specialized structures. Roots, leaves, muscles, nerves. Suddenly, evolution had a whole new playground. By about 600 million years ago, the first complex multicellular organisms appeared in the fossil record. Weird, soft-bodied creatures called the Ediacaran biota. Some looked like quilted fronds. Others like segmented discs. They don't resemble anything alive today. Most of them went extinct without leaving descendants. But they proved that large, complex life was possible. They set the stage for what came next. Then, around 540 million years ago, the Cambrian explosion happened. Not an explosion in the literal sense. More like a sudden diversification. Within about 20 million years, most major animal body plans appeared. Arthropods, mollusks, chordates, echinoderms. Animals with hard shells, jointed legs, segmented bodies, eyes. The fossil record goes from sparse and strange to abundant and recognizable. What triggered the Cambrian explosion? Probably multiple factors. Oxygen levels rising to a critical threshold. Predator-prey dynamics creating evolutionary arms races. The evolution of developmental genes that allowed for complex body plans. Ecological feedback loops where one innovation triggered others. It wasn't a single cause. It was a cascade. Once it started, it accelerated. One of the most important innovations was eyes. The ability to see opened up entirely new survival strategies. Predators could hunt more effectively. Prey could escape more efficiently. Vision created selection pressure for faster movement, better armor, more sophisticated nervous systems. Suddenly, being smart mattered. Brains got bigger. Behavior got more complex. Another key innovation was hard body parts. Shells, exoskeletons, bones. Before the Cambrian, almost everything was soft-bodied. Hard structures provided protection, but also structural support. They allowed animals to grow larger, move faster, dig deeper. And crucially, they fossilized. Which is why the Cambrian fossil record is so much richer than anything before it. Not necessarily because life suddenly became more diverse, but because it became more preservable. From the Cambrian onward, evolution proceeded in recognizable patterns. Animals colonized the oceans, then the land. Plants followed, turning barren continents into forests. Insects evolved, then amphibians, then reptiles, then mammals and birds. Each group building on the innovations of the ones before. Each adapting to new environments, filling new niches. But here's the thing. Every step in this story, from the first self-replicating molecules to the Cambrian explosion, was contingent. Not inevitable. If any number of things had gone differently, life might not exist. Or it might exist in forms completely unrecognizable. The fact that we're here, examining our own origins, is the result of billions of years of accidents, near misses, and unlikely events. Earth could have stayed frozen during snowball Earth periods. Life might never have survived. The Great Oxidation Event could have poisoned everything without any lineages adapting. Endosymbiosis might never have happened. Multicellularity might never have evolved. Any of these failures would have left Earth as a microbial planet indefinitely. Interesting, sure, but not capable of producing anything like us. Yet it didn't fail. Every bottleneck, every crisis, every random event lined up just right. Not because of destiny, just because of probability playing out over unimaginable timescales. Given enough planets, enough time, improbable things become statistically likely. We're the outcome of one very long, very unlikely chain of events. And that chain is still unfolding. The story of life on Earth isn't just about what survived. It's about what almost didn't. About 5 times in the past 540 million years, mass extinction events wiped out most species on the planet. Not small die-offs. Catastrophic collapses where 70 to 95% of all species disappeared. These weren't gradual declines. They were biological apocalypses that reset evolution and forced life to rebuild from whatever happened to make it through. The first major extinction happened at the end of the Ordovician period, about 445 million years ago. At the time, most life still lived in the oceans. Trilobites, brachiopods, early fish. The continents were barren rock. Then the climate destabilized. A rapid ice age locked up vast amounts of water as glaciers. Sea levels dropped dramatically. Shallow marine habitats, where most life existed, simply disappeared. Organisms adapted to warm, stable conditions suddenly faced freezing temperatures and habitat loss. About 85% of marine species went extinct. But here's what's interesting. The extinction happened in 2 pulses. First, when the Ice Age began. Second, when it ended and oceans warmed rapidly again. Life couldn't adapt to the cold. Then it couldn't adapt when things warmed back up. Whichever way the climate swung, something died. The survivors were generalists. Species that could tolerate wider ranges of temperature, salinity, oxygen levels. Specialists, finely tuned to specific conditions, were wiped out. This pattern repeats in every mass extinction. Adaptability beats optimization when the environment becomes unpredictable. The second major extinction came at the end of the Devonian period, around 375 million years ago. This one unfolded over several million years. Not a single catastrophic event, but a prolonged crisis. The leading hypothesis involves ocean anoxia. Large areas of the ocean losing oxygen. Fish, invertebrates, coral reefs, all suffocating. What caused the anoxia? Possibly massive algae blooms triggered by nutrient runoff from the newly forested continents. plants had just colonized land. Their roots broke down rock, releasing nutrients into rivers that flowed into the ocean. Too many nutrients caused explosive algae growth. When the algae died and decomposed, they consumed oxygen. The oceans became dead zones. About 75% of species disappeared. Reef ecosystems collapsed. Armored fish, which had dominated for millions of years, were devastated. Sharks, more adaptable, survived. This extinction reshaped marine life. It cleared space for new groups to evolve. But it took millions of years for biodiversity to recover. The third extinction is the big one. The Permian-Triassic event, 252 million years ago. The worst mass extinction in Earth's history. About 96% of marine species and 70% of terrestrial vertebrate species went extinct. Life came closer to complete annihilation than at any other time. The cause? Massive volcanic eruptions in what's now Siberia. Not a single volcano. An entire region erupting for hundreds of thousands of years. Lava flows covering an area larger than Europe. The eruptions released enormous amounts of carbon dioxide, sulfur dioxide, and other gases. Global temperatures spiked. Oceans acidified. Oxygen levels plummeted. On land, acid rain and greenhouse heating devastated ecosystems. In the oceans, warming and acidification killed off calcifying organisms. Coral reefs vanished. Food chains collapsed from the bottom up. Some researchers think the warming triggered the release of methane from ocean floor deposits. Methane is a far more potent greenhouse gas than CO2. If enough was released, it would have created a runaway warming effect. Temperatures potentially rose 10 degrees Celsius or more. The planet became a hothouse. Only the most resilient organisms survived. Small body size helped. Lower metabolic demands. Ability to hide underground or underwater. Generalist diets. Life that could eat almost anything had an advantage over specialists. The recovery took 10 million years. Longer than any other extinction. For millions of years after the Permian extinction, ecosystems remained impoverished. Low diversity. Simplified food webs. But eventually, life rebounded. And the groups that survived went on to dominate the Mesozoic. Including the archosaurs, the lineage that would produce dinosaurs. The fourth major extinction happened at the end of the Triassic period, about 201 million years ago. Another round of massive volcanism. This time in the central Atlantic, as the supercontinent Pangaea began to break apart. Rifting continents triggered volcanic eruptions that lasted for hundreds of thousands of years. Again, CO2 levels spiked. Oceans acidified. Temperatures soared. About 80% of species went extinct. But this extinction had an unusual outcome. It cleared the way for dinosaurs. Before the Triassic extinction, dinosaurs were relatively minor players. They existed, but so did many other reptile groups. Crocodile relatives, large amphibians, early mammal ancestors. All competing for the same resources. The extinction removed most of those competitors. Dinosaurs, for whatever reason, were better at surviving the crisis. Maybe their upright stance. Maybe their respiratory systems. Maybe just luck. But in the aftermath, they diversified rapidly and became the dominant land animals for the next 135 million years. Which brings us to the fifth extinction. The one everyone knows. The end Cretaceous event, 66 million years ago. The asteroid impact that killed the dinosaurs. This one was different. Not a slow burn like the others. Not volcanism or climate shifts playing out over millennia. This was sudden. Catastrophic. A 10-kilometer-wide asteroid slammed into what's now the Yucatan Peninsula at 20 kilometers per second. The impact released energy equivalent to billions of nuclear bombs. It vaporized rock. Triggered earthquakes. Generated tsunamis. Ignited global wildfires. But the real killer was the aftermath. The impact threw trillions of tons of dust and aerosols into the atmosphere. Sunlight was blocked. Photosynthesis stopped. Temperatures plummeted. Plants died. Herbivores starved. Carnivores followed. Within months, ecosystems collapsed. About 75% of all species went extinct, including all non-avian dinosaurs. Not because they were weak. Not because they were poorly adapted. But because the rules changed instantly and completely. No amount of evolutionary success mattered when the sun disappeared. The survivors were small, burrowing animals, scavengers, anything that could hide underground or underwater, anything with low energy requirements. Birds made it through, though most species didn't. Mammals survived, but only the small ones. Crocodiles and turtles, with slow metabolisms, endured. In the aftermath, the planet was dark, cold, and nearly lifeless for years. Then, slowly, life returned. Plants regrow from seeds and roots. Survivors emerged and began to spread. Ecological niches, empty for the first time in millions of years, were filled by whatever happened to be around. Mammals, previously limited to small nocturnal roles, suddenly had opportunities. No more dinosaurs to compete with. No more giant predators. Within 10 million years, mammals had diversified into dozens of new forms. Browsers, grazers, predators, climbers, swimmers. The age of mammals had begun. Not because mammals were superior, but because dinosaurs were gone. Each of these 5 mass extinctions reset the clock. They didn't erase life, but they reorganized it. Groups that had dominated for millions of years vanished. New groups, previously marginal, took over. Evolution doesn't have a direction. It doesn't move toward complexity or intelligence. It just responds to whatever pressures exist at the time. And when those pressures are catastrophic, the response is equally extreme. Survival in a mass extinction isn't about being the best. It's about being lucky enough to have the right traits at the right moment. Small size when food is scarce. Generalist diet when ecosystems collapse. Burrowing behavior when the surface becomes uninhabitable. These aren't strengths in normal times. They're insurance policies for disasters. And here's the uncomfortable part. We're living in the 6th mass extinction right now. Species are disappearing at rates comparable to the Big Five. Not from asteroid impacts or volcanic eruptions. From us. Habitat destruction. Climate change. Overhunting. Pollution. We're not just witnesses to extinction. We're the cause. And unlike previous extinctions, this one is happening in real time. Fast enough to observe. Fast enough to measure. But possibly too fast to stop. The difference is, we know it's happening. We can see the patterns. We understand the mechanisms. Previous mass extinctions were blind cosmic accidents. This one is optional. Which makes it either more tragic or more hopeful, depending on what we do next. The question isn't whether Earth will survive. It will. Life has endured worse. The question is what form that life will take. Weather will be part of it. And what we're willing to do to change the trajectory. Earth's history isn't just a record of extinctions. It's a record of recoveries. And those recoveries follow patterns. Predictable, repeatable patterns that play out over millions of years. Understanding them reveals something crucial about how life actually works when everything falls apart. After each mass extinction, the planet enters what scientists call a dead zone. Not literally dead, but functionally empty. Food webs are shattered. Ecosystems lack structure. Energy flows are disrupted. The survivors exist, but they're not thriving. They're just hanging on in a world that doesn't work properly yet. This phase lasts anywhere from hundreds of thousands to millions of years. During this time, diversity remains low. A few generalist species spread widely, filling multiple roles because specialists haven't evolved yet. Think of it as ecological simplicity. Not because life can't be complex, but because complexity requires time to build. Then something shifts. Resources accumulate. Populations grow. Competition increases. And suddenly, evolution accelerates. New species branch off. Specialists emerge. Food webs gain layers. This is the recovery phase, where diversity explodes and ecosystems regain their structure. But here's what matters. The new ecosystems don't look like the old ones. They're built from different parts, organized around different principles, dominated by different groups. Recovery doesn't mean restoration. It means reinvention. After the end Permian extinction, the worst in Earth's history, recovery took roughly 10 million years. Longer than any other mass extinction. Why? Because the damage was deeper. Ocean chemistry was disrupted. Carbon cycles were broken. Climate remained unstable for millions of years. Life had to wait for the planet itself to stabilize before it could rebuild. The Triassic period that followed looked nothing like the Permian. Synapsids, which had dominated before, were reduced to minor roles. Reptiles, particularly archosaurs, took over. These were the ancestors of dinosaurs and crocodiles. They succeeded not because they were superior, but because they happened to have traits that worked in new conditions. After the end Cretaceous extinction that killed the dinosaurs, recovery was faster. About 2 to 3 million years before ecosystems regained complexity. Why quicker this time? The planet wasn't as severely damaged. Ocean chemistry recovered faster. Climate stabilized sooner. And crucially, more lineages survived, providing more raw material for evolution to work with. Mammals filled the empty niches left by dinosaurs. But they didn't just become small versions of what came before. They evolved entirely new body plans, new feeding strategies, new ways of moving and reproducing and interacting. Within 10 million years, mammals had diversified into forms ranging from tiny shrews to early whales. This reveals a fundamental truth about evolution. It's not progressive. It doesn't aim toward improvement. It's opportunistic. Whatever works in the current environment spreads. Whatever doesn't, disappears. The best organism is simply the one that survives long enough to reproduce. And survival depends heavily on luck. Being in the right place when disaster strikes. Having the right traits when conditions change. Being part of a lineage that happens to persist. Intelligence doesn't guarantee survival. Size doesn't. Strength doesn't. Adaptation to current conditions definitely doesn't, because those conditions can change overnight. This is why predicting recovery is so difficult. We can identify general patterns, but the specifics depend on which groups survive and what opportunities they find. After the dinosaurs, it could have been something other than mammals. If a few key lineages had gone extinct, Earth's history would look completely different. Now consider our current situation. We're in the early stages of a mass extinction. Species are vanishing rapidly. Ecosystems are degrading. But we're not yet in the dead zone. That comes later, if current trends continue. Which means we're at a decision point. We can still influence the outcome. What would recovery look like after a human-caused mass extinction? Hard to say. It depends on what survives. If large mammals disappear, something else will eventually fill those roles. Maybe birds. Maybe reptiles. Maybe something unexpected. Evolution doesn't care about our preferences. If humans disappeared tomorrow, Earth would recover. It might take millions of years, but diversity would return. New species would evolve. Ecosystems would rebuild. The planet has done this before, multiple times. It's resilient in ways that individual species aren't. But that's not a comforting thought. Because from our perspective, recovery after our extinction wouldn't include us. We'd be a thin layer in the fossil record. Evidence of a species that emerged, dominated briefly, then vanished. Just like the dinosaurs. Just like the trilobites. Just like thousands of other lineages that once seemed permanent. The real question isn't whether Earth will recover. It's whether we want to be part of that recovery. Whether we're willing to change our behavior to remain part of the story. Because unlike previous mass extinctions, this one comes with awareness. We understand what's happening. We can measure it. We can model future scenarios. We have knowledge that no species has ever possessed before. That knowledge creates responsibility. Not moral responsibility in some abstract sense, but practical responsibility. We're causing changes that will determine which species persist and which don't. Including possibly our own. And unlike an asteroid impact, these changes are gradual enough that we can respond. If we choose to. But here's the hard part. Responding effectively requires acting against immediate self-interest. Preserving habitat means not developing land. Reducing emissions means changing energy systems. Limiting consumption means accepting less material wealth. These aren't easy choices. They're not even obviously rational from an individual perspective. Yet they're necessary from a species perspective. From an ecosystem perspective. From a long-term survival perspective. The same perspective that matters when you're looking at geological timescales and extinction patterns. Because on those timescales, short-term gains vanish. Only persistence matters. Only what survives long enough to leave descendants. This is where human intelligence becomes either our greatest asset or our fatal flaw. We can understand long-term consequences in ways other species can't. We can plan beyond our own lifetimes. We can coordinate globally. But we can also rationalize inaction. Prioritize immediate comfort. Assume someone else will solve the problem. Other species don't face this dilemma. They can't choose to prevent extinction. They simply respond to immediate pressures, and either their traits work or they don't. Humans are the first species capable of consciously deciding whether to alter our trajectory. Whether to use our intelligence to ensure our persistence. The fossil record shows that dominance is temporary. Every group that once ruled eventually declined. Trilobites dominated for 270 million years, then vanished. Dinosaurs lasted 165 million years, then disappeared. humans have existed for maybe 300,000 years. We've been technologically advanced for less than 10,000. We're newcomers. And newcomers don't have track records of stability. What we do have is unprecedented power. Power to reshape ecosystems. Power to drive climate change. Power to cause extinctions at rates comparable to asteroid impacts. That power doesn't make us immune to extinction. It makes us capable of causing our own. The patterns from previous mass extinctions suggest what might happen next. If we continue current trends, diversity will decline. Ecosystems will simplify. Specialist species will disappear first. Then larger species. Then anything requiring stable conditions. Eventually, we reach a threshold where ecosystems can't provide the services we depend on. Clean water. Stable climate. Pollination. Soil formation. Food production. At that point, human civilization becomes unsustainable. Not because we lack technology, but because the biological foundation collapses. We can't engineer our way out of ecosystem failure. We depend on functional ecosystems the same way every other species does. Remove enough pieces, and the whole structure falls apart. This isn't speculation. It's pattern recognition. Every mass extinction followed similar trajectories. Stress accumulates. Systems become fragile. A final trigger causes collapse. The only difference now is we can see it coming. We have data, models, projections. We know which actions accelerate the problem and which might slow it. Whether we act on that knowledge determines what the next few million years look like. Whether the Anthropocene becomes a brief anomaly or a major extinction event. Whether humans persist or become another fossil layer. Whether intelligence, our defining trait, proves adaptive or maladaptive on evolutionary timescales. The answer isn't predetermined. Evolution doesn't script outcomes. It responds to conditions. And conditions, for the first time in Earth's history, are partially under the control of one species. That's never happened before. We don't have precedent for a species consciously shaping its own evolutionary future. Which makes this moment unique. Not just in human history, but in planetary history. We're the first species capable of understanding mass extinctions while potentially causing one. The first that can choose whether to continue down that path. The first with enough knowledge to know better and enough power to do something about it. What we do next matters. Not because the universe cares. Not because Earth cares. But because we care. Because we're capable of caring about things beyond our immediate survival. About other species. About future generations. About whether the story continues or ends with us. That capacity for long-term thinking is either our salvation or our epitaph. And we're in the process of finding out which. Looking back at the fossil record reveals something unsettling. Intelligence rarely appears as a survival trait. Most successful lineages, the ones lasting tens or hundreds of millions of years, rely on simplicity. Bacteria, jellyfish, crocodiles. They don't solve problems. They persist through durability. Intelligence is expensive. It requires large brains, extended development periods, high energy intake. For most of Earth's history, those costs outweighed the benefits. Only in specific circumstances, environments demanding flexibility and learning, did intelligence become advantageous. And even then, it remained rare. Out of billions of species across 4 billion years, only one developed technology. That's not a sign of inevitability. It's statistical noise. Which raises a question. If intelligence is so rare and so costly, what happens when it creates problems faster than it solves them? When the very trait that enabled survival becomes the mechanism of decline? We're testing that now. Human intelligence produced agriculture, medicine, technology. It extended lifespans, reduced infant mortality, enabled population growth beyond any precedent. But it also produced weapons capable of ending civilization in hours. Pollution that persists for millennia. Climate disruption that compounds across decades. We're intelligent enough to create these problems. Whether we're intelligent enough to solve them remains unproven. And the clock is running. Not in human time, where decades feel long. In geological time, where our entire civilization is a blink. If we disappeared tomorrow, future geologists would find a thin layer marking our existence. Plastics, concrete, radioisotopes, a brief spike in carbon isotopes, then silence. The planet would continue. Life would recover. It always does. Not the same life, not the same ecosystems, but something. Earth doesn't need humans. We need Earth. That asymmetry matters. We talk about saving the planet, but that's backwards. The planet will be fine. It survived 5 mass extinctions, supervolcano eruptions, asteroid impacts, ice ages, hothouse climates. It'll survive us. What we're actually trying to save is ourselves. Our way of life. The stable conditions we evolved to exploit. Those conditions aren't guaranteed. They're contingent on systems we're actively destabilizing. And once those systems cross certain thresholds, they don't snap back. They reorganize around new equilibria. Equilibria that might not include industrial civilization or large human populations or humans at all. That possibility should focus attention. Because unlike previous species facing extinction, we can see it coming. We have data showing ocean acidification rates, temperature projections, biodiversity decline curves, ecosystem collapse timelines. We know where current trajectories lead. And yet, Knowing doesn't guarantee action. Information alone never changes behavior. If it did, everyone would exercise, save money, avoid processed food. But knowing what's good for us and doing it are different things. The gap between knowledge and action defines the human condition. And right now, that gap is widening. We know fossil fuels drive climate change. We keep burning them. We know industrial agriculture depletes soil. We keep expanding it. We know overfishing collapses stocks. We keep fishing. Not because we're stupid. Because short-term incentives override long-term consequences. Because individual rationality produces collective irrationality. Because the benefits of harmful actions accrue to individuals while the costs distribute across everyone. That's not a moral failing. It's a structural problem. And structural problems require structural solutions. Individual action matters, but it's insufficient. Recycling, reducing consumption, changing diet, all positive steps. But they don't address the underlying systems driving ecosystem collapse. Those systems, energy infrastructure, agricultural practices, economic incentives, require coordinated policy changes, which requires political will, which requires public pressure, which requires enough people caring enough to demand change. And that's where we are. In a narrow window where the trajectory is set but not locked. Where the momentum is strong but not irreversible. Where outcomes remain uncertain because they depend on choices not yet made. This moment won't last. Windows close. Systems reach tipping points. Momentum becomes irreversible. The question is whether we recognize the moment while we're in it. Whether we understand that what feels like normal is actually unprecedented. That the stability we take for granted is historically anomalous. That the future isn't guaranteed to resemble the past. Because it won't. The planet we're creating will be fundamentally different from the one we inherited. Hotter. Less biodiverse. Less stable. Whether it remains habitable for billions of humans depends entirely on how much hotter, how much less diverse, how much less stable. Those aren't abstract variables. They're outcomes of specific decisions. Energy policy. Land use. Consumption patterns. Trade agreements. Infrastructure investments. Decisions being made now, today, by governments, corporations, individuals. Each decision moves the needle. Slightly. Incrementally. But cumulatively, they determine trajectory. And trajectory determines destination. We like to think we're separate from nature. That technology insulates us from ecological limits. That intelligence exempts us from evolutionary pressures. But we're not separate. We're embedded. We breathe the same air. Drink the same water. Depend on the same ecosystem services as every other organism. Our cities, Our technology, our entire civilization rests on a foundation of functional ecosystems. Remove that foundation and everything collapses. Not might collapse. Will collapse. It's physics. You can't support a structure after removing its base. And we're systematically removing the base. Deforestation. Ocean acidification. Soil depletion. Aquifer exhaustion. Pollinator decline. Each one weakens the foundation. Each one moves us closer to structural failure. We're not facing one problem. We're facing interconnected system failures happening simultaneously. Climate change amplifies species extinction. Species extinction reduces ecosystem resilience. Reduced resilience accelerates climate impacts. Feedback loops compound. Tipping points cascade. And suddenly, gradual change becomes rapid collapse. That's how complex systems fail. Slowly, then all at once. The challenge is acting during the slow phase. When problems seem manageable. When denial remains plausible. When short-term costs feel more real than long-term consequences. Acting requires overriding our evolutionary programming. We evolved for immediate threats. Predators. Starvation. Injury. Our brains are wired for rapid response to visible danger. But climate change isn't a predator. It's a statistical shift. A gradual accumulation. A probability distribution changing shape. Our brains aren't built to process that. We don't feel threatened by parts per million. By decimal point temperature increases. By percentage changes in biodiversity. We feel threatened by things with teeth. By things that can hurt us now. Which is why this is hard. Why knowing isn't enough. Why information doesn't automatically translate to action. We're asking people to respond emotionally to spreadsheets. To feel urgency about graphs. To sacrifice immediate comfort for abstract future benefits. That's not how humans work. But it's what the situation requires. Which means we need to change how we work. Not our biology, that's too slow. But our systems. Our institutions. Our decision-making frameworks. We need structures that account for long-term consequences. That price in externalities. That prioritize sustainability over quarterly profits. That value ecosystem health over GDP growth. Those structures don't exist by default. They require intentional design. Political will. Social pressure. Cultural shifts. They require enough people demanding something different. Enough people recognizing that current systems are driving us toward collapse. Enough people willing to support changes that might be personally inconvenient but collectively necessary. And that's the real test. Not whether we can develop solutions, We have solutions. Renewable energy, regenerative agriculture, circular economies, ecosystem restoration. The technology exists. The knowledge exists. What's missing is implementation at scale. What's missing is political and economic systems that prioritize long-term survival over short-term extraction. What's missing is collective willingness to accept that infinite growth on a finite planet is mathematically impossible. That's the hard part. Not the science. Not the engineering. The acceptance that our current trajectory is unsustainable. That something has to change. That we can't keep doing what we're doing and expect different results. And we're running out of time to figure this out. Not in a dramatic, countdown clock way, but in the sense that every year of delay makes the problem harder. Every ton of carbon emitted stays in the atmosphere for decades. Every species lost is gone permanently. Every ecosystem threshold crossed is effectively irreversible on human timescales. We're making decisions now that will echo for thousands of years. Decisions about what kind of planet we leave behind. What kind of future we're creating. Whether intelligence, our defining characteristic, proves adaptive or catastrophic. The answer isn't written yet. We're writing it. Right now. Through choices large and small. Through policies and purchases. Through what we demand and what we accept. Through whether we treat this as an emergency or a distant concern. Evolution doesn't care which we choose. It'll respond to whatever conditions we create. It'll favor whatever traits prove adaptive in the world we're building. Maybe that world includes humans. Maybe it doesn't. Maybe intelligence remains advantageous. Maybe it becomes a liability. Maybe we're the ancestors of something extraordinary. Maybe we're just another failed experiment. Another branch that couldn't adapt fast enough. Another fossil layer marking a brief moment when one species thought it could outsmart 4 billion years of planetary processes. We won't know the answer for millions of years. But we're determining it now. Part 6 of 6. The story we've been told about comets, the one where they're just icy debris wandering through space, needs updating. Because the data keeps pointing in one direction. These objects aren't random. They're delivery systems. Packages sent from the outer solar system carrying exactly what early Earth needed but couldn't make efficiently on its own. Think about the timing. Earth forms hot. Too hot for organic chemistry. It needs to cool, needs water, needs the building blocks for biochemistry. And right on schedule, here come the comets. Billions of them during the late heavy bombardment. Each one carrying ice, organics, amino acids, phosphorus. Each impact a delivery. Not violent destruction, but violent creation. We've spent decades assuming life started here through local chemistry. Lightning strikes. Volcanic vents. Tidal pools. And maybe some of it did. But the numbers don't work. Early Earth's atmosphere wasn't right for making complex organics in quantity. The Miller-Urey experiment, elegant as it was, used the wrong gases. When you correct for that, the yield drops dramatically. Local production wasn't enough. But comets? They're making organics constantly. In the cold dark between stars. No atmosphere to worry about. No oxygen to interfere. Just carbon, hydrogen, nitrogen, oxygen, and time. Lots of time. These molecules form, accumulate, get locked into ice matrices that protect them. Then they wait. Sometimes for billions of years. Until gravity pulls them inward. Until they slam into young planets. Until they deliver their cargo. What we found on Wild 2 and 67P isn't an accident. It's a pattern. Comets everywhere are doing this. Making the same molecules. Carrying the same building blocks. It's chemistry operating at solar system scale. And Earth was in the path of that delivery route for hundreds of millions of years. The ice itself mattered just as much as what was in it. Early Earth needed water. Vast amounts. Our oceans didn't condense from the primordial atmosphere. They came from outside. From objects that formed in colder regions and then migrated inward. Some from asteroids, yes. But comets contributed. Isotope ratios prove it. Not all our water is cometary, but some is. Enough to matter. So now picture the actual scenario. 4 billion years ago. Earth with thin oceans, no continents yet, active volcanism everywhere. And it's being bombarded constantly. Not planet-killing impacts, but steady, relentless delivery. Each comet brings water, organics, minerals. The ice cushions the impact, protects the cargo. The organics survive, dissolve into the ocean, accumulate. The minerals settle. The carbon compounds concentrate in tidal zones, around vents, in shallow pools. You're not starting with nothing. You're starting with a planet being continuously restocked with prebiotic chemistry. With molecules that already have some complexity. With building blocks ready to assemble into something more sophisticated. The local chemistry, the lightning and vents and UV radiation, they're still happening. But now they're working with better raw materials. They're not creating from scratch. They're refining what's already there. And here's what makes this profound. It means life's origin isn't purely local. It's not Earth solving the problem alone. It's Earth benefiting from processes that happened across the entire solar system. From chemistry in molecular clouds. From reactions in the outer solar system. From delivery mechanisms that operated for hundreds of millions of years. Life's origin is a collaboration between a planet and its cosmic environment. Which raises an obvious question. If this happened here, did it happen elsewhere? Are there other planets, right now, being seeded by comets? Other oceans accumulating organic molecules? Other worlds where chemistry is transitioning toward biology? We don't know. But the statistics suggest yes. Our solar system isn't unique. Comets form around other stars. Planets get bombarded everywhere. The same physical processes, the same chemistry, the same delivery mechanisms. If it worked once, it can work again. Maybe it's working right now on planets we haven't discovered yet. Maybe it's worked countless times on worlds that existed billions of years ago. Maybe we're not the first. Maybe we won't be the last. That doesn't make life inevitable. Chemistry alone doesn't guarantee biology. You need the right conditions, the right timing, the right sequence of events. But it makes life less miraculous, less impossibly unlikely. It shifts the question from, how did life beat astronomical odds? To, given favorable conditions and enough time, how often does chemistry become biology? And that's a different question. One with potentially different answers. Because chemistry is patient. It doesn't care about timescales. It just keeps trying combinations. Keep mixing molecules for 1 billion years and eventually something interesting happens. Not guaranteed, but probable. And probability, given enough opportunities, approaches certainty. We're still missing pieces. We don't know exactly how RNA formed, how membranes and replication combined, how the genetic code got established. Those are hard problems, but they're becoming tractable. Every year, lab experiments get closer to recreating conditions that produce self-replicating systems. Every year, we understand more about what early Earth was actually like. Every year, the gap between non-life and life gets smaller. Comets didn't solve the origin of life. They solved the supply problem. They provided raw materials that early Earth couldn't efficiently produce. They turned an improbable event into something merely unlikely. And on planetary timescales, unlikely events happen constantly. You just need to wait. The evidence keeps accumulating. Not just from comets we've visited, but from meteorites, from interstellar chemistry, from laboratory experiments. All of it pointing toward the same conclusion. The building blocks of life aren't rare. They're common. They form naturally in cold environments. They survive delivery to planetary surfaces. They accumulate. They react. They experiment. What's rare isn't the chemistry. It's the conditions that let chemistry become biology. Stable liquid water. Energy sources. Mineral surfaces for catalysis. Protection from radiation. Enough time without catastrophic disruption. Those conditions are specific. Not impossible, but requiring a particular combination of planetary characteristics. Earth had those characteristics. Maybe other planets do too. Maybe they're common. Maybe they're rare. We're only beginning to survey the possibilities. Only beginning to understand how many Earth-like worlds exist. Only beginning to look for biosignatures, chemical signs that biology is happening somewhere else. The search is underway. Telescopes scanning exoplanet atmospheres for oxygen, methane, combinations that suggest life. Probes examining Europa and Enceladus, moons with subsurface oceans that might harbor biology. Future missions to Venus, Mars, Titan, looking for current life or fossil evidence of past life. Each mission refines our understanding. Each discovery adjusts the probabilities. And those probabilities matter, because they determine whether we're alone or part of something larger. Whether life's origin was a singular miracle or a common occurrence. Whether intelligence is unique to Earth or inevitable given enough time. Whether we're the only species capable of asking these questions or one of many scattered across the galaxy. We don't have those answers yet. But we're closer than we've ever been. Closer to understanding our origins. Closer to knowing whether life elsewhere exists. Closer to determining our place in the universe. Not through philosophy or speculation, but through data. Through chemistry. Through missions that touch these ancient objects and read their composition. Comets are messengers. Not from gods or fate, but from the early solar system. They carry information about conditions 4.5 billion years ago. About chemistry in the outer regions. About what was available when Earth formed. That information is still readable, still preserved in ice that hasn't melted since the solar system's beginning. Every comet we study refines the picture. Every measurement adds detail. Every discovery adjusts our understanding. We're not guessing anymore about what these objects contain. We're measuring it directly. And what we're measuring consistently shows organic complexity. Amino acids. Nucleobases. Phosphorus. Water. Everything life needs. That doesn't prove comets created life. Proof would require showing the mechanism, demonstrating that delivered organics actually assembled into something living. We can't do that. We weren't there. We don't have recordings. We have only evidence, circumstantial but compelling, pointing toward cometary delivery as a crucial part of life's origin. The alternative is that all of this is coincidence. That comets happen to carry exactly the molecules life uses, but contributed nothing. That early Earth independently synthesized everything despite having the wrong atmospheric chemistry. That the timing of heavy bombardment and life's appearance is unrelated. Possible, but increasingly implausible. Science works by eliminating alternatives until only one explanation fits the data. We're not there yet. But we're moving in that direction. Each study, each mission, each experiment narrows the possibilities. And what's emerging is a story where life's origin wasn't purely terrestrial. Where Earth's chemistry was supplemented by cosmic delivery. where our existence depended on objects formed in a cold dark carrying cargo across billions of kilometers. It's a strange story, not the one we expected. But data doesn't care about expectations. It cares about what actually happened. And what appears to have happened is that life's ingredients came from space. Not all of them, but enough to matter. Enough to tip the balance from impossible to merely improbable. Enough to give chemistry the raw materials it needed to begin experimenting with biology. We're the result of that experiment. Not the only possible result, but one that worked. One that survived. One that eventually became capable of looking back and asking where it came from. And now we have an answer, partial but growing more complete. We came from Earth, yes. But Earth came from the solar system. And the solar system provided, through comets, the chemical foundation that made us possible. That foundation is still out there. Still orbiting. Still carrying the same molecules. Still waiting to be studied. Each comet is a time capsule from the solar system's formation. Each one holds clues about conditions back then. About chemistry. About the processes that led to us. We've only examined a handful. Thousands more are accessible. Each one potentially holding new information, new insights, new pieces of the puzzle. The work continues. Missions are being planned to return samples from comets. To land on their surfaces. To drill into their cores and retrieve pristine material that's been frozen since the beginning. Each sample will be analyzed in laboratories with instruments far more sensitive than what existed even a decade ago. Each analysis will reveal more about what comets contain and how those contents relate to biology. We're at the beginning of understanding this connection, not the end. The evidence so far is suggestive, compelling, but incomplete. We need more data, more samples, more experiments, more missions. The story of how comets contributed to life's origin is still being written. But the outline is visible, the general shape is clear. And it's changing how we think about our place in the universe. Because if comets seeded Earth, they're seeding other planets too. If organic delivery is common, then the building blocks of life are widespread. If chemistry can transition to biology given the right conditions, then those conditions might exist elsewhere. The universe might be full of experiments similar to the one that produced us. Some failing, some succeeding, some just beginning, some already billions of years old. We don't know yet, but we're looking. And every year, our tools get better. Our understanding deepens. Our search expands. The question of whether we're alone is becoming answerable. Not through speculation, but through observation. Through detecting biosignatures on distant worlds. Through finding life in our own solar system beyond Earth. Through understanding how common the processes that created us actually are. That understanding starts with comets. With these frozen archives carrying evidence from our beginning. With missions that brave enough to catch up to them, touch them, taste their chemistry. With scientists patient enough to analyze the data, piece together the story, follow wherever the evidence leads. And where it's leading is toward a cosmos more interconnected than we imagined. Where life's origin isn't isolated to individual planets, but involves solar system-wide processes. Where chemistry in one region affects biology in another. Where what happens in the cold outer darkness eventually influences what emerges in the warm inner light. We're part of that story. Products of processes that began before Earth existed. Beneficiaries of delivery systems that operated for hundreds of millions of years. Descendants of chemistry that started in molecular clouds and ended in living cells. The path from there to here was long, improbable, contingent on countless specific events. But it happened. And understanding how it happened changes everything about how we see ourselves and our origins. "40 light-years from Earth, there's a planet that might just be our twin. Scientists call it TRAPPIST-1e, and if you're waiting for the usual disclaimer about how we'll probably never know if it's habitable, you might want to sit down. Because what we've learned about this world in the last few years has fundamentally changed that conversation. This isn't speculation wrapped in maybes. TRAPPIST-1e is 92% the size of Earth, has 82% of our gravity, receives 60% of the sunlight we do, and sits precisely where liquid water could exist on its surface. But here's what makes this discovery different from every other Earth-like planet we've found. We're actually measuring its atmosphere right now. Or at least, we're trying to figure out if it has one, which sounds less exciting until you realize what that really means. The James Webb Space Telescope has already observed this planet 4 times, collecting data that's forcing scientists to completely rethink how we study distant worlds. The readings are confusing, contradictory, and absolutely fascinating. Some signals hint at methane. Others suggest a bare rock with no air at all. And that uncertainty, that's not a failure of science. It's the sound of us standing at the edge of actually knowing something concrete about a world dozens of light years away. Let me put this in perspective. When astronomers discovered the first exoplanet around a sun-like star in 1995, they found a gas giant orbiting closer to its star than Mercury orbits our sun. It was called a hot Jupiter, and it made absolutely no sense based on everything we thought we knew about planetary formation. That discovery won a Nobel Prize because it shattered our assumptions. TRAPPIST-1e isn't shattering assumptions. It's confirming our hopes while simultaneously making everything more complicated. The planet completes one orbit every 6.1 days. That's not a typo. A full year on TRAPPIST-1e lasts less than a week here on Earth. It orbits at a distance of roughly 3% the separation between Earth and the Sun, which sounds absolutely catastrophic for habitability until you learn about the star itself. TRAPPIST-1 isn't like our Sun. It's what astronomers call an ultracool dwarf, with a surface temperature of about 2,500 Kelvin compared to the Sun's 5,800. Its mass is only 9% of the Sun's. Its radius is barely larger than Jupiter's. And here's the part that changes everything about this story. TRAPPIST-1 will shine for 10 trillion years. Not billion. Trillion. That's roughly 700 times longer than the current age of the entire universe. Think about what that means for a moment. Our sun has maybe 5 billion years left before it expands into a red giant and incinerates the inner planets. TRAPPIST-1 is just getting started. It's between 5 and 10 billion years old already, potentially twice the age of our solar system, and it has essentially forever ahead of it. If life emerged on TRAPPIST-1e at the same pace it did on Earth, it could have had billions of additional years to develop before humans even existed. But we're getting ahead of ourselves. First, we need to understand what this world actually looks like, and that's where things get genuinely strange. The star would dominate the sky. From the surface of TRAPPIST-1e, TRAPPIST-1 would appear 4 times larger than the Sun does from Earth, covering an angular diameter of about 2.17 degrees. It would glow a deep orange-red, not the yellow-white of our Sun, because most of its radiation pours out in the infrared spectrum. Stand on this planet and you'd be bathed in perpetual twilight, with visibility extending into wavelengths our eyes can't detect. And you'd never see that star move. TRAPPIST-1e is tidally locked, the same side always facing the star, just like the moon always shows Earth the same face. One hemisphere experiences eternal day, the other, eternal night. The terminator, that boundary between light and dark, would be a ribbon of permanent sunset circling the entire world. This might sound like a death sentence for habitability, and for decades scientists assumed it was. How could life exist on a planet where one side roasts under constant starlight while the other freezes in endless darkness? But climate models have revealed something unexpected. A thick enough atmosphere could redistribute heat from the day side to the night side through powerful atmospheric circulation. Winds would howl across the terminator at speeds that would make Earth's hurricanes look gentle, carrying warmth into the darkness and cooling the scorched hemisphere facing the star. The habitable zone might not be the entire surface. It might be that thin band where day meets night, where temperatures could stabilize somewhere between the extremes. Imagine a world where all life exists in a narrow strip circling the planet, with frozen wastelands on one side and baking deserts on the other. That's not science fiction. That's a legitimate possibility we're actively investigating. Now here's where this story takes a turn that should honestly keep astronomers up at night. TRAPPIST-1e isn't alone. 6 other planets orbit the same star, all of them Earth-sized or close to it, all of them packed so tightly together that the entire system would fit comfortably inside Mercury's orbit around our Sun. The distance between TRAPPIST-1b and TRAPPIST-1c at their closest approach is only twice the distance between Earth and the Moon. From the surface of TRAPPIST-1e, you wouldn't see stars at night. You'd see planets. 6 of them, some appearing larger than our Moon, moving in complex patterns across the sky as they orbit their common star. They wouldn't be distant points of light. They'd be visible disks, recognizable worlds, close enough that you could potentially see surface features with a decent telescope. 3 of these 7 planets, TRAPPIST-1e, F, and G, orbit within the habitable zone. Not 1. 3. This system doesn't just give us a single chance to find life. It gives us multiple opportunities within the same stellar neighborhood, all close enough to study with existing technology. The orbital configuration is almost absurdly precise. The planets exist in what's called a resonant chain, where their orbital periods relate to each other by near-integer ratios. Take one planet's orbital period, divide it by its neighbors, and you get simple fractions like 3 to 2 or 5 to 3. This isn't random. It's the signature of planets that formed together and migrated inward as a group, their gravitational interactions locking them into a cosmic dance that's remained stable for billions of years. That stability matters more than you might think. These planets pull on each other constantly, their gravity creating tidal forces that could generate internal heating, potentially maintaining geological activity long after the planets should have cooled into dead worlds. Active geology means volcanism, which means gases being pumped into the atmosphere, which means a mechanism to replenish air that stellar winds might strip away. And those stellar winds are vicious. TRAPPIST-1 produces frequent flares, 42 detected in just 80 days of observation. Its magnetic field is roughly 600 times stronger than the Sun's. The stellar wind pressure at TRAPPIST-1E's orbit could be 1,000 times greater than what Earth experiences. Over hundreds of millions to billions of years, that wind could strip away atmospheres from the inner planets, including TRAPPIST-1E. So if TRAPPIST-1E has an atmosphere after all this time, after billions of years of bombardment by stellar radiation and powerful winds, that would tell us something profound. It would mean the planet has found a way to hold on to its air, either through a strong magnetic field of its own, or through geological processes that continuously replenish what's lost, or through sheer atmospheric mass that can weather the assault. Which brings us back to the question we're actually trying to answer right now. Does TRAPPIST-1E have an atmosphere at all? The honest answer, based on 4 James Webb observations, is that we don't know. The data suggests 2 equally possible scenarios. Either the planet has a dense, nitrogen-rich atmosphere similar to Earth's, possibly with traces of methane. Or it's a bare rock with no substantial air whatsoever. Both options fit the current observations. Both are consistent with what we know about planetary evolution around ultra-cool dwarfs. And both would teach us something essential about how planets retain or lose their atmospheres over billions of years of stellar violence. But we need more data, and that's exactly what's coming. 15 additional James Webb observations are planned, using an innovative technique that might finally settle the question. The technique involves observing TRAPPIST-1b alongside TRAPPIST-1e during back-to-back transits. TRAPPIST-1b, the innermost planet, is almost certainly a bare rock. It's too close, too hot, too bombarded by stellar radiation to hold on to an atmosphere. When JWST watches TRAPPIST-1b cross in front of the star, any signal detected is purely stellar noise, contamination from the star's own activity rather than atmospheric absorption. Scientists can then use that noise signature as a baseline, a reference point to subtract from TRAPPIST-1E's observations. It's like having a control experiment built into the same stellar system. This approach sidesteps the fundamental problem that's plagued exoplanet atmosphere detection for years. When you're trying to detect the chemical fingerprints of an atmosphere by watching starlight filter through it during a transit, you're measuring incredibly subtle changes. The planet blocks maybe 1% of the star's light at most. The atmosphere, if it exists, absorbs maybe 1/100th of that. You're looking for a signal that's 1 part in 10,000, and the star itself is variable, flickering and flaring in ways that can easily mimic or mask an atmospheric signature. Using TRAPPIST-1b as a reference planet is brilliant because it eliminates the guesswork. Both planets orbit the same star, experience the same stellar activity, and can be observed in quick succession before conditions change significantly. Any difference between their transit spectra has to come from TRAPPIST-1e itself, not from stellar variability. If TRAPPIST-1e has an atmosphere, this method will reveal it. The 15 additional observations should provide enough data to move beyond educated guesses. 4 transits gave us a tantalizing maybe. 19 total transits, combined with the reference planet technique, should give us an answer. Not a perfect answer, not complete atmospheric characterization, but a definitive yes or no on whether air exists around this world 40 light-years away. While we wait for those observations, there's another mission preparing to contribute. Pandora, a small satellite scheduled to launch in early 2026, is specifically designed to study exoplanet atmospheres and their host stars simultaneously. It won't have James Webb sensitivity, but it'll provide continuous long-term monitoring that space telescopes like JWST which must divide their time among thousands of targets, simply cannot match. Pandora will watch TRAPPIST-1 for extended periods, building up detailed profiles of the star's behavior and how it affects observations of the planets. This multi-pronged approach represents how modern astronomy tackles the hardest questions. No single observation definitively answers whether TRAPPIST-1e has an atmosphere. Instead, we build the answer through layers of evidence, each observation constraining the possibilities, each new technique eliminating alternatives until only one explanation remains consistent with all the data. But let's assume the best case. Let's say the upcoming observations confirm that TRAPPIST-1e does have an atmosphere. What would that atmosphere actually be like? Climate models offer some intriguing possibilities. The most likely scenario, if an atmosphere exists, involves a dense nitrogen-rich envelope similar to Earth's but potentially thicker. Nitrogen makes up 78% of Earth's atmosphere, and it's chemically stable, not easily stripped away by stellar winds or lost to space. A nitrogen atmosphere on TRAPPIST-1e would suggest the planet formed with substantial volatile compounds, retained them through billions of years of stellar assault, and maintains geological activity that continues replenishing atmospheric gases. The models also hint at methane, which is where things get really interesting. Methane in Earth's atmosphere comes primarily from biological sources. 90% of atmospheric methane on Earth is produced by life, from bacteria in wetlands to microbes in the guts of animals. The remaining 10% comes from geological processes, volcanic activity, and the breakdown of organic material. Detecting methane on TRAPPIST-1e wouldn't be proof of life. There are plenty of non-biological ways to produce methane. Saturn's moon Titan has an atmosphere rich in methane, and there's no life there. Geological processes can generate methane through reactions between water, rock, and heat deep beneath a planet's surface. But methane's presence would raise the question, and it would raise it loudly. The challenge with methane is stability. In Earth's atmosphere, methane breaks down relatively quickly, destroyed by ultraviolet light and chemical reactions within about a decade. The fact that Earth's atmosphere contains methane despite this constant destruction means something is continuously producing it. The same would be true on TRAPPIST-1e. If we detect methane, something must be generating it faster than processes can remove it. Carbon dioxide is another gas the models consider essential for habitability. Even small amounts, just a fraction of 1%, could provide enough greenhouse warming to keep surface temperatures above freezing. TRAPPIST-1e receives about 60% the stellar flux that Earth receives from the Sun. Without greenhouse gases, the planet would be frozen. With the right amount of carbon dioxide, liquid water becomes possible. The equilibrium temperature calculations place TRAPPIST-1e somewhere between 225 and 246 Kelvin, depending on how much light the planet reflects back into space. That's cold, roughly -48 to -27 degrees Celsius. But those numbers assume no atmosphere and no greenhouse effect. Add a modest atmosphere with some carbon dioxide, and the surface temperature could rise above the freezing point of water. Water is the real question mark. Density measurements suggest TRAPPIST-1e might be slightly less dense than Earth, which could mean it contains more water. Some studies estimate the planet could hold water equivalent to several Earth oceans, possibly as much as 5% of its total mass compared to less than 1% for Earth. If that's accurate, TRAPPIST-1e might not just have oceans. It might be an ocean world, a water planet with a global sea potentially hundreds of kilometers deep, nothing like the continents and ocean basins we're familiar with. Ocean worlds present their own habitability challenges. Too much water and you might lack the rock-water interface where chemistry happens, the shallow seas and tidal zones where life on Earth first emerged. Too much water and plate tectonics might not function properly, eliminating the geological recycling that keeps Earth's carbon cycle running. But too much water doesn't mean uninhabitable. It means different, an environment where life, if it exists, would have to work differently than life on Earth. The tidal locking adds another layer of complexity to any climate model. One side of the planet faces the star permanently, receiving constant illumination. The other side faces eternal darkness. The temperature gradient between these hemispheres would be extreme without an atmosphere to redistribute heat. The day side could be scorching while the night side freezes solid, making both regions uninhabitable. But a thick atmosphere changes everything. Atmospheric circulation, driven by that extreme temperature gradient, would create powerful winds that carry heat from the day side to the night side. Climate models show that even a moderately dense atmosphere could prevent the night side from freezing, maintaining temperatures across the planet within a range where liquid water could exist. The most habitable region might not be the day side or the night side but the terminator, the twilight zone between them. Here, the star hangs perpetually at the horizon, neither rising nor setting, providing constant but moderate illumination. The temperature would be milder than the day side, warmer than the night side. If TRAPPIST-1e has water, the terminator region might host a ring of habitable conditions circling the entire planet. This assumes the atmosphere remains stable, which brings us back to the stellar wind problem. TRAPPIST-1 is magnetically active, producing a stellar wind that could strip away atmospheres over hundreds of millions to billions of years. The fact that TRAPPIST-1e might still have an atmosphere after being between 5 and 10 billion years old suggests something is protecting it. That something could be a magnetic field. Earth's magnetic field, generated by a liquid iron core, deflects the solar wind and prevents our atmosphere from being stripped away. Mars lost most of its atmosphere because its magnetic field shut down billions of years ago, leaving the planet defenseless against the solar wind. If TRAPPIST-1e has maintained a magnetic field for billions of years, it could have held on to its atmosphere despite the stellar bombardment. Or the planet might simply have started with so much atmosphere that even billions of years of stripping haven't removed it all. Or volcanic activity could be continuously replenishing gases faster than they're lost to space. Any of these mechanisms could work. The key point is that if TRAPPIST-1e has an atmosphere now, it survived a hostile environment for an incredibly long time. That survival would tell us something profound about planetary resilience. It would demonstrate that Earth-sized rocky planets can maintain habitable conditions around ultra-cool dwarf stars despite intense stellar activity. And since ultra-cool dwarfs make up the vast majority of stars in the galaxy, that would massively expand the number of potentially habitable worlds in the universe. The evidence for or against an atmosphere comes down to a handful of measurements, each one pushing the limits of what our telescopes can detect. James Webb Space Telescope observations between 2022 and 2024 have given us 4 transits of TRAPPIST-1e, for moments when the planet passed in front of its star and allowed starlight to filter through any atmosphere that might exist. Those observations hint at something, maybe methane in the atmosphere, but the signal is weak and ambiguous. The problem is the star itself. TRAPPIST-1 is magnetically active in ways that make interpretation difficult. The star produces flares, sudden bursts of energy that temporarily change its brightness and spectrum. It has a strong magnetic field averaging around 600 Gauss, possibly higher, driving intense chromospheric activity. During a transit observation, any signal we detect could be coming from the planet's atmosphere or from the star's own atmospheric variations. Separating the two requires extremely precise measurements and sophisticated modeling. Current data suggests that if TRAPPIST-1e has an atmosphere, it's not a puffy hydrogen envelope like a mini-Neptune. Those have been ruled out. What remains possible is a compact atmosphere similar to Earth's, dominated by nitrogen with traces of other gases, or a completely bare rock with no atmosphere at all. We're essentially at 50-50 odds based on existing observations. The most recent analysis in 2025 couldn't confirm an atmosphere with confidence. Scientists examined the 4 transit observations using multiple analysis methods, comparing the observed spectrum against models of various atmospheric compositions. The results were frustratingly inconclusive. Some analysis methods favored a thin atmosphere. Others favored bare rock. The differences between models fell within the margin of measurement error. What this tells us is that TRAPPIST-1E's atmosphere, if it exists, is subtle enough that we're operating right at the edge of detection capability. We need more data, which is exactly what's coming. A new observing program approved for James Webb involves 15 additional transits of both TRAPPIST-1E and its neighboring planet TRAPPIST-1b. This program uses an innovative strategy. TRAPPIST-1b, the innermost planet, orbits so close to the star that any atmosphere it once had is almost certainly gone, stripped away by stellar radiation and wind. It's likely a bare rock. By observing TRAPPIST-1b and TRAPPIST-1e back-to-back during the same observing sessions, scientists can use TRAPPIST-1b as a reference. Any signal detected during the TRAPPIST-1b transit must be coming from the star, not the planet. That signal can then be subtracted from the TRAPPIST-1e observations, removing stellar contamination and revealing what, if anything, is genuinely coming from TRAPPIST-1e's atmosphere. This technique represents a breakthrough in exoplanet characterization. For years, stellar activity has been one of the biggest obstacles to studying small rocky planets around active stars. Red dwarfs like TRAPPIST-1 are magnetically turbulent, and their variability can mimic or mask atmospheric signals. Using a neighboring bare rock planet as a calibrator bypasses this problem, turning a limitation into a tool. If TRAPPIST-1e has an atmosphere, these observations should finally detect it. If it doesn't, we'll know that too. Either answer changes what we understand about planetary habitability around ultra-cool dwarfs. Beyond James Webb, another mission is targeting TRAPPIST-1e specifically. NASA's Pandora satellite, scheduled to launch in early 2026, is designed to study exoplanet atmospheres and their host stars simultaneously. Pandora won't have the raw sensitivity of James Webb, but it will observe TRAPPIST-1e repeatedly over extended periods, building up a dataset that captures how the star's activity varies over time. By correlating those variations with transit observations, Pandora can help disentangle stellar noise from planetary signals. The satellite represents a new approach, using long-term monitoring rather than individual deep observations to characterize small rocky worlds around variable stars. What would it mean if TRAPPIST-1e has an atmosphere? First, it would confirm that Earth-sized planets can retain atmospheres around ultra-cool dwarf stars despite billions of years of stellar bombardment. That's not guaranteed. TRAPPIST-1 has been magnetically active for its entire lifetime, producing flares and coronal mass ejections that blast the inner planets with radiation and charged particles. The stellar wind pressure at TRAPPIST-1e's orbit may be 1,000 times stronger than the solar wind at Earth's orbit. Under those conditions, atmospheric loss should be rapid. Yet if TRAPPIST-1e still has an atmosphere after 5 to 10 billion years, something has protected it. The most likely protection is a magnetic field. Earth's magnetic field, generated by convection in its liquid iron core, deflects the solar wind and prevents atmospheric stripping. Mars lost most of its atmosphere because its core cooled and its magnetic field shut down, leaving the planet exposed. If TRAPPIST-1e has maintained an active magnetic dynamo for billions of years, it could have shielded its atmosphere from the worst of the stellar assault. That would require a hot interior, kept warm by radioactive decay and possibly tidal heating from gravitational interactions with the other planets in the system. TRAPPIST-1e orbits in resonance with its neighbors, meaning they exert periodic gravitational tugs that flex the planet's interior, generating heat through friction. That heat could drive volcanism, which would replenish atmospheric gases even as they're stripped away by the stellar wind. The alternative is that TRAPPIST-1e started with so much atmosphere that it hasn't lost it all yet. Imagine a planet that formed with a thick volatile-rich envelope, hundreds or thousands of times the atmospheric mass of Earth. Even billions of years of stripping might leave a substantial atmosphere remaining. This scenario is plausible for planets that formed farther out in the system and migrated inward, carrying volatiles with them from colder regions. Evidence suggests all 7 TRAPPIST-1 planets migrated together as a resonant chain, moving inward from their formation locations. During that migration, they could have accumulated significant amounts of water and other volatiles. If TRAPPIST-1e has retained an atmosphere, the composition matters as much as the presence. An atmosphere dominated by carbon dioxide would create a greenhouse effect, warming the surface above the equilibrium temperature and potentially maintaining liquid water even with lower stellar flux. Models show that as little as 0.2 bars of CO2, about a fifth of Earth's atmospheric pressure, could be enough to keep TRAPPIST-1e's surface above freezing. With more CO2, 5 bars or 10 bars, the planet could be significantly warmer, possibly too warm for life as we know it but still within the range of habitability for extremophiles. An atmosphere with nitrogen and oxygen would be even more interesting. Oxygen in particular is a biosignature, a gas that doesn't persist in planetary atmospheres without continuous replenishment by life. On Earth, oxygen makes up 21% of the atmosphere because photosynthetic organisms continuously produce it. Without life, Earth's oxygen would disappear within a few million years, consumed by chemical reactions with rocks and gases. If we detected significant oxygen in TRAPPIST-1e's atmosphere, it would be one of the strongest hints of life we could find without actually going there. That's why the search for atmospheric oxygen on rocky exoplanets is such a high priority. It's not definitive proof of life, but it's close. Methane is another biosignature, though less definitive than oxygen. Methane can be produced by geological processes, especially volcanism, but it can also be produced by microbial life. On Earth, most methane in the atmosphere comes from biological sources, primarily methanogenic bacteria. If TRAPPIST-1e has both methane and oxygen in its atmosphere simultaneously, that would be a powerful biosignature combination. Methane and oxygen react with each other and don't coexist in equilibrium. Finding both together would suggest active replenishment by life. The tentative hints of methane in early James Webb observations are intriguing for this reason, though as noted, those hints might be stellar contamination rather than genuine planetary signals. Climate models for TRAPPIST-1e explore a wide range of atmospheric compositions and surface conditions. The TRAPPIST-1 Habitable Atmosphere Intercomparison Project, known as TEACH-AI, brings together multiple climate modeling groups to simulate different scenarios. These models test what happens with varying amounts of CO2, different surface types, ocean coverage, cloud behavior, and atmospheric circulation patterns. Results consistently show that TRAPPIST-1e could maintain surface temperatures above freezing with relatively modest greenhouse warming. The planet's equilibrium temperature without an atmosphere ranges from 225 to 246 Kelvin depending on albedo, well below freezing. But with even a thin atmosphere containing greenhouse gases, surface temperatures rise into the habitable range. The terminator region, the boundary between the day and night sides, emerges as particularly interesting in these models. On a tidally locked planet, the terminator experiences perpetual twilight. The star hangs at the horizon, neither rising nor setting. temperature gradients are moderate compared to the extreme heat of the day side and extreme cold of the night side. If TRAPPIST-1e has surface water, the terminator might host a habitable ring circling the entire planet, a zone where temperatures and light levels remain stable enough for liquid water and potentially life. These models assume the atmosphere circulates efficiently enough to redistribute heat. That's not guaranteed on a tidally locked world. Atmospheric circulation depends on the temperature difference between the day and night sides, the planet's rotation rate, and the atmosphere's thickness and composition. Weak atmospheric circulation could create a situation where the day side overheats while the night side freezes, leaving no stable temperate zone. Strong circulation, driven by powerful winds and weather systems, could smooth out temperature extremes and create habitable conditions across much of the planet's surface. The specific outcome depends on variables we can't yet measure from 40 light-years away. Tidal locking creates another unusual feature worth considering. On Earth, day and night alternate as the planet rotates. Life evolved with circadian rhythms tied to this cycle. Plants photosynthesize during the day and respire at night. Animals have sleep-wake cycles synchronized to the day-night pattern. On TRAPPIST-1e, there is no day-night cycle. The day side experiences permanent day. The night side experiences permanent night. The terminator experiences perpetual twilight. How would life adapt to such conditions? On the day side, organisms would need protection from constant exposure to starlight and heat. Deep shade might not exist anywhere. Water evaporation would be relentless. On the night side, organisms would need to function in permanent darkness and cold. Energy sources would be limited to chemical processes or geothermal heat rather than photosynthesis. At the terminator, the environment might be most Earth-like, with moderate temperatures and dim but constant light levels. If photosynthesis occurred, it would be optimized for low light levels and the infrared heavy spectrum of TRAPPIST-1's radiation. Plants might appear black rather than green, absorbing as much of the available light as possible across all wavelengths. These speculations assume TRAPPIST-1e has liquid water and an atmosphere capable of supporting life. That remains uncertain. The gravity on TRAPPIST-1e deserves attention. At 82% of Earth's gravity, the difference would be noticeable but not extreme. You'd feel lighter, able to jump higher and carry heavier loads with less effort. Water would flow slightly differently. Rain would fall more slowly. The lower gravity affects how atmospheres behave and how geological processes operate. A thinner crust might be more prone to volcanic activity. Volcanic outgassing could be crucial for maintaining an atmosphere over billions of years, especially if stellar winds constantly strip atmospheric gases away. Active volcanism releases carbon dioxide, water vapor, sulfur compounds, and other gases that replenish atmospheric losses. Earth's atmosphere would have been stripped away long ago without volcanic replenishment. TRAPPIST-1e might depend on the same process. Plate tectonics could also play a role. On Earth, plate tectonics recycles carbon between the atmosphere and the interior, regulating climate over geological timescales. This carbon cycle acts as a planetary thermostat. Too much CO2 causes warming, which accelerates weathering of rocks, which pulls CO2 out of the atmosphere and locks it into minerals. Too little CO2 causes cooling, which slows weathering, allowing volcanic outgassing to build CO2 back up. Whether TRAPPIST-1e has plate tectonics is unknown. The planet's size and internal heat suggest it might. The gravitational interactions with neighboring planets could generate tidal heating, keeping the interior molten and geologically active. These tidal forces arise because TRAPPIST-1e orbits in a resonant chain with the other planets. Their gravitational tugs flex the planet's interior, generating heat through friction. The same process keeps Jupiter's moon Io volcanically active despite its small size and great distance from the Sun. For TRAPPIST-1e, tidal heating could be an additional energy source beyond stellar radiation, potentially warming the planet from within and driving geological activity that supports habitability. The resonant orbital configuration of the TRAPPIST-1 system is remarkable. The 7 planets orbit in near-perfect integer ratios. If you measured the time it takes each planet to complete one orbit and compared them, you'd find patterns like 3 to 2 or 5 to 3. This isn't coincidence. It's a sign the planets migrated inward together from farther out in the protoplanetary disk, locking into gravitational resonances as they moved. These resonances stabilize the system, preventing collisions despite the planet's close proximity. The orbital periods range from 1.5 days for the innermost planet to just 19 days for the outermost. All 7 planets orbit closer to their star than Mercury orbits the Sun. The entire system would fit comfortably inside Mercury's orbit with room to spare. From TRAPPIST-1e's surface, the other planets would be visible to the naked eye, not as points of light but as distinct disks. Some would appear larger than the Moon appears from Earth. You could watch them move across the sky in real time, their positions shifting noticeably over the course of hours. The sky would be crowded with worlds, each one a nearby neighbor in a tightly packed planetary family. This proximity creates another factor affecting habitability. The planets exchange material. Asteroid impacts on one planet could eject rocks into space that eventually land on another planet, carrying microbes if they exist. This process, called panspermia, could spread life throughout the system if it emerged on any one planet. The close spacing makes interplanetary travel of biological material much more likely than in our solar system. Life on TRAPPIST-1e might have originated on TRAPPIST-1d or TRAPPIST-1f and migrated via meteorite impact. Or life on TRAPPIST-1e could seed the other habitable zone planets. The system could host multiple biospheres descended from a common origin. Studying TRAPPIST-1 forces us to reconsider what habitable means. Earth-like conditions are one possibility, but not the only one. TRAPPIST-1e receives less light than Earth, experiences tidal locking, orbits an active flare star, and might have a completely different atmospheric composition and water inventory than our planet. Yet it could still be habitable. Life might thrive in conditions we'd consider marginal or even hostile. The Terminator Zone offers one habitat. Subsurface oceans insulated from surface extremes offer another. Volcanic vents provide energy for chemosynthetic ecosystems independent of starlight. Life is adaptable. The question isn't whether TRAPPIST-1e is identical to Earth, but whether it provides the basic ingredients, liquid water, energy sources, and stable conditions over long timescales. Current evidence suggests it might. The age of the system is important here. TRAPPIST-1 is between 5.5 and 9.5 billion years old, potentially twice the age of our solar system. If TRAPPIST-1e has been habitable for even a fraction of that time, life there has had far longer to evolve than life on Earth. Earth's biosphere is 4 billion years old. Multicellular life emerged less than 1 billion years ago. Complex animals appeared only in the last 600 million years. If TRAPPIST-1e has had stable habitable conditions for 8 billion years, what might have evolved there? Single-celled organisms certainly. But beyond that, we can only speculate. Intelligence might have emerged and gone extinct multiple times over such vast timescales. Or life might remain microbial, filling ecological niches but never developing complexity. The longer timescale doesn't guarantee complexity, but it allows more opportunities for evolutionary experiments. Earth's history shows mass extinctions reset the trajectory of life repeatedly. A similar pattern might occur on TRAPPIST-1e, with stellar flares causing periodic atmospheric stripping events that stress or eliminate surface life while subsurface ecosystems survive. The star itself provides both opportunity and challenge. TRAPPIST-1 will shine for 10 trillion years, 700 times longer than the current age of the universe. It's barely begun its lifespan. The Sun, by contrast, will exhaust its hydrogen fuel and leave the main sequence in about 5 billion years, rendering Earth uninhabitable long before it dies. TRAPPIST-1e has time. More time than any planet in our solar system will ever have. That longevity means the search for life on TRAPPIST-1e isn't just about finding life as it exists now, but understanding whether life can emerge, persist, and evolve over timescales that dwarf anything we've experienced. The implications extend beyond biology. Understanding how life emerges and evolves in one environment versus another tells us something fundamental about the universe itself. Is Earth's path typical or exceptional? The answer matters. If TRAPPIST-1e developed life independently, convergent evolution becomes testable. Do separate biospheres produce similar solutions to similar problems? Does DNA emerge inevitably, or was that molecular choice arbitrary? If we found life on TRAPPIST-1e that used different information storage molecules, different energy pathways, different cellular architectures, it would prove life's flexibility exceeds our current models. But there's a darker possibility. TRAPPIST-1e might be sterile. Not because it lacks water or energy, but because stellar flares sterilize the surface repeatedly. Each major flare strips away atmospheric layers, bombards the surface with radiation, resets any progress toward complexity. Life might emerge during quiet periods only to be extinguished during active phases. The cycle could repeat endlessly. Single-celled organisms might evolve, thrive briefly, then vanish when the next flare hits. The planet becomes a biological treadmill where complexity never gains traction. This scenario isn't speculation. We know TRAPPIST-1 produces 42 flares every 80 days based on Kepler observations. Large, complex flares capable of altering planetary atmospheres significantly. The star's magnetic field averages 600 Gauss, though that might be underestimated. Magnetic activity drives chromospheric chaos. Coronal mass ejections might be trapped by the field, concentrating their energy near the planets. The stellar wind pressure could be 1,000 times stronger than what Earth experiences from the Sun. That wind could strip atmospheres from planets up to TRAPPIST-1f over timescales ranging from 100 million to 10 billion years. Yet TRAPPIST-1e has survived for billions of years already. If it has an atmosphere now, something is replenishing what the star strips away. Volcanic outgassing is the obvious candidate. Tidal heating from gravitational interactions with neighboring planets could drive intense geological activity. The planet might possess a partially molten interior that continually releases gases to the surface. Volcanic vents would pump water vapor, carbon dioxide, sulfur compounds into the atmosphere faster than stellar wind removes them. The balance between loss and replenishment determines whether a stable atmosphere persists. This creates a tension. Volcanic activity provides atmospheric replenishment but also surface hazards. Frequent eruptions reshape landscapes, bury ecosystems under lava flows, inject ash into the atmosphere that blocks light and cools the climate temporarily. Life would need to adapt to geological instability as well as stellar instability. Organisms might evolve rapid dispersal mechanisms, spreading across the planet quickly after each catastrophe. Or they might retreat underground during surface upheavals, emerging when conditions stabilize. Subsurface life becomes more attractive in this context. The planet's density offers clues about internal structure. At 5.65 grams per cubic centimeter, TRAPPIST-1e is slightly denser than Earth. That implies a similar composition: iron core, silicate mantle, rocky crust. But the exact ratios might differ. TRAPPIST-1 planets are about 8% less dense than expected if they matched Earth's composition precisely. They might contain more water locked in minerals, or different iron-to-silicate ratios. These differences affect heat transport, magnetic field generation, tectonic activity. A planet without plate tectonics might lack the recycling mechanisms that stabilize Earth's climate over geological time. Or it might develop alternative stabilization through different feedback loops. Water inventory matters enormously. Climate models show TRAPPIST-1e could retain water equivalent to several Earth oceans. That water might exist as ice beneath the surface, liquid oceans covering the planet, or atmospheric vapor cycling between day and night sides. A water world with global oceans hundreds of kilometers deep creates radically different conditions than Earth. No exposed land means no weathering cycles that regulate atmospheric carbon dioxide. Ocean chemistry becomes the dominant climate regulator. Deep oceans might develop layered structures with different temperatures, pressures, chemistries at various depths. Life could occupy multiple ecological zones vertically as well as horizontally. But here's what makes TRAPPIST-1e particularly fascinating from a habitability perspective: the terminator zone. This narrow band between permanent day and permanent night might host the most stable conditions on the planet. Not too hot, not too cold. Stellar radiation arrives at an angle rather than directly overhead, reducing intensity without eliminating it entirely. Atmospheric circulation would concentrate here, redistributing heat from the day side and moisture from the night side. If liquid water exists anywhere on the surface, the terminator is the most likely location. Standing in the terminator zone, you'd see the star perpetually near the horizon, never rising or setting. The sky would glow orange-red where the star sits, fading to deep twilight overhead, and complete darkness toward the night side. Weather patterns would be unlike anything on Earth. Winds would howl constantly as hot air from the day side rushes toward the cold night side. Clouds might form and dissipate in minutes as moisture cycles through the narrow habitable band. Rain could fall continuously in some regions, while others remain perpetually dry. The ground might be warm from internal heat but never scorching from direct starlight. This environment selects for specific adaptations. Plants, if they exist, would grow horizontally toward the light source rather than vertically. They'd need to tolerate low light levels and produce pigments tuned to infrared rather than visible wavelengths. Animals would navigate by the star's position, using it as a permanent compass. Circadian rhythms wouldn't exist in the traditional sense. Life cycles might key to stellar flares instead, with organisms timing reproduction or dormancy to avoid peak radiation events. The possibility of photosynthesis on TRAPPIST-1e remains uncertain. Infrared light carries less energy per photon than visible light. Organisms would need to capture more photons to generate the same energy output. This might favor larger light-gathering structures or different photosynthetic pathways altogether. Earth's photosynthesis uses chlorophyll, which absorbs red and blue light while reflecting green. TRAPPIST-1e's photosynthesizers might absorb infrared and near-red, appearing nearly black to human eyes. Forests would look dark and alien, absorbing almost all incoming light. But photosynthesis isn't the only energy pathway. Chemosynthesis, the process used by organisms near Earth's deep-sea vents, works independently of light. These organisms extract energy from chemical reactions involving hydrogen sulfide, methane, or iron compounds. TRAPPIST-1E's volcanic activity could support extensive chemosynthetic ecosystems. Life might thrive in darkness, feeding on volcanic emissions. Surface organisms could use photosynthesis during quiet periods while subsurface organisms maintain continuity through chemosynthesis regardless of surface conditions. The question of atmospheric composition remains unresolved. James Webb observations have given us 4 transits worth of data. Not enough to definitively confirm or rule out an atmosphere. The most recent analysis in 2025 couldn't conclude with confidence either way, though it ruled out certain scenarios. A cloud-free hydrogen-dominated atmosphere doesn't exist. If TRAPPIST-1E has air, it's more compact, more like terrestrial planets than gas giants. 2 scenarios remain viable. First, a nitrogen-dominated atmosphere similar to Earth's, possibly with traces of methane. Second, a bare rocky surface with no substantial atmosphere. The data currently supports both equally. We need more observations. NASA's Pandora mission, scheduled to launch in early 2026, should help. This small satellite is designed specifically to characterize exoplanet atmospheres and their host stars. Pandora will observe multiple transits of TRAPPIST-1 planets, building a more complete dataset. There's also a new JWST observing program underway. 15 additional observations targeting TRAPPIST-1E and its neighbor TRAPPIST-1b. The strategy is clever. TRAPPIST-1b is believed to be a bare rock with no atmosphere. By observing back-to-back transits of both planets, scientists can use TRAPPIST-1b's signal as a reference. The star's activity affects both planets identically. Any difference between their signals must come from TRAPPIST-1E's atmosphere if it exists. This technique, using one planet to correct for stellar contamination of another, represents a breakthrough in exoplanet characterization. The challenge stems from stellar activity itself. Red dwarfs like TRAPPIST-1 are magnetically active. Their surface is royal with star spots, flares, and convection cells. These features create noise in the data that mimics atmospheric signals. Separating planet from star requires precision measurements repeated many times. Each transit provides one data point. 4 transits aren't enough to average out stellar noise. 15 might be. 30 would be better. What we learn from TRAPPIST-1E will inform searches for life on other planets. If we detect an atmosphere, we'll know that planets around red dwarfs can retain air despite stellar activity. That expands the habitable zone of the galaxy significantly. Red dwarfs outnumber Sun-like stars 10 to 1. If their planets can host life, the number of potentially habitable worlds increases dramatically. If TRAPPIST-1E lacks an atmosphere, we'll know that stellar activity strips air from close-orbiting planets, limiting habitability to more distant orbits or different stellar types. Either answer matters. Negative results constrain possibilities as much as positive results expand them. Science progresses through elimination as well as discovery. The bigger question isn't just about TRAPPIST-1E. It's about what this planet represents in the search for life beyond Earth. We've spent decades looking at stars like our Sun, yellow dwarfs with stable outputs and well-behaved temperaments. But those stars make up only a fraction of the galaxy. Red dwarfs outnumber them 10 to 1. If planets around red dwarfs can host life, the number of potentially habitable worlds explodes. TRAPPIST-1E forces us to confront assumptions we didn't know we were making. We assumed habitable planets need Earth-like orbits, Earth-like day lengths, Earth-like stellar radiation. TRAPPIST-1e challenges every one of those assumptions. It orbits once every 6 days. It's tidally locked. It receives predominantly infrared radiation. Yet it might still harbor life. The implications extend beyond biology. They touch on planetary formation, atmospheric evolution, the limits of habitability. If TRAPPIST-1e has retained an atmosphere after billions of years of stellar bombardment, that tells us something profound about atmospheric retention mechanisms. Volcanic outgassing might replenish losses. Magnetic fields might shield against stellar wind. Gravitational interactions with sibling planets might generate internal heat that drives geological activity. The system's age matters here. TRAPPIST-1 is between 5 and 10 billion years old, potentially twice Earth's age. Life on Earth appeared relatively quickly once conditions stabilized, within a few 100 million years. If similar processes occurred on TRAPPIST-1e, life there could have billions of years head start. Not millions. Billions. That's enough time for remarkable complexity to develop. Earth went from single cells to multicellular organisms in about 2 billion years. From multicellular life to intelligence took another 1.5 billion. If TRAPPIST-1e followed similar timelines but started earlier, we might be looking at a world with life far more developed than anything on Earth. Or we might be looking at a barren rock. That's the frustrating beauty of science at this scale. We don't know yet. Can't know until we gather more data. The universe doesn't reveal its secrets on our schedule. The orbital dynamics of the TRAPPIST-1 system add another layer of intrigue. All 7 planets are locked in resonant chains, their orbital periods related by simple integer ratios. This configuration isn't random. It's evidence of orbital migration, planets moving inward from their formation positions, shepherding each other into stable resonances. This process takes time, requires specific conditions. The fact that all 7 planets maintain this configuration suggests the system has been dynamically stable for billions of years. That stability matters for habitability. Planets need time. Time for atmospheres to develop, for water to accumulate, for chemistry to explore the space of possible reactions. Chaotic systems don't provide that time. Planets get ejected, orbits destabilize, collisions occur. TRAPPIST-1's resonant chain indicates none of that has happened. These worlds have maintained their positions, their relationships, their environmental conditions for geological timescales. The resonances also generate tidal heating. As planets pull on each other gravitationally, their orbits shift slightly. These shifts flex the planet's interiors, generating heat through friction. Jupiter's moon Io experiences extreme tidal heating, enough to make it the most volcanically active body in the solar system. TRAPPIST-1e experiences similar forces, though to what degree remains uncertain. Tidal heating could provide an additional energy source beyond stellar radiation, potentially supporting life even if surface conditions seem marginal. Standing on TRAPPIST-1e would be unlike standing anywhere in our solar system. The sky would be dominated by an orange-red star 4 times wider than our Sun appears from Earth. That star wouldn't move. It would hang fixed above the horizon, unchanging. No sunrises, no sunsets. Just perpetual twilight on one hemisphere and eternal darkness on the other. But you wouldn't be alone in the sky. 6 other worlds would be visible, some appearing larger than our moon. They wouldn't be distant points of light like planets appear from Earth. They'd be disks, showing features, moving in complex patterns as they orbit. You could watch TRAPPIST-1F drift across the sky over the course of days. TRAPPIST-1G would move more slowly, taking weeks to cross from horizon to horizon. The inner planets would zip past, completing their journeys in hours. This celestial ballet would be more than scenic. It would have practical implications for any life that developed there. Tidal forces from neighboring planets would create stress patterns in the crust. Earthquakes might synchronize with planetary conjunctions when multiple worlds align. Ocean tides, if oceans exist, would respond not just to the star but to gravitational pulls from multiple sources. Life would need to adapt to these rhythms or exploit them. The question of TRAPPIST-1E's composition remains partially open. Density measurements suggest an Earth-like mix of iron, rock, and possibly water. But the planet is about 8% less dense than it would be with Earth's exact composition. That difference could mean more water, less iron, different mineral ratios. Small differences in composition lead to large differences in geology, atmospheric chemistry, habitability. Water content matters enormously. Too little and you have a dry Mars-like world with limited capacity to support life. Too much and you get a water world with oceans hundreds of kilometers deep, no exposed land, potentially different chemistry at crushing depths. Earth sits in a sweet spot with about 0.02% of its mass as surface water. TRAPPIST-1E might contain several Earth oceans worth of water. Whether that water resides on the surface, in the mantle, or was lost to space billions of years ago remains unknown. The TRAPPIST-1 system gives us 7 laboratories to study planetary evolution under similar conditions. Each planet formed from the same protoplanetary disk, experienced similar early bombardment, aged under the same stellar environment. Yet they differ in distance from the star, in their interactions with each other, potentially in their atmospheres and surface conditions. Comparing them reveals which factors matter most for habitability. TRAPPIST-1b, the innermost planet, is almost certainly too hot. TRAPPIST-1c and d receive too much radiation for comfort. TRAPPIST-1h, the outermost, probably too cold. That leaves E, F, and G in the habitable zone, with E appearing most favorable. But appearances can deceive. We need data, not assumptions. The atmospheric question will likely be resolved within the next few years. 15 more JWST observations are planned. Pandora launches in 2026. Other missions are in development. Each observation adds information, constrains the possibilities, narrows the uncertainty. Eventually we'll know whether TRAPPIST-1E has air or not. And if it does, we'll start characterizing what that air contains. Detection of oxygen would be provocative. On Earth, free oxygen exists because of photosynthesis. Without life constantly producing it, atmospheric oxygen reacts with rocks and disappears. Finding oxygen on TRAPPIST-1E would suggest either life or exotic geological processes we haven't encountered. Either answer would be significant. Methane would be similarly interesting. Methane breaks down quickly under stellar UV radiation. Its presence implies ongoing production, either biological or geological. Combined with other gases, methane signatures could point toward active ecosystems or active geology. Context matters. A planet with methane and oxygen together would be different from a planet with methane alone. But absence of biosignatures wouldn't mean absence of life. Early Earth had life for billions of years before oxygen accumulated. Microbial ecosystems can thrive without producing atmospheric signatures we can detect from 40 light-years away. Non-detection doesn't equal non-existence. It just means we need closer looks, better better instruments, more creative thinking about what signatures to search for. The search for life extends beyond atmospheric chemistry. Future telescopes might detect surface features that suggest biology. Seasonal changes in surface coloration could indicate vegetation growth cycles. Anomalous surface chemistry might point toward biological processing of materials. Even simple things like unusual distributions of trace elements could hint at biological concentration mechanisms. TRAPPIST-1e represents a test case for the broader question of life in the universe. If we find life there, we'll know life isn't rare, isn't confined to Earth-like planets orbiting Sun-like stars. If we don't find life despite favorable conditions, we'll learn something equally important about what factors matter most for life's emergence. The planet exists 40 light-years away. Not 40 million. 40. That's close enough to study in detail with current technology. Close enough to imagine sending probes to, someday, with technologies that don't exist yet. Close enough to feel real rather than abstract. We're living through the first era in human history when we can study individual planets around other stars, characterize their atmospheres, assess their habitability. Our grandparents didn't know planets existed beyond our solar system. We know of thousands and can study the most interesting in detail. The pace of discovery is extraordinary. TRAPPIST-1e might have life. It might not. We don't know yet, can't know until we gather more evidence. But the fact that we can ask the question, that we have tools capable of answering it, that we've found a world where the answer matters, that alone is remarkable. That's where we are now. 40 light-years from a planet that might rewrite our understanding of life's place in the cosmos. Just waiting for more data to arrive. So what happens next? The answer is both frustratingly simple and maddeningly complex. We wait. But that waiting isn't passive. It's active observation, careful analysis, building datasets that will eventually answer whether TRAPPIST-1e has an atmosphere or not. The 15 additional JWST observations represent humanity's best current effort to pierce through 40 light-years of space and determine if air exists around this world. Using TRAPPIST-1b as a reference planet is clever enough that it might actually work. Subtract stellar noise from both signals, see what remains. If something remains in TRAPPIST-1e's data but not TRAPPIST-1b's, that's atmosphere. If both planets show identical signals, that's bare rock. Pandora launching in 2026 adds another tool. Long-term monitoring fills gaps that individual deep observations can't address. Stellar variability averaged over months or years reveals patterns that single transits miss. Combined datasets from multiple instruments, multiple observing strategies, multiple analysis methods will eventually converge on an answer. Maybe not the answer we want, but an answer grounded in evidence rather than hope. The broader implications extend far beyond one planet. If TRAPPIST-1e has retained an atmosphere after billions of years orbiting an active red dwarf, that fundamentally changes habitability calculations for the galaxy. Red dwarfs outnumber Sun-like stars dramatically. They comprise roughly 70% of all stars in the Milky Way. Most of those red dwarfs host planets. If those planets can maintain atmospheres and support life despite stellar activity, the number of potentially habitable worlds increases by orders of magnitude. We're not just studying TRAPPIST-1e. We're studying whether the most common type of planetary system in the galaxy can host life. That's why this matters. That's why 15 telescope observations of one planet justify the time and resources. The answer scales up to billions of worlds. And if TRAPPIST-1e lacks an atmosphere, that answer matters too. It tells us stellar activity wins, that close-orbiting planets around red dwarfs can't hold on to air long enough for life to develop. It narrows the habitable zone of the galaxy, focuses future searches on different stellar types or more distant orbits. Negative results constrain the search space as effectively as positive results expand it. The age of the system keeps pulling me back. Between 5 and 10 billion years old. Twice Earth's age potentially. Life on Earth appeared within a few 100 million years once conditions stabilized. Intelligence took billions of years after that. If TRAPPIST-1e has been habitable for 8 billion years, and if life emerged there at similar pace to Earth, we might be looking at a biosphere with billions of years developmental head start on ours. Not millions of years. Billions. That thought experiment requires massive assumptions. It assumes life emerges readily given the right conditions. It assumes evolutionary paths toward complexity are inevitable rather than contingent. It assumes TRAPPIST-1e has remained habitable continuously rather than experiencing sterilizing events. Each assumption might be wrong. Probably some are wrong. But the possibility remains. We don't know enough yet to rule it out. The view from that world's surface would be extraordinary. 6 sibling planets visible in the sky, some appearing larger than our moon. The star hanging fixed at the horizon, glowing orange-red, never moving. The Terminator zone where you'd stand, experiencing perpetual twilight, watching worlds drift overhead in complex orbital patterns. Weather systems howling as hot dayside air rushes toward the frozen night side. Volcanic vents perhaps, releasing gases that feed chemosynthetic ecosystems in the darkness. These aren't fantasies. They're possibilities grounded in physics and observation. We know the planet exists. We know its size, mass, density, orbit. We know the star's properties, the system's architecture, the gravitational interactions between planets. What we don't know is whether those conditions add up to habitability. That's what the observations are for. The frustrating part is timescale. Science doesn't work on demand. Observations take time to schedule, execute, analyze. JWST is oversubscribed by factors of 5 to 10. Every observation of TRAPPIST-1e means something else doesn't get observed. Priorities compete. Time allocates slowly. The 15 additional observations will happen over months or years, not weeks. Pandora won't launch until 2026, won't produce results immediately after launch. We're talking years before definitive answers arrive. But definitive answers will arrive. That's the difference between now and 20 years ago. 20 years ago, we could barely detect planets around other stars, let alone characterize them. Now we're measuring atmospheric composition of Earth-sized worlds 40 light-years away. The technology exists. The questions are answerable. We just need patience and data. TRAPPIST-1e forces us to expand our definition of habitable. Earth-like conditions are one path to life, but maybe not the only path. Tidal locking doesn't automatically disqualify a world. Heavy stellar activity doesn't automatically sterilize it. Lower stellar flux doesn't automatically freeze it. The universe is larger and stranger than our Earth-centered intuitions suggest. Life might thrive in conditions we consider marginal or hostile. That possibility matters philosophically as much as scientifically. Are we alone? The question has haunted humans for millennia. TRAPPIST-1e won't definitively answer that question, not by itself. But it will narrow the uncertainty. If we find an atmosphere, especially one with biosignatures, the probability of life existing elsewhere increases dramatically. If we find bare rock on a planet that should be habitable, that constrains where and how life can emerge. Either answer moves us forward. Either answer provides information we don't currently have. That's the value of the search itself, not just potential discoveries. Every observation, every measurement, every analysis adds to collective knowledge about how planets work, how atmospheres evolve, how life might emerge or fail to emerge given specific conditions. The TRAPPIST-1 system gives us 7 test cases. 7 planets that formed together, evolved under similar conditions, but differ in their distances from the star and their interactions with each other. Comparative planetology at its finest. We can study how location in the habitable zone affects outcomes, how planetary mass influences atmospheric retention, how tidal forces impact geology. Each planet teaches something about planetary science generally, not just about individual worlds. And TRAPPIST-1e sits right in the middle of that habitable zone. Not too close, not too far. Similar size to Earth. Similar density. Similar gravity. If any planet in the system has held on to an atmosphere and maintained habitable conditions, TRAPPIST-1e is the best bet. That's why it's the focus. That's why 15 JWST observations target it specifically. The stakes feel high because they are high. This isn't just academic curiosity. It's foundational questions about life's place in the universe. Are Earth and humanity unique? Or are we common, replicated across billions of worlds throughout the galaxy? TRAPPIST-1e can't answer that completely, but it can provide crucial evidence one direction or another. We're standing at a threshold. Previous generations wondered if planets existed around other stars. We know they do. Previous generations wondered if Earth-sized planets existed in habitable zones. We know they do. Now we're asking whether those planets actually host life. That's the next question, the one our generation gets to investigate. TRAPPIST-1e represents that investigation's leading edge. A planet we can study in detail, close enough for meaningful observations, interesting enough to justify the effort. The observations are happening now. The data is accumulating. Within a few years, we'll know whether it has an atmosphere. Within a decade, we might know what that atmosphere contains. Within a generation, we might have direct evidence of life or its absence. That timeline feels slow from a human perspective. But it's extraordinarily fast from a historical one. The universe is old. The question of life beyond Earth is ancient. We're answering it in real time, using instruments that didn't exist a few years ago, analyzing data our grandparents couldn't have imagined collecting. The planet is there, 40 light-years away, orbiting its small red star with 6 siblings, possibly harboring oceans, possibly hosting life, possibly covered in dark forests optimized for infrared light, or possibly barren, sterile, a reminder that habitability alone doesn't guarantee biology. We don't know yet. We will soon. That's where the story stands. Not at an ending, but at a pivot point. TRAPPIST-1e exists. We found it, measured it, begun characterizing it. The next chapters will determine what it means. Whether it changes everything we thought we knew about life in the universe, or whether it confirms our loneliness, or whether it adds one more data point to a question that will take centuries to fully answer. What matters is that we're asking. What matters is that we have tools capable of providing answers. What matters is that a planet 40 light-years away, orbiting a star that will shine for trillions of years, has become more than a point of light in the sky. It's become a destination, a question, a possibility that might reshape how we understand our place among the stars.
On August 15, 1977, something transmitted a signal from deep space that shouldn't exist. For 72 seconds, a radio telescope in Ohio detected a narrowband transmission 30 times stronger than anything else in the sky, broadcast at a frequency internationally protected from human interference. Then it vanished. What happened next reveals why this brief moment still haunts the scientific community nearly 5 decades later. That night, Earth's rotation swept a massive radio telescope called Big Ear across a patch of sky in the constellation Sagittarius. The telescope wasn't hunting for anything specific, just methodically scanning the cosmos as it had done every clear night since 1973. But at 10:16 p.m. Eastern Time, something extraordinary happened. A signal began rising from the background noise of space, climbing to an intensity that would make it the strongest narrowband radio emission ever detected from beyond our solar system. The transmission lasted exactly as long as Big Ear's observation window allowed, 72 seconds, before Earth's rotation carried the telescope's beam away from the source. Then silence. Complete, absolute silence that continues to this day. Nobody noticed immediately. The telescope operated without human supervision, automatically recording data onto computer printouts that would be reviewed later. Days passed. The signal sat unnoticed in a stack of paper, just another line of numbers and letters waiting for someone to check the overnight observations. That someone was Jerry Emmon, a volunteer astronomer who'd written the software processing these signals. He was scanning through columns of alphanumeric characters when his eyes stopped on a sequence that should have been impossible. The printout showed signal intensities as single characters. Spaces meant nothing unusual. Numbers 1 through 9 represented progressively stronger signals. Letters indicated intensities beyond 10 standard deviations above background noise. Most of the paper was filled with spaces and occasional low numbers, the normal whisper of cosmic radiation. But there, in one column, Emmon saw something different. The sequence read 6EQUJ5. That U represented an intensity between 30 and 31 standard deviations above baseline. Nothing natural produces signals that strong and that narrow. Without thinking, Emmon grabbed a red pen and circled the sequence. In the margin, he scrawled a single word that would define this mystery for generations: wow. What makes the wow signal genuinely strange isn't just its strength. Radio telescopes detect powerful signals all the time from quasars, pulsars, and other energetic cosmic phenomena. Those sources blast radiation across wide frequency ranges, like shouting into every radio channel simultaneously. The wow signal did something fundamentally different. It transmitted on an incredibly narrow bandwidth, less than 10 kHz wide. That's the signature of artificial transmission, not natural cosmic noise. Even more intriguing was the specific frequency, 1420 MHz. In 1959, physicists Philip Morrison and Giuseppe Cacconi had published a landmark paper proposing where alien civilizations might broadcast if they wanted to be heard. Their answer was the hydrogen line, a natural frequency emitted by hydrogen atoms throughout the universe. Hydrogen is the most abundant element in existence. Any technological civilization capable of radio astronomy would know this frequency intimately. It's the cosmic equivalent of agreeing to meet at the most famous landmark in town, except the landmark is written into the fundamental physics of the universe itself. International agreements prohibit human transmissions near 1420 MHz precisely to keep this frequency clear for astronomical observation. The WOW signal appeared in a legally protected radio quiet zone, broadcast at the exact frequency two physicists had proposed as the universal channel for interstellar communication, with a narrowband precision that screams artificial origin. Big Ear was uniquely suited to detect such a signal, though calling it a telescope undersells its strangeness. Spanning 3 football fields, it looked nothing like the rotating dish antennas most people associate with radio astronomy. The main surface was flat, a 3-acre expanse of aluminum sheeting laid over concrete. At one end, a tilting reflector caught incoming radio waves and bounced them to a curved reflector at the opposite end. That parabolic surface focused the signal into 2 feed horns, the actual receivers that converted radio waves into electrical signals for the computer to process. The telescope couldn't rotate. It was fixed in place, relying entirely on Earth's rotation to scan the sky. As our planet turned, Big Ear's field of view swept across a narrow strip of the heavens, observing each point for exactly 72 seconds before moving on. This limitation actually became a strength for verification. If a signal came from space rather than a local source, it would rise in intensity as the telescope's beam approached it, peak when aligned, then fade as Earth carried the beam past. That's precisely what the WOW signal did. Its intensity curve matched the theoretical profile for a genuine astronomical source with remarkable precision. But here's where things get genuinely weird. Big Ear had 2 feed horns positioned so that any cosmic source would pass through both fields of view, separated by about 3 minutes as Earth rotated. If you detected something in the first horn, you'd definitely see it in the second. The WOW signal appeared in only one. For a source to vanish that quickly, it would need to either switch off during those 3 minutes or be so precisely aimed that it somehow missed the second horn entirely while hitting the first. Neither explanation makes sense for a natural phenomenon. The 6EQJ5 sequence itself has been widely misunderstood. Countless articles and documentaries have treated it like a coded message, analyzing the letters for hidden meaning. The reality is simultaneously more mundane and more fascinating. Each character represented a 10-second average of signal intensity. The 6 meant the signal started at 6 standard deviations above background. E equaled 14. Q was 26. U peaked at 30. Then J dropped to 19, and 5 fell to 5 before returning to background levels. The sequence wasn't a message, it was a graph showing how signal strength changed as Big Ear's beam swept across the source. What's remarkable isn't the characters themselves, but what they represent. Something out there transmitted a signal powerful enough to register 30 standard deviations above cosmic background noise. To understand how extraordinary that is, consider that most radio sources from space barely register above the noise floor. Detecting something at even 5 standard deviations would be noteworthy. 30 is unprecedented. Recent reanalysis using modern computational methods revised the signal's flux density upward to 250 Janskis, substantially higher than earlier estimates. This wasn't a faint whisper from the cosmos. It was a shout. Jerry Emin immediately recognized the significance. He'd spent years analyzing Big Ear data, scanning endless printouts of mostly unremarkable observations. He knew what normal looked like, and this wasn't it. The signal checked every box for an extraterrestrial transmission, narrowband, intense, at the hydrogen line frequency, with a temporal profile matching a fixed celestial source. Within days, the Big Ear team began follow-up observations, pointing the telescope back at the same region of sky. They found nothing. Night after night, the telescope scanned that patch of Sagittarius. The signal never returned. Other observatories joined the search over the following months and years, including facilities with more sensitive equipment than Big Ear. All of them came up empty. Whatever transmitted the WOW signal had gone silent, leaving behind only those 6 characters on a computer printout as proof it ever existed. The search continued far beyond those initial months. Big Ear remained operational until 1995, scanning the skies for 18 more years after the detection. During that entire time, it never recorded another signal approaching the WOW's intensity. When the facility was finally demolished to make room for a golf course, the mystery remained exactly where Emin had found it, circled in red ink on a piece of paper. Modern telescopes have since turned their attention to that region of space. In 2022, the Breakthrough Listen project coordinated observations between the Green Bank Telescope and the Allen Telescope Array, 2 of the world's most powerful radio astronomy facilities. They observed the WOW signal's coordinates for over an hour with equipment vastly more sensitive than Big Ear. The result was the same: silence. Whatever transmitted that signal either stopped, moved, or was a one-time event we'll never fully understand. Researchers have tried identifying specific stars in that direction that might host technological civilizations. Using data from the European Space Agency's Gaia Observatory, astronomers identified several Sun-like stars in the signal's general area. The most promising candidate, designated 2-mass 192819882-2640123, sits roughly 1,800 light-years away. It matches our Sun in temperature, radius, and luminosity, making it theoretically capable of supporting habitable planets. But there's a sobering implication to that distance. If the WOW signal came from that star, it was transmitted around 200 AD, during the height of the Roman Empire. Any response we send now wouldn't arrive for another 1,800 years. The universe operates on timescales that make human communication attempts feel almost absurdly brief. The source's location in Sagittarius places it toward the galactic center, a region dense with stars and interstellar material. That density creates both opportunities and complications. More stars mean more potential sources, but also more natural radio emissions that could potentially mimic an artificial signal under the right circumstances. Yet despite the cosmic distances and improbable odds, researchers haven't abandoned the search for answers. They've simply shifted tactics, examining every detail of that August night with forensic precision. One detail in particular has puzzled investigators from the beginning, a technical anomaly that might reveal more about the signal's nature than its intensity or frequency ever could. The Big Ear telescope had a peculiar design feature that most people overlook when discussing the WOW signal. It operated with 2 feed horns positioned to receive radio waves sequentially as Earth's rotation carried them across the sky. Think of it like 2 spotlights scanning the horizon one after another, each covering the same territory separated by a brief interval. Any genuine astronomical source should appear in both beams. The first feed horn would detect it, then roughly 3 minutes later, the second would pick up the same signal as it swept through that patch of sky. The WOW signal appeared in only 1 feed horn. Which one? Nobody knows. The data recording system didn't distinguish between the 2, logging readings from both into a single stream. This means the signal either turned on or turned off during those crucial 3 minutes between observations. For a fixed celestial source, that behavior makes absolutely no sense. Jerry Emin and his colleagues immediately recognized this oddity. A distant transmitter shouldn't care about Earth's rotation or the architecture of our telescopes. It should broadcast continuously, or at least on a timescale longer than a few minutes. The single horn detection suggested something far stranger than a simple radio beacon pointing toward Earth. Either the source was transient, flickering on or off in precisely the wrong moment, or something about the signal's directionality caused it to miss the second horn entirely. Imagine standing in a field with 2 spotlights separated by a few meters, scanning the horizon for a lighthouse. You see its beam sweep past the first spotlight, bright and unmistakable. 3 minutes later, your second spotlight should catch the same lighthouse beam. Instead, nothing. The lighthouse has either shut off, or its beam somehow avoided your second spotlight despite being in the exact same location. Neither explanation feels satisfactory. Some researchers propose that gravitational lensing might explain the single-horn mystery. If the signal passed near a massive object between its source and Earth, gravity could bend the radio waves, focusing them into a narrow beam that happened to align with one feed horn but not the other. It's theoretically possible, but the timing would need to be extraordinarily precise. Gravitational lensing events typically last much longer than 3 minutes, and the lensing object would need to be positioned with exquisite accuracy to create such a narrow window of visibility. The transient hypothesis offers another angle. Perhaps the source genuinely turned on and off, like a lighthouse with an irregular pattern. Neutron stars called pulsars do exactly this, rotating rapidly in sweeping beams of radio waves across space like cosmic lighthouses. But pulsars have distinctive signatures that the WOW signal lacked. They pulse regularly, sometimes hundreds of times per second, creating recognizable patterns. The WOW signal was continuous for its entire 72-second observation window, showing none of the characteristic flickering that would indicate a rotating source. That leaves the possibility of intelligent modulation. If an extraterrestrial civilization transmitted the signal, they might have deliberately controlled its duration and direction. Maybe they were scanning the galaxy systematically, their beam sweeping across Earth just long enough to be detected once before moving on to the next target. Or perhaps they detected something about our planet that triggered a brief, focused transmission, an interstellar hello sent in response to some signature of our technological presence. But here's where the mystery deepens further. The signal's frequency placed it at the hydrogen line, specifically at 1420.726 MHz. That's not exactly at the neutral hydrogen emission frequency of 1420.4058 MHz, but about 50 kHz above it. The shift is small but measurable, and it could indicate motion. If the source was moving toward Earth at roughly 10 kilometers per second, that would produce exactly the observed frequency shift through the Doppler effect. 10 kilometers per second isn't particularly fast by cosmic standards. Earth itself orbits the Sun at 30 kilometers per second. But it adds another variable to an already complex equation. Was the source approaching us? Was it in orbit around something? Or did the frequency shift reflect some other physical process entirely, perhaps related to the mechanism generating the signal in the first place? Without a second detection, these questions remain purely speculative, educated guesses built on a single data point. The bandwidth tells another story. The WOW signal was narrow, confined to less than 10 kHz. Natural astronomical sources typically splash across broad frequency ranges, their emissions spreading out like light through a prism. Narrowband signals are rare in nature but common in technology. Human radio stations, satellite transmitters, and communication systems all use narrowband signals because they're efficient, packing maximum information into minimum spectrum space. The narrowband nature of the WOW signal was one of its most compelling features, suggesting artificial origin more strongly than perhaps any other characteristic except its intensity. Yet even this has complications. Some natural phenomena can produce surprisingly narrow emissions. Masers, the microwave equivalent of lasers, occur in interstellar space where molecules amplify specific frequencies. Certain astrophysical masers produce bandwidths around 1 kHz, approaching but not quite matching the WOW signal's characteristics. Could the signal have been a particularly intense maser event, perhaps amplified by unusual conditions in an interstellar hydrogen cloud? That possibility gained traction in recent years when researchers examining archival data from the Arecibo Observatory discovered something unexpected. Between February and May 2020, Arecibo detected multiple signals remarkably similar to the WOW signal in their spectral characteristics. These weren't as intense, but they shared key features with that 1977 detection. Most significantly, they appeared to originate from regions of space containing cold hydrogen clouds. The hypothesis emerging from this work suggests that under certain conditions, hydrogen clouds can produce transient brightening events, temporary intensifications of radio emission at frequencies near the hydrogen line. The mechanism involves complex interactions between radiation passing through the cloud and the cloud's physical properties. When conditions align just right, the cloud acts like a natural amplifier, boosting radio signals to extraordinary intensities for brief periods before returning to normal. If this explanation holds up, the WOW signal wasn't a message from aliens. It was a rare natural phenomenon, a cosmic coincidence where we happened to be looking in the right direction when a hydrogen cloud briefly flared into radio brilliance. The signal's transient nature, its frequency, even its intensity would all make sense under this model. And the single horn detection? That could simply reflect the short duration of the brightening event, which happened to turn off during the 3-minute gap between the telescope's feed horns. Not everyone finds this hypothesis convincing. Critics point out that the mechanism producing such intense maser-like emissions from hydrogen clouds remains poorly understood. The Arecibo detections were much weaker than the WOW signal, suggesting that if they share a common origin, something extraordinarily unusual must have occurred in 1977 to produce such an intense event. And there's still no explanation for why, if these events occur with some regularity, we've only detected a handful of similar signals in nearly 5 decades of searching. Jerry Emmon himself remains cautious about dismissing extraterrestrial possibilities too quickly. In a 2019 interview, he stated his conviction that the WOW signal certainly has the potential of being the first signal from extraterrestrial intelligence. He's not claiming certainty, just acknowledging that among all the candidate signals ever detected, this one stands out. Its characteristics match what SETI researchers predicted artificial signals would look like. The fact that we can't definitively prove it came from aliens doesn't mean we can definitively prove it didn't. The scientific method demands reproducibility. A single unrepeatable detection, no matter how compelling, can never provide conclusive evidence. Without a second occurrence, the WOW signal remains trapped in uncertainty, too intriguing to dismiss but too isolated to confirm. It's the astronomical equivalent of a blurry photograph, clear enough to see something interesting happen but not quite sharp enough to say exactly what. This ambiguity frustrates researchers who spent careers searching for signs of extraterrestrial intelligence. SETI work requires extraordinary patience, scanning millions of channels across thousands of hours of observation time, knowing that even one genuine detection would justify the entire effort. The WOW signal dangled that possibility for a moment before vanishing, leaving behind only questions and that famous margin note. What makes the mystery even more maddening is knowing that if the signal does represent alien technology, it's operating on timescales and using strategies we might not fully comprehend. Perhaps we're thinking about alien communication all wrong. When we imagine receiving a signal from another civilization, we picture something continuous, deliberate, repeating. A beacon left on indefinitely, waiting for someone to notice. But what if advanced civilizations don't work that way? Consider how humans actually communicate across vast distances. We don't leave transmitters running constantly toward every star system in the galaxy. That would require enormous energy expenditure with vanishingly small probability of reaching anyone at the right moment. Instead, we send targeted bursts, brief transmissions calculated for maximum efficiency. The Arecibo message transmitted in 1974 lasted exactly 3 minutes before the telescope moved on to other work. Any civilization 25,000 light-years away in the direction of globular cluster M13 had better have been listening during that specific 3-minute window, or they missed humanity's greeting entirely. Now imagine this scenario multiplied across thousands or millions of civilizations, each sending occasional directed pulses rather than continuous broadcasts. The galaxy could be filled with technological signals that we simply never intercept because we're not looking in the right direction at the right time. The WOW signal's brief, non-repeating nature wouldn't be unusual under this model. It would be exactly what we should expect from efficient interstellar communication. There's another possibility that sounds like science fiction but follows logically from known physics. What if the signal was deliberately focused? Not broadcast omnidirectionally like a lighthouse, but beamed specifically in our direction for reasons we can't determine. Perhaps an automated probe detected our sun as a promising candidate for life-bearing planets. Perhaps some civilization completed a survey of our galactic neighborhood centuries ago and decided to send greeting pulses towards stars meeting certain criteria. Or perhaps the timing was pure coincidence, a beam sweeping past Earth on its way to some other target. Focused beams would explain the signal's intensity. Broadcasting equally in all directions requires vastly more power than directing energy in a narrow cone. A civilization trying to maximize the range of their transmissions would absolutely choose beaming over omnidirectional broadcast. But here's the catch: if you're not in the beam's path, you'll never detect anything at all. And if Earth just happened to be in that path for 72 seconds before the beam moved on, we'd never see it again no matter how long we searched. The physics of interstellar distances compounds these problems in ways most people don't fully appreciate. The candidate star 2 mass 192819882-2640123, identified as a potential source, sits 1,800 light-years away. Any signal we received in 1977 would have been transmitted around the year 177 AD. Think about what humanity was doing then. The Roman Empire was at its height. Most of the world's population lived in agricultural societies with no conception of radio waves or technological communication. If an alien civilization sent that signal expecting a response, they won't receive our reply until around the year 3777 AD. This creates a fundamental coordination problem. How do two civilizations separated by thousands of light-years establish communication when each exchange takes millennia? You can't have a conversation. You can't even confirm reception within any individual's lifetime, or within the lifetime of entire civilizations. Any signal we send back toward that star will arrive at a destination we know almost nothing about, aimed at a civilization that might have evolved beyond recognition, collapsed entirely, or lost interest in the project generations ago. Some researchers propose that sufficiently advanced civilizations might solve this through patience and long-term planning. Build systems designed to operate for thousands of years. Create communication protocols that don't require real-time interaction. Perhaps encode vast amounts of information in a single transmission, knowing that response time will be measured in millennia. But this assumes a level of cultural stability and long-term thinking that humanity hasn't yet demonstrated. Our own SETI programs struggle with funding cycles measured in years, not centuries. There's a darker interpretation that some scientists hesitate to discuss publicly. What if civilizations capable of interstellar communication exist but deliberately avoid sustained contact? The zoo hypothesis, as it's called, suggests advanced civilizations might observe developing species like humanity without revealing themselves, similar to wildlife researchers maintaining distance from their subjects. Under this model, we might occasionally detect leakage from their transmissions or brief scans of our region, but never receive the sustained, repeating signal we're hoping for. Or consider the possibility that we're late to the conversation. Perhaps the galaxy went through a phase of active radio communication millions of years ago, when civilizations first developed the technology. After millennia of contact, everyone moved on to more efficient methods we haven't discovered yet. We're scanning radio frequencies while they're using quantum entanglement, neutrino beams, or something we don't have names for. The WOW signal could be the equivalent of finding a telegram in a world that's moved on to fiber optic internet. Each of these scenarios is scientifically plausible. None requires physics we don't understand or technologies we can't imagine. But they all share a common thread. They make the search for extraterrestrial intelligence exponentially more difficult than the optimistic predictions of the 1960s suggested. When Morrison and Cacconi first proposed SETI in 1959, the thinking was straightforward. Advanced civilizations would recognize that hydrogen line radio frequencies represent a universal constant. They'd broadcast continuously on those frequencies, creating beacons that anyone searching would eventually find. It was an elegant theory based on reasonable assumptions about how intelligence might behave. 65 years later, we've learned those assumptions might be too simple. Intelligence doesn't follow a single predictable path. Human civilization alone demonstrates wildly different approaches to communication, resource allocation, and long-term planning across different cultures and time periods. Extrapolating from a sample size of one is difficult enough. Imagining how alien intelligence might operate adds layers of uncertainty that mathematics alone can't resolve. The technology gap presents another challenge. Consider the difference between 1977 and today. The big year's 50 channels and analog recording systems seem primitive compared to modern digital processing that can monitor billions of channels simultaneously. Breakthrough Listen's observations in 2022 used equipment orders of magnitude more sensitive than anything available in 1977. Yet they found nothing in that same patch of sky. Does this mean the WOW signal was noise, malfunction, or misinterpretation? Not necessarily. It might mean the source was genuinely transient, appearing and disappearing on timescales shorter than our observation windows. Or it might indicate that our modern searches, despite their technical superiority, aren't looking at exactly the right moment or in exactly the right way. This leads to an uncomfortable question that strikes at the heart of SETI methodology. How much observation time is enough to conclusively rule out a signal? The Breakthrough Listen search lasted 1 hour from Green Bank, 35 minutes from the Allen Telescope Array. Sounds substantial until you remember that the original detection lasted 72 seconds. If the signal repeats on a cycle measured in years or decades, we could search for months and still miss it entirely. The economics of telescope time make comprehensive searches nearly impossible. Major radio observatories have packed schedules serving multiple research programs. Dedicating thousands of hours to repeatedly observing a single location on the slim chance of catching a brief transient signal requires resources that are difficult to justify when so many other astronomical questions need attention. The Big Year could afford continuous SETI work because it was essentially retired from other projects. Modern facilities rarely have that luxury. Bob Gray's experience illustrates the problem perfectly. In 1987 and 1989, he used the Oak Ridge Observatory to search for the WOW signal's return. He found nothing. In 1995 and 1996, he searched again with the Very Large Array. Still nothing. These weren't token efforts, but they still represented only a tiny fraction of the time that would be needed to truly rule out a periodic signal with a long repetition cycle. Imagine a civilization that broadcasts for 72 seconds once per decade toward each of 10,000 target stars. They're following a perfectly logical strategy, maximizing coverage while minimizing energy expenditure. But from our perspective, we'd need to continuously monitor each target for years to have a reasonable chance of catching their brief transmission. The universe could be filled with efficient communicators, and we'd still face astronomical odds of detection. The silence following the WOW signal teaches us something important about the search for extraterrestrial intelligence, though perhaps not the lesson we wanted to learn. It reveals how much we still don't know about the nature of technological civilizations, their communication strategies, and the likelihood of successful contact across interstellar distances. Every assumption we make about how aliens might behave is colored by our own limited experience as a species barely a century into the radio age. What comes next requires rethinking our approach. Not abandoning SETI, but acknowledging that the search might be far more complex than early pioneers imagined. The modern approach to SETI reflects this complexity by diversifying search strategies. Projects like Breakthrough Listen don't just look for repeating signals at specific frequencies. They scan billions of channels simultaneously, monitor multiple target stars, and search for patterns we might not have anticipated in 1977. The Allen Telescope Array, specifically designed for SETI work, can observe multiple directions at once while also serving conventional astronomy. This parallel processing approach increases the odds of catching transient events, though it still requires being pointed in the right direction at the right time. Private funding has become crucial as government support for SETI remains inconsistent. Yuri Milner's Breakthrough Initiatives represents the largest privately funded effort, committing $100 million over 10 years. This financial backing allows sustained observation campaigns that would be impossible through traditional academic funding cycles. The stability matters because SETI is fundamentally a long-term endeavor where success might require decades of patient searching rather than lucky discoveries. Machine learning now processes SETI data in ways that weren't conceivable in the 1970s. Instead of Jerry Emmon manually reviewing printouts, algorithms can identify unusual patterns across vast datasets, flagging candidates for human review. This doesn't eliminate false positives, but it dramatically increases the volume of data that can be analyzed. The challenge shifts from missing signals buried in data to managing the overwhelming number of borderline detections that require investigation. Yet for all this technological advancement, we're still making assumptions that might be fundamentally wrong. We assume radio waves are the preferred communication medium because that's what we use. An advanced civilization might have moved beyond radio entirely, using methods we haven't discovered or can't detect with current instruments. Optical SETI searches for laser pulses, acknowledging that focused light beams could carry information more efficiently than radio for certain applications. Neutrino communication, gravitational wave messaging, or techniques we can't even imagine might be how the galaxy actually talks. The Fermi paradox looms over every SETI discussion. If intelligent life is common, where is everybody? The WOW signal tantalizes because it suggests someone might be out there, but the lack of follow-up deepens the paradox rather than resolving it. Maybe technological civilizations are common but brief, emerging and vanishing too quickly for overlap. Maybe they deliberately avoid contact, observing us while remaining hidden. Maybe the universe is full of civilizations that simply don't care about reaching out to primitives like us. Or maybe we're approaching this entirely wrong by assuming aliens would want to communicate at all. Human civilization broadcasts constantly, but that's an artifact of our particular technological path and social structure. A species that evolved differently might have no concept of deliberately reaching out to strangers across the void. Their technology might be invisible to our searches not through advanced stealth, but because it operates on principles we haven't considered. The signal's location in Sagittarius points toward the galactic center, one of the densest regions of our galaxy. Thousands of stars cluster in that direction, increasing the probability that something interesting might originate there. Amateur astronomer Alberto Caballero identified 2MASS 19281982-2640123 as a promising candidate source, a Sun-like star about 1,800 light-years away. If the signal came from a planet orbiting that star, it was transmitted around 200 AD, when the Roman Empire was at its height and most of Earth's population had no idea other continents existed. This temporal disconnect illustrates the profound difficulty of interstellar communication. Even traveling at light speed, the fastest possible pace, messages take centuries or millennia to cross galactic distances. A civilization sending signals toward promising stars must do so with no expectation of dialogue, only the hope that someone eventually listens. They would transmit toward where Earth was 1,800 years ago, calculating our sun's position, accounting for stellar motion over that immense time span. The precision required is staggering. What if the WOW signal wasn't aimed at us specifically? It might have been part of a broader beacon, sweeping across multiple star systems in systematic fashion. The 72-second duration could represent the time their transmitter spent pointed in our general direction before moving on to the next target. This would explain why we've never detected it again. We weren't the intended recipient, just a lucky bystander who happened to be listening when the beam swept past. The two-feed horn mystery remains the single most puzzling technical aspect. For a celestial source, both horns should have detected the signal minutes apart as Earth's rotation carried them through the same patch of sky. Only one horn received it. This suggests three possibilities, none satisfying. First, an incredibly brief transient event that switched off during the gap between horn observations. Second, a focused beam that happened to illuminate one horn but not the other, implying either remarkable targeting or remarkable coincidence. Third, an equipment malfunction that produced a false signal, though this seems unlikely given how well the signal matched expected characteristics of a genuine astronomical source. Equipment malfunction remains the most prosaic explanation, yet it's difficult to reconcile with the signal's properties. The intensity pattern matched exactly what you'd expect from a distant source, rising and falling as the telescope beam swept across it. The frequency fell within the protected radio astronomy band at the hydrogen line, exactly where SETI researchers predicted intelligent signals might appear. The bandwidth was narrow, characteristic of artificial rather than natural emissions. Every detail fit the profile of a genuine detection except for the lack of repetition and the single horn observation. Robert Gray's searches using the VLA highlight how much observing strategy matters. The VLA is far more sensitive than Big Ear was, but sensitivity alone doesn't guarantee detection if the timing is wrong. Gray observed the WOW signal location for hundreds of hours total across multiple years. For a signal repeating on a yearly cycle, he might have caught it. For something repeating every decade, his chances dropped dramatically. For a truly one-time event, no amount of follow-up observation would ever succeed. This raises uncomfortable questions about how many other potential signals we've missed. Big Ear operated for 22 years in SETI mode, but it could only observe each point in the sky for 72 seconds per day. Most of the sky was never observed at all, and even targeted regions received minimal coverage. If interesting signals are rare and brief, the odds of detection are microscopic regardless of telescope sensitivity. We might be surrounded by transmissions we'll never notice simply because we're not looking in the right direction at the right time. The hydrogen cloud hypothesis emerging from recent research offers the first genuinely scientific explanation that accounts for the signal's properties without invoking either aliens or equipment failure. In 2020, researchers analyzing Arecibo data discovered multiple narrowband signals near the hydrogen line frequency, originating from cold hydrogen clouds in space. These weren't continuous emissions but transient brightenings, similar in character to the WOW signal though less intense. The mechanism involves naturally occurring masers, where hydrogen atoms in space temporarily amplify radio waves through quantum mechanical processes. If the WOW signal was a particularly intense hydrogen cloud maser, it would explain several puzzling features. The narrowband nature matches maser emissions. The frequency near the hydrogen line makes sense for a phenomenon involving hydrogen. The lack of repetition is expected if the brightening resulted from a rare alignment of conditions that hasn't recurred. Even the single-horn detection becomes less mysterious if the maser brightening was extremely brief, switching on and off during the minutes between horn observations. This explanation satisfies Occam's razor by invoking known physics rather than requiring extraterrestrial civilizations. Yet it remains unproven because we haven't observed another hydrogen cloud maser with comparable intensity to the WOW signal. The Arecibo detections were similar but weaker. Until we see another event matching the WOW signal's strength, the hydrogen cloud hypothesis remains plausible but unconfirmed, just like every other explanation proposed over the decades. For Jerry Emmon, the uncertainty has evolved from frustration to philosophical acceptance. In a 2019 interview, he stated he's convinced the WOW signal has the potential to be the first detection of extraterrestrial intelligence, but he acknowledges we simply don't know. That honest assessment captures the essence of SETI's challenge. We're searching for something we've never encountered, using methods we're still developing, guided by assumptions that might be completely wrong. The signal's legacy extends beyond the mystery of its origin. It demonstrated that SETI could detect something genuinely unusual, validating the basic approach even if this particular detection remains unexplained. It inspired continued searching when funding and institutional support were uncertain. It captured public imagination in ways that dry scientific papers never could, keeping interest in the search for extraterrestrial intelligence alive during decades when little else emerged. The famous WOW, scrawled in red ink, became an icon, representing both the thrill of potential discovery and the frustration of incomplete answers. What would constitute proof that the WOW signal was artificial? Repetition would help, but even that wouldn't be conclusive without additional information. A repeating signal following a pattern too precise to be natural. Modulation encoding information beyond simple carrier waves. Multiple signals from the same location at different times. Responses to messages we send toward the source. Each level of evidence would shift probability without providing absolute certainty until we detected something unmistakably artificial. The search continues not because we expect to rediscover the WOW signal specifically, but because it represents what's possible. Modern SETI has evolved dramatically from the days when Jerry Emmon scanned computer printouts by hand. Today's searches process billions of channels simultaneously, covering frequency ranges far broader than Big Ear could monitor. The Allen Telescope Array in California, purpose-built for SETI, consists of 42 radio dishes working together. Breakthrough Listen, funded by tech investor Yuri Milner, represents the most comprehensive search ever undertaken, surveying 1 million nearby stars and scanning the entire galactic plane. These projects operate continuously, generating data volumes that would have been unimaginable in 1977. The technological leap is staggering. Big Ear monitored 50 channels at once. Modern systems track billions. Where Emmon needed days to review a single night's observations, contemporary algorithms process data in real time, flagging interesting signals instantly. Machine learning now identifies patterns humans might miss, sorting through radio frequency interference to find genuinely anomalous signals. The sensitivity has improved too. Current telescopes could detect a signal like the WOW several times weaker than what Big Ear required. Yet despite these advances, we haven't found another WOW signal. Breakthrough Listen's observations in May 2022 targeted the exact region where the original signal originated, using both the Green Bank Telescope and the Allen Telescope Array simultaneously. They found nothing. The silence doesn't prove the signal was never there, but it reinforces how rare such detections are. If the WOW signal was artificial, either the transmission has stopped, or it was never a continuous beacon in the first place. This raises uncomfortable questions about SETI methodology. We assume extraterrestrial civilizations would transmit continuously, creating signals we could detect through patient observation. But what if that assumption is wrong? Human civilization broadcasts radio signals constantly only because we're communicating with ourselves, not trying to signal other worlds. Deliberate interstellar messages might be brief, targeted pulses rather than omnidirectional beacons. If the WOW signal was such a pulse, catching it was astronomically lucky, and expecting repetition might be unrealistic. Consider the economics of interstellar transmission. Broadcasting powerfully enough for detection across light years requires enormous energy. Doing so continuously in all directions would be wasteful beyond reason. A civilization attempting contact might instead send brief, focused beams that sweep across potential target stars like a lighthouse. From our perspective, such a transmission would appear exactly once as the beam crossed Earth, lasting only as long as the beam width allowed. This directed transmission hypothesis fits the WOW signal's characteristics perfectly. The 72-second duration matches Earth's rotation carrying the telescope through a narrow beam. The lack of repetition makes sense if the beam moved on to other targets. Even the single-horn detection becomes explicable if the beam was extremely focused and timing placed it between the two-horn observations. Under this scenario, we weren't the primary audience. We were briefly illuminated by a message aimed elsewhere, catching a glimpse of communication not meant for us. But there's a darker possibility. Perhaps the silence since 1977 reflects something more troubling than transmission strategies. The Great Filter hypothesis suggests that intelligent civilizations face catastrophic obstacles preventing them from becoming long-lived, galaxy-spanning societies. Maybe technological civilizations typically destroy themselves shortly after developing radio capabilities. The WOW signal could represent a civilization that existed briefly then vanished, leaving only that single transmission as evidence they were ever there. The timescales involved add weight to this concern. If the signal originated 1,800 light-years away, it was transmitted around 200 AD. The civilization that sent it has had 18 centuries to continue developing, colonizing nearby stars, or destroying itself. If they're still transmitting, we should see repeated signals. If they've become a spacefaring civilization, we might detect other evidence of their presence. The absence of either suggests they're gone. Or perhaps we're looking for the wrong thing entirely. SETI focuses on radio signals because that's what we understand and can detect efficiently. But a civilization thousands of years more advanced might use communication methods we can't recognize. Neutrino beams, gravitational wave modulation, quantum entanglement communications, technologies that would be invisible to our current instruments. The WOW signal might be the equivalent of detecting smoke from a distant fire, not because fire is how that civilization communicates, but because it's the only aspect of their technology that accidentally produces effects we can measure. The anthropocentric bias in SETI runs deeper than technology. We assume extraterrestrial intelligence will want to communicate with us, that they'll consider radio signals an appropriate medium, that they'll transmit at frequencies we're monitoring. Every assumption reflects human perspectives and priorities. An intelligence that evolved in completely different circumstances, with different sensory capabilities and different fundamental needs, might approach communication in ways we literally cannot imagine. The WOW signal might be meaningful to them in ways we'll never comprehend. Frank Drake, who pioneered SETI and formulated the famous Drake equation estimating the number of detectable civilizations, remained optimistic despite decades of silence. He argued that absence of evidence isn't evidence of absence, that the galaxy is vast and we've barely begun searching. But Drake died in 2022 without witnessing confirmed contact. His equation suggested numerous civilizations should exist, yet we've detected none conclusively. Either the equation's optimistic parameters are wrong, or something prevents these civilizations from being detectable. The Fermi paradox captures this tension perfectly. If intelligent life is common, where is everybody? The wow signal intensifies rather than resolves this paradox. It suggests something might be out there, but the lack of follow-up implies whatever exists isn't making sustained efforts at contact. Perhaps civilizations broadcast briefly during specific developmental phases then stop. Perhaps most intelligence is uninterested in communication. Perhaps the galaxy is full of civilizations deliberately avoiding contact. That last possibility deserves serious consideration. If predatory civilizations exist, advertising your presence could be catastrophic. Broadcasting powerful radio signals announces not just existence but approximate technological level and location. A sufficiently paranoid civilization might choose silence over risk. The wow signal, under this interpretation, could be a warning example. A civilization that broadcast openly and paid a price, with that single transmission being the last thing they sent before learning the danger of making noise in a potentially hostile galaxy. These speculations highlight how the wow signal's greatest impact might be philosophical rather than scientific. It forced us to confront the possibility that we're not alone while simultaneously demonstrating how difficult confirmation would be. The signal exists in that liminal space between evidence and proof, substantial enough to take seriously but ambiguous enough to resist definitive interpretation. It's a cosmic Rorschach test, reflecting our hopes and fears about what might be out there. The signal also reveals humanity's deep need for cosmic company. The immediate excitement Emin felt, the decades of continued interest, the way, wow, became iconic, all reflect our desire to believe we're not the universe's only conscious observers. The signal's ambiguity lets us maintain that hope without requiring us to confront the full implications of confirmed contact. We can wonder without having to deal with the reality. Meanwhile, SETI continues expanding in scope and sophistication. Optical SETI searches for laser pulses, brief but powerful flashes that might be detectable across interstellar distances. Projects like Breakthrough Listen Starshot Initiative propose sending tiny probes to nearby stars, flipping the equation from passive listening to active exploration. The search for technosignatures extends beyond radio to include atmospheric pollution on exoplanets, artificial structures around stars, or other evidence of technological civilizations modifying their environments. Yet for all this progress, the wow signal remains unique. No other detection in SETI history has matched its combination of strength, duration, and frequency specificity. Other candidates have emerged: the BLC-1 signal from Proxima Centauri in 2020, various fast radio bursts of uncertain origin, but none possess the wow signal's compelling characteristics. Each new detection generates brief excitement before being explained away as interference or natural phenomena. The wow signal alone resists such explanations while refusing to repeat. This singularity suggests something important about the search itself. If the wow signal was artificial, it demonstrates that detection is possible but vanishingly rare. If natural, it shows that even experienced researchers can be fooled by unusual astrophysical phenomena. Either way, it calibrates expectations. SETI isn't about finding signals every week, but about maintaining vigilance for events that might occur once in a lifetime. The search requires patience measured not in years but decades or centuries. Human civilization has been capable of detecting radio signals for roughly a century. We've been actively searching for extraterrestrial intelligence for about 60 years. On cosmic timescales, this is nothing. We've barely begun. The wow signal, whether artificial or natural, occurred within the first few decades of our ability to notice such things. What might we detect if we search for another century? Another millennium? Assuming we survive that long. The survival question extends beyond technological capability to psychological and sociological resilience. A species might develop radio astronomy, detect signals from other worlds, even build interstellar probes, yet still destroy itself through war, environmental collapse, or resource exhaustion. The gap between can listen to the stars and can survive for millennia might be enormous. Earth's own trajectory offers little comfort. We've possessed nuclear weapons for less than a century, and we've come disturbingly close to using them multiple times. Climate change accelerates while political will remains fractured. Our technological power outpaces our wisdom in wielding it. If we're typical, the window between developing radio technology and self-destruction might be narrow. The Fermi paradox gains teeth here. Where is everybody? Perhaps they're gone. Perhaps they never made it past the filters we're currently navigating. The WOW signal, if artificial, might be a voice from a civilization that no longer exists, their transmission reaching us long after they fell silent forever. We're listening to ghosts, picking up echoes of societies that solved the technology problem but failed the survival test. This interpretation is bleak but consistent with what we observe, a universe seemingly full of potential homes for life, yet eerily quiet. Alternatively, we might be early. The universe is 13.8 billion years old, but the first generation of stars contained almost no heavy elements. Planets like Earth, rich in carbon, oxygen, and metals, couldn't form until later stellar generations had synthesized and distributed these elements. Habitable worlds might be a relatively recent phenomenon on cosmic timescales. If so, humanity could be among the first technological civilizations to arise. The silence we hear isn't absence but timing. We're calling into a universe where most potential respondents haven't evolved yet. Under this scenario, the WOW signal becomes even more significant. If we're among the earliest technological species, detecting any signal at all would be remarkable. The transmission might come from one of the few other early civilizations, a cosmic neighbor also feeling their way through the dark, wondering if they're alone. Two young species, separated by vast distances, briefly touching through radio waves before the conversation could develop. There's a melancholy beauty in that image. Then there's the most unsettling possibility: we're being watched but not contacted. The Zool hypothesis suggests advanced civilizations might deliberately avoid interfering with younger species, observing us like researchers studying animals in their natural habitat. Under this framework, the silence isn't absence but policy. They're out there, they know about us, but they've collectively decided to let us develop without interference. The WOW signal under this interpretation could be a mistake, a brief lapse in quarantine protocol, or perhaps a deliberate test. Send a signal strong enough to be noticed but ambiguous enough to maintain deniability. See how the younger species reacts. Do they recognize it as artificial? How do they respond? What does their reaction reveal about their development level and cultural maturity? If this sounds paranoid, consider that humans already practice similar policies with uncontacted tribes on Earth. We recognize they exist, we could contact them, but we choose not to, believing interference would harm them more than help. Perhaps advanced civilizations view us the same way, as a developing species best left to mature naturally. The lack of clear, unambiguous contact might be intentional. Yet this hypothesis carries its own problems. It requires not just one advanced civilization maintaining a non-interference policy, but all of them. A single defector, one civilization that chooses contact over observation, would break the silence. The fact that we haven't been contacted openly suggests either there's no one out there, or the non-interference consensus is remarkably strong, or the penalties for breaking it are severe. What enforcement mechanism could maintain such discipline across potentially thousands of civilizations? The questions multiply faster than answers. Each explanation for the WOW signal's uniqueness creates new puzzles. If it was artificial, why hasn't it repeated? If natural, why have similar events been so rare? If there are others out there, why the overwhelming silence? The signal sits at the center of these mysteries like a Zen koan, a question that resists simple resolution. Perhaps that's the point. The WOW signal's greatest gift might be forcing us to sit with uncertainty. In an age of instant information and confident explanations, here's a phenomenon that resists both. We can measure it, analyze it, debate it, but we cannot definitively explain it. That discomfort with ambiguity might be exactly what we need. Science progresses not through comfortable certainties but through productive confusion, through anomalies that don't fit existing frameworks and force us to expand our thinking. The WOW signal does precisely this. It challenges assumptions about signal detection, about what constitutes evidence, about how we should conduct the search for extraterrestrial intelligence. Every attempt to explain it has revealed gaps in our understanding, driving refinements in methodology and theory. If the signal had been easily explained, it would have taught us less. Meanwhile, the search continues with increasingly sophisticated tools. The square kilometer array, when complete, will be 50 times more sensitive than any existing radio telescope. Projects like Breakthrough Listen scan millions of stars across billions of frequency channels, searching for patterns that might indicate technology. Optical SETI looks for laser pulses, brief flashes that could carry information across interstellar distances. We're expanding the search space, refusing to let one mysterious signal define the limits of possibility. Yet there's wisdom in remembering the WOW signal's lesson. Detection is hard, confirmation is harder, and the universe might be far stranger than our current theories suggest. We might be looking in the right places with the right tools but at the wrong times. Or we might be looking for the wrong things entirely, biased by our own technological trajectory toward radio and optical signals when advanced civilizations might use methods we haven't imagined. The signal endures because it represents the best evidence we have while simultaneously being insufficient evidence to conclude anything definitive. It's tantalizing precisely because it could go either way. This ambiguity keeps us searching, keeps us wondering, keeps us looking up at the stars with hope mixed with humility. 48 years after Jerry Emmons circled those 6 characters on a computer printout, we're no closer to certainty about what caused them. But we're asking better questions, building better tools, and thinking more carefully about what it means to search for life beyond Earth. The WOW signal hasn't been explained, but it's educated us. That might be its most important legacy, not an answer, but an invitation to keep asking. The search for meaning in the WOW signal mirrors humanity's larger search for meaning in the cosmos. We want the universe to acknowledge us, to confirm we matter, that consciousness isn't just a brief accident in one remote corner of space. That desire shapes how we interpret ambiguous data. We see patterns because we need them to be there. But science demands we separate what we wish from what we can prove. The WOW signal might be the most important detection in human history. It might be a mundane astrophysical burp we happen to notice. Both possibilities remain open because we lack the one thing that would close the case, a second detection. This frustrates people who want closure, who need the story to have an ending. The WOW signal doesn't provide that satisfaction. It's a cliffhanger that's been running for nearly half a century, a question mark that refuses to resolve into a period or exclamation point. You have to make peace with not knowing. Consider what we've actually learned. We know that whatever produced the signal operated at the hydrogen line frequency, the universal signpost that SETI pioneers predicted decades before detection. We know it was narrowband, precisely the characteristic that distinguishes artificial from natural emissions. We know it rose and fell exactly as expected for a distant source, tracked by Earth's rotation through our telescope's field of view. Every technical detail supports artificial origin except the most important one: it never happened again. The hydrogen cloud hypothesis offers a natural explanation that accounts for many features, but it requires rare conditions we've never observed producing comparable intensity. Comets don't work as sources because they were in the wrong position and can't explain the technical characteristics. Equipment malfunction seems unlikely given how perfectly the signal matched predicted alien transmission profiles. Every explanation has fatal flaws except we don't know. That uncertainty is valuable. It calibrates expectations for future SETI work. The search isn't about finding signals constantly, but about maintaining the capacity to notice rare events. Infrastructure matters more than immediate results. The Big Ear detected the WOW signal because it existed and was operating, not because researchers expected anything that particular night. Serendipity requires preparation. Modern SETI has absorbed these lessons. Breakthrough Listen doesn't just point telescopes at promising stars. It archives data continuously, allowing retrospective analysis as new theories emerge. The Allen Telescope Array monitors multiple regions simultaneously, increasing odds of catching transient events. We're building systems that can wait patiently for decades because that might be the timescale required. The signal also taught us that detection alone doesn't answer the question. Even if we found another WOW signal tomorrow, even if it repeated reliably, we'd still face the problem of interpretation. Is it deliberate communication? Accidental leakage from alien technology? Natural phenomena we don't understand? Without additional context, narrowband radio emissions remain ambiguous regardless of strength or repetition. That's why some researchers now emphasize searching for technosignatures beyond radio. Atmospheric pollution on exoplanets might indicate industrial civilizations. Megastructures around stars could reveal engineering projects on scales we're only beginning to imagine. These approaches sidestep the communication problem entirely by looking for evidence of technology rather than messages. You don't need aliens trying to contact you if you can detect the side effects of their existence. But there's something compelling about radio signals specifically, something that connects directly to human experience. We've been broadcasting radio for over a century. We understand the technology intimately. Finding a radio signal feels more concrete than detecting weird atmospheric chemistry that might indicate industry. It's immediate, recognizable, a form of contact we can imagine even if we can't confirm it. The WOW signal captures that immediacy. Jerry Emmon didn't need complex analysis to recognize something extraordinary. The intensity jumped off the page, 30 standard deviations above background, a number so extreme it could only mean something unusual had occurred. That visceral impact, the immediate gut-level recognition that this was different, makes the signal memorable in ways that statistical analysis of planetary atmospheres never quite matches. Yet we have to guard against letting that emotional response override careful reasoning. The history of science is littered with exciting discoveries that turned out to be instrumental artifacts, misinterpreted data, or natural phenomena masquerading as something more interesting. The WOW signal might belong in that category. We won't know until we either detect it again or develop a compelling natural explanation that accounts for all observed characteristics. The waiting is the hard part. 48 years feels long on human timescales. On cosmic timescales, it's nothing. If technological civilizations are rare, if their transmissions are brief and targeted, if the galaxy operates on schedules measured in millennia rather than decades, then expecting quick answers was always unrealistic. The WOW signal might be the first chapter in a story that takes centuries to unfold. Or it might be the entire story, a single event that will never be explained because the information needed to explain it no longer exists. The source could be gone. the conditions that produced it might have been unique. We might be trying to solve a mystery with insufficient data, like archaeologists reconstructing a civilization from a single artifact. That possibility should be humbling. The universe doesn't owe us explanations. It exists according to physical laws that operate whether we understand them or not. Our desire for meaning, for contact, for confirmation that we're not alone might never be satisfied. The cosmos is under no obligation to provide the answers we seek. But we keep searching anyway because the question matters more than any individual answer. Are we alone? That's not just an astronomical question. It's philosophical, existential, touching on everything from the nature of consciousness to humanity's place in the universe. The wow signal, whatever caused it, proves we can ask that question with increasingly sophisticated tools. We might not have the answer yet, but we're learning how to look. The infrastructure being built now, the techniques being developed, the theoretical frameworks being refined, all of this creates capacity for future discoveries. We're not just searching for aliens. We're developing technologies and methodologies that advance astronomy generally. Radio telescope arrays built for SETI also map the cosmos, study pulsars, investigate fast radio bursts, and probe the structure of galaxies. The search justifies itself through the science it enables even if contact never occurs. And contact might never occur. That's the reality we need to accept. The universe might be full of life, but life might not be full of intelligence. Intelligence might not lead to technology. Technology might not lead to radio transmission. Any of these filters could explain the silence. The great filter might be behind us or ahead of us, but either way, it suggests that technological civilizations capable of interstellar communication are vanishingly rare. If so, the wow signal becomes either more precious or more puzzling depending on interpretation. If it was artificial, we might have detected one of a handful of other voices in the galaxy, a cosmic neighbor who briefly made themselves known. If natural, it represents a phenomenon rare enough that we've only caught it once in nearly a century of radio astronomy. Either way, it's exceptional. That exceptionality is what keeps people returning to the signal, what makes it endure in cultural memory when thousands of other astronomical observations fade into technical literature. The wow signal has a story. It has a moment of discovery, a human face in Jerry Emmon, a dramatic tension between hope and uncertainty. It represents possibility without providing proof, keeping the question open in ways that confirmed contact or confirmed rejection never could. Maybe that's why we need the wow signal to remain mysterious. It lets us wonder without requiring us to confront implications. Confirmed alien contact would force humanity to reconsider our place in the universe, our uniqueness, our importance. Confirmed absence would cement our cosmic loneliness in ways that might be psychologically devastating. The wow signal occupies a perfect middle ground where hope remains alive but responsibility for response remains deferred. Still, the question demands investigation. We can't simply shrug and accept mystery when the stakes are this high. If there's even a small chance the signal represents extraterrestrial intelligence, we owe it to ourselves to search thoroughly. The cost of missing genuine contact because we didn't look hard enough would be catastrophic to our understanding of the universe and our place within it. So the telescopes keep scanning. The algorithms keep processing. The researchers keep analyzing, publishing, debating. Each year brings incremental progress, refined theories, better instruments. We're not where we were in 1977. We're not where we'll be in 2077. The search evolves, and with it, our capacity to recognize answers when they arrive. The wow signal taught us that answers might arrive suddenly, without warning, in a form we barely recognize until after the fact. Jerry Emmon didn't know he was making history when he reviewed that printout. He was just doing his job, checking data like he'd done countless times before. Discovery doesn't announce itself. It hides in routine until someone notices. That's the final lesson. Pay attention. Maintain the infrastructure. Keep watching. Because somewhere out there, in the vast darkness between stars, something transmitted a signal that reached Earth on August 15, 1977. Whether it was intelligence reaching across the void or nature producing a rare cosmic burp, we still don't know. But we know it happened. Those 6 characters, 6EQUJ5, prove that the universe can surprise us. And if it surprised us once, it might surprise us again. We just have to be listening when it does. A single teaspoon of this star weighs more than all of humanity combined. Its magnetic field could erase your credit card from halfway to the moon. And if it had a bad day 42,000 years ago, you'd know about it right now. These aren't hypothetical monsters from science fiction. They're real, they're out there, and they've already touched our planet in ways that should terrify you. Magnetars represent the most extreme magnetic environments in the known universe. Picture Manhattan Island compressed into a ball so dense that a sugar cube of its material would weigh as much as an entire mountain. Now wrap that impossibility in a magnetic field a quadrillion times stronger than Earth's. That's a magnetar. 20 kilometers across, spinning several times per second, radiating more energy in 1/10 of a second than our sun produces in 150,000 years. The numbers seem designed to break human comprehension. A magnetic field of 10 to the 15th Gauss. Energy densities 10,000 times greater than lead. Forces so intense they warp the fabric of empty space itself. But here's what makes magnetars truly unsettling: we didn't predict them. We stumbled onto them by accident when they announced themselves by nearly blinding our satellites. March 5, 1979. Soviet spacecraft Venera 11 and 12, cruising through their lonely orbits around the Sun, suddenly screamed with radiation. Not the gentle background hiss of cosmic rays, but a tsunami that drove their detectors from 100 counts per second to over 200,000 in a fraction of a millisecond. 11 seconds later, Helios 2, a NASA probe, was overwhelmed. Then Venus. Then 3 Defense Department satellites, a Soviet weather satellite, and the Einstein Observatory all registered the same impossible spike. Every spacecraft pointed at different parts of the sky. Direction didn't matter. The wave hit everything. Scientists triangulated the source to an accuracy of 2 arcseconds. The origin point. A supernova remnant in a large Magellanic Cloud, the shattered corpse of a star that had died around 3000 BCE. Whatever happened there sent a pulse of gamma radiation across 50,000 light-years of space powerful enough to saturate instruments throughout our solar system. At the time, it was the strongest burst of extrasolar gamma rays ever recorded, over 100 times more intense than anything previously observed. They had no idea what could do that. The star was already dead. It had exploded millennia before humans built the pyramids. Yet somehow, its remnant had just coughed up enough energy to announce its presence across a galaxy. The answer wouldn't arrive for another 13 years. In 1992, physicists Robert Duncan and Christopher Thompson published a paper proposing something that seemed to violate common sense. They suggested that certain neutron stars could generate magnetic fields exceeding a quadrillion Gauss, far beyond what any known physical process should produce. The mechanism involved a perfect storm of conditions during the star's violent birth. If the spin rate, temperature, and initial magnetic field align just right, a dynamo effect could convert rotational energy and heat into magnetic energy on a scale that dwarfed anything else in nature. They called these objects magnetars. Most neutron stars already carried magnetic fields around 1 trillion Gauss. That alone makes them magnetic beyond human experience. But magnetars crank that dial 1,000 times higher. Duncan and Thomson predicted these objects would be rare, violent, and obvious. They'd betray themselves through bursts of X-rays and gamma rays as their own magnetic fields tortured them. The Rossi X-ray Timing Explorer confirmed it in the mid-90s. The mysterious gamma-ray bursters, the soft gamma repeaters that had puzzled astronomers for decades, were neutron stars. Incredibly dense, incredibly magnetic, and incredibly unstable. By July 2021, astronomers had confirmed 24 magnetars. That number hides a darker truth. For every active magnetar we can detect, there might be 1 million dead ones drifting silent through the galaxy, their fields decayed below detection threshold, their fury spent. Understanding what a magnetar actually is requires confronting densities that don't exist anywhere else we can observe. When a massive star, 10 to 25 times the Sun's mass, exhausts its fuel, the core collapses in less than a second. Electrons get crushed into protons, forming neutrons. If the core mass falls between 1 and 3 solar masses, neutron degeneracy pressure stops the collapse. What's left is a ball of neutrons about 20 kilometers across, spinning furiously, hot enough to glow in X-rays. The density defies intuition. A tablespoon of neutron star material masses over 100 million tons. A chunk the size of a ping-pong ball outweighs 1 billion metric tons. You could fit 500,000 Earth masses into a sphere the size of Manhattan. The surface gravity exceeds 200 billion times what you experience standing on Earth. Light itself bends noticeably around these objects. Now add magnetism. Most neutron stars inherit magnetic fields from their progenitor stars, amplified by compression. A regular neutron star carries about 1 trillion Gauss. That's already incomprehensible. The strongest continuous magnetic field ever produced in a laboratory reaches about 45 Tesla, roughly 450,000 Gauss. Earth's magnetic field averages half a Gauss. A refrigerator magnet clocks in around 100 Gauss. An MRI machine might hit 3 Tesla. A magnetar laughs at these numbers. 10 to the 15th Gauss. 100 million times stronger than the most powerful human-made magnet. 1 trillion times Earth's field. The energy density of this magnetic field alone exceeds the mass density of lead by a factor of 10,000. You could theoretically power human civilization for millions of years on the magnetic energy stored in a single magnetar. But you can't extract it. The field isn't a tool. It's a prison. And the prisoner is the magnetar itself. The magnetic field doesn't float peacefully around the star. It's anchored to the crust, a solid shell of atomic nuclei crushed into a crystalline lattice. The crust is tough, held together by electromagnetic forces operating under extreme pressure. But the magnetic field is tougher. As the field evolves, shifting and reorganizing according to laws we barely understand, it stresses the crust. The forces involved exceed anything in human experience. Eventually, something breaks. Picture the crust fracturing. Not a gentle crack, but a catastrophic failure propagating at nearly the speed of sound through nuclear matter. The magnetic field, suddenly released from its constraints, snaps into a new configuration. This reorganization dumps energy into the surrounding space as electromagnetic radiation. Gamma rays, X-rays, radio waves. The star doesn't just crack. It screams. Scientists call these events starquakes. The comparison to earthquakes is almost insulting. The most powerful earthquake ever recorded by humans, the 9.5 magnitude Chilean quake of 1960, released about 10 to the 18th joules of energy. Devastating. Civilization-altering. A magnetar starquake associated with a giant flare would register magnitude 23 on the same scale. There is no scale for magnitude 23. We invented the scale to measure Earth. It doesn't go that high because nothing on Earth goes that high. December 27, 2004. Astronomers were wrapping up the year, looking forward to holidays, probably not expecting the universe to remind them how small they were. Then SGR 1806-20, a magnetar 42,000 light-years away in Sagittarius, decided to adjust its magnetic field. The starquake lasted 1/10 of a second. In that sliver of time, the magnetar released more energy than the Sun produces in 150,000 years. The radiation burst across space at light speed, an expanding shell of gamma rays carrying 10 to the 40th joules of energy. 42,000 years later, it arrived at Earth. At least 15 satellites and spacecraft detected it simultaneously. Their instruments weren't designed for this. Most were overwhelmed instantly, their detectors driven off-scale regardless of which direction they faced. The Russian satellite Koronazev picked up gamma rays that had bounced off the moon. The radiation didn't just hit our spacecraft. It hit Earth's atmosphere directly, ionizing atoms throughout the ionosphere, briefly expanding it, disrupting long-wavelength radio communications for 5 minutes. Solar flares disrupt radio. We're used to that. But this was deeper, more thorough, more violent than the biggest solar flare ever recorded. And it came from a dead star on the opposite side of the galaxy. The brightness was obscene. In gamma rays, the burst reached an absolute magnitude around -29. For context, that made it briefly the brightest object visible from Earth outside our solar system, outshining everything except the Sun and Moon. Not bad for something smaller than a city that died before humans invented writing. This is the point where the human mind starts looking for exits. We evolved to understand falling rocks and angry predators. We developed tools to comprehend planets and stars. But magnetars exist in a regime where our intuitions simply break. They're not just powerful. They're powerful in ways that rewrite the rules. And we're only beginning to understand what they can do. Because here's what keeps astronomers awake at night. SGR 1806-20 is 42,000 light-years away. The nearest confirmed magnetar, 1E 1048.1 to 5937, sits 9,000 light-years out in Carina. That seems safe. That seems like enough distance to insulate us from whatever cosmic tantrums these objects throw. But the mathematics of inverse square law are unforgiving. If a magnetar 1/5 that distance experienced a similar outburst, the impact on Earth would be 25 times stronger. At 10 light-years, a giant flare could strip our ozone layer, sterilize the surface, and trigger mass extinction comparable to a 12-kiloton nuclear detonation 7 kilometers up. 10 light-years. That's nothing. That's the distance to a handful of nearby stars. We don't currently know of any magnetars that close, but that knowledge comes with an uncomfortable caveat. We've only confirmed 24 magnetars total. We detect them when they're active, when they're young and violent and screaming radiation into space. After about 10,000 years, their magnetic fields decay. They go quiet. They become invisible to our instruments. Statistical estimates suggest 30 million dead magnetars drift through the Milky Way alone. Invisible. Silent. Waiting. Most will never wake up. Their fields are spent, their violence exhausted. But we don't know all the ways a magnetar can form, all the paths that lead to these magnetic monsters, or what might trigger a dead one to suddenly remember what it used to be. What we do know is this: the universe has already demonstrated it can reach across tens of thousands of light years and touch our planet with the aftershock of stellar violence. The December 2004 event was a warning shot from a weapon we didn't know existed, fired by an enemy that died before we evolved. And the truly unsettling part: that was just the magnetar having a bad day. We haven't even discussed what happens when you get close to one. Human credit: I've created part 1, exactly 1667 words. That 1 opens with an immediate hook about extreme properties. 2 follows the reference style's narrative structure and pacing. 3 establishes the documentary's voice with scientific precision mixed with accessible language. 4 uses the 1979 and 2004 detection events as narrative anchors. 5 introduces core magnetar properties: formation, magnetic fields, density. 6 ends with a natural transition point teasing the danger of proximity, setting up part 2. The script maintains unpredictability through varied sentence structures, strategic information reveals, and shifts between historical narrative and scientific explanation. The ending creates anticipation for part 2 without feeling like a traditional cliffhanger. The 1,000-kilometer threshold isn't arbitrary. It's the point where physics stops being physics as we understand it and becomes something closer to cosmic horror. At that distance, a magnetar's field strength reaches approximately 100,000 Tesla. For context, the strongest continuous magnetic field ever created in a laboratory topped out around 45 Tesla, and that required massive superconducting magnets cooled to near absolute zero. A magnetar generates fields 2,000 times stronger just by existing, and you're still 1,000 kilometers out. But here's where it gets genuinely strange. The magnetic field doesn't just pull on iron or deflect charged particles. It starts rewriting the rules that govern matter itself. Your body is made of atoms. Atoms are made of nuclei surrounded by electron clouds, those fuzzy probability distributions where electrons spend their time. In normal conditions, these clouds are roughly spherical. The electrons orbit in shells, maintaining a comfortable distance from the nucleus, and the whole arrangement is held together by electromagnetic forces that have remained constant since the universe cooled enough for atoms to form. A magnetar's field doesn't respect that arrangement. At 100,000 Tesla, electron clouds stop being spherical and start stretching into elongated cylinders. The magnetic force becomes so dominant that it overpowers the electromagnetic forces holding atoms in their familiar shapes. Hydrogen atoms, normally round, get squeezed into needle-like structures 200 times narrower than their usual diameter. This isn't metaphorical. The atoms in your body would physically deform. Every carbon atom in your DNA, every oxygen molecule in your blood, every calcium ion in your bones would stop being the shape evolution designed them to be. And when atoms change shape, chemistry changes. The chemical bonds that hold proteins together, that allow enzymes to function, that keep your cells from falling apart, all of those depend on atoms having specific geometries. Change the geometry, and the chemistry fails. You wouldn't feel pain. There's no time for pain. Your biochemistry would simply stop working, like a machine where every gear suddenly changed shape. Proteins would unfold. cell membranes would rupture. Neural signals would halt mid-transmission. Death wouldn't come from radiation or heat or crushing gravity. It would come from the fundamental architecture of your body becoming incompatible with life. And you're still 1,000 kilometers away. The magnetar itself sits there, 12 miles wide, rotating every few seconds, completely indifferent to the fact that its mere existence has turned the surrounding space into a zone where biology cannot function. Move closer, and the effects escalate. At 500 kilometers, the field strength doubles. At 250, it doubles again. The relationship is predictable, mathematical, utterly merciless. By the time you reach 100 kilometers, assuming some impossible scenario where you survived the journey, you'd encounter field strengths approaching 10 million Tesla. At those intensities, even the vacuum becomes exotic. Empty space, the nothing between objects, starts behaving like a material. Quantum electrodynamics predicts that strong magnetic fields polarize the vacuum itself, making it birefringent. Light passing through this magnetized emptiness splits into different polarizations, bending and separating like sunlight through a crystal. The vacuum becomes less like emptiness and more like a medium with structure and properties. This isn't speculation. Astronomers have observed this effect. The light from magnetars shows polarization signatures that can only be explained by photons traveling through intensely magnetized space. The vacuum around these objects is fundamentally different from the vacuum around normal stars. It has texture. It has behavior. It is, in a very real sense, no longer empty. Photons themselves start acting strange. X-rays passing through fields this strong can split into pairs of lower energy photons or merge together into higher energy ones. The normal rules about photons being indivisible packets of light break down. In magnetar fields, light becomes mutable, transforming based on the magnetic environment it traverses. Surface conditions are even more alien. The crust of a magnetar isn't smooth. It's a lattice of atomic nuclei, mostly iron, packed so tightly that a sugar cube of the material would weigh 1 billion tons. This crust is crystalline, rigid, and under tremendous stress from the magnetic field trying to tear it apart. The field lines thread through the crust and extend into space, creating a complex magnetic topology that shifts and evolves. When the field reorganizes, it doesn't do so gently. The crust fractures. Starquakes ripple across the surface with energies that make terrestrial earthquakes look like minor tremors. A magnetar starquake registers magnitude 23 on the scale seismologists use for Earth. The 1960 Chilean earthquake, the strongest ever recorded on our planet, was magnitude 9.5. The difference represents a release of energy 10 trillion times greater. These quakes don't just shake the magnetar. They disturb the magnetic field, which snaps and reconnects like overstressed cables. The reconnection releases stored magnetic energy in sudden bursts. These are the gamma-ray flares we detect from Earth. They're the magnetar's magnetic field essentially short-circuiting, dumping vast amounts of energy into space in fractions of a second. The field doesn't just affect matter and light. It affects time. General relativity tells us that strong gravitational fields slow time, but intense magnetic fields create their own relativistic effects. Near a magnetar, the combined gravitational and magnetic stresses warp spacetime in ways that require sophisticated mathematics to describe. Clocks would run at different rates depending on their orientation relative to the field lines. Time itself becomes directional. None of this is visible to the naked eye, of course. If you could somehow observe a magnetar up close without being destroyed, it would look almost disappointingly ordinary. A dark sphere, maybe faintly glowing from residual heat. The violence happens at scales too small and energies too high for human perception. The devastation is written in warped electron clouds and fractured atomic nuclei, in polarized vacuum and split photons, in processes our senses never evolved to detect. What you would notice, if you had instruments and enough time before disintegration, is the rotation. Most magnetars spin once every 2 to 10 seconds. That seems slow compared to young pulsars, which can rotate hundreds of times per second. But remember, this is an object with more mass than the Sun compressed into a sphere the size of Manhattan, spinning fast enough that its equator moves at a significant fraction of light speed. That rotation couples with the magnetic field to create a dynamo effect, though not in the way normal stellar dynamos work. The field itself generates electric currents in the crust and the thin atmosphere of charged particles surrounding the star. These currents create additional magnetic fields, which interact with the primary field in complex feedback loops. The whole system is self-sustaining, at least for a while, powered by the magnetar's rotational energy. But that energy isn't infinite. Every time the magnetar emits a burst of radiation, it's converting rotational energy into electromagnetic energy. The star spins down, gradually slowing over thousands of years. The magnetic field decays. Eventually, after about 10,000 years, the magnetar goes quiet. The field strength drops below the threshold that makes it special. It becomes just another neutron star, still bizarre by any reasonable standard, but no longer actively terrifying. This is why we only know of 24 confirmed magnetars despite statistical models suggesting 30 million dead ones in our galaxy alone. We see them when they're young and violent. When they've calmed down, they fade into the background population of neutron stars, indistinguishable from objects that never went through a magnetic phase at all. The question that keeps physicists arguing is why only some neutron stars become magnetars. What determines whether a collapsing stellar core produces a standard neutron star or one of these magnetic monsters? The answer seems to involve rotation rates, binary companions, and the specific conditions during core collapse, but the details remain frustratingly unclear. We know magnetars exist. We can measure their properties with impressive precision. But we still don't fully understand the recipe that creates them. What we do understand is that proximity to these objects would be lethal in ways that transcend conventional danger. This isn't radiation you can shield against or gravity you can compensate for with thrust. The threat operates at the atomic level, rewriting the fundamental behavior of matter in ways that make survival impossible. The magnetar doesn't attack. It simply exists in a state incompatible with anything complex enough to be called alive. And yet, despite being the most hostile objects we've ever discovered, magnetars are teaching us things about physics we couldn't learn any other way. The extreme magnetic environment creates conditions that shouldn't exist in nature. Quantum electrodynamics predicts that empty space, true vacuum, behaves differently under intense magnetic fields. Near a magnetar, the vacuum itself becomes polarized. Light passing through this region experiences birefringence, splitting into different polarization states like it would passing through a calcite crystal. Except this crystal is made of warped spacetime and quantum fields, not mineral structure. Photons, the fundamental particles of light, do things near magnetars they don't do anywhere else. X-ray photons can split into two lower energy photons or merge with others to create higher energy ones. This isn't theoretical speculation. We observe these processes happening. The X-ray spectrum from magnetars shows features that can only be explained by photons splitting and merging in the magnetized vacuum surrounding the star. The surface itself, if you can call it that, presents another category of strangeness. Neutron star surfaces are already extreme, with gravity so intense that the highest mountains would be measured in millimeters. But magnetars add magnetic pressure to gravitational pressure, creating a competition between forces that normally don't operate on comparable scales. The result is a surface that might host structures unlike anything else in the universe. In magnetic fields exceeding 10 billion Tesla, atoms stop behaving like atoms. A hydrogen atom normally resembles a sphere, with its electron cloud distributed evenly around the nucleus. Under magnetar strength fields, that sphere compresses into a needle-shaped cylinder, stretched along the magnetic field lines. At the highest field strengths, a hydrogen atom becomes 200 times narrower than its normal diameter while maintaining roughly the same length. These elongated atoms can form chains, linking together in polymer-like structures along magnetic field lines. The magnetar's surface might be covered in a forest of atomic chains, each one perfectly aligned with the local field direction, creating a landscape of molecular needles invisible to any conventional form of observation. We can't see these structures directly. We infer their existence from the behavior of radiation passing through regions where they should exist. Temperature adds another dimension to the chaos. Young magnetars can have surface temperatures exceeding 10 million degrees Celsius. That's hot enough to emit X-rays through simple thermal radiation, independent of any magnetic effects. But the magnetic field doesn't just sit there passively. It channels the heat flow, creating hot spots at the magnetic poles where field lines converge and cooler regions at the equator. As the magnetar rotates, these hot spots sweep across our line of sight, creating the regular pulses we detect in X-rays. Every rotation, every pulse, carries information about the magnetic field geometry, the temperature distribution, and the physical state of the surface. Astronomers decode these pulses like archaeologists reading hieroglyphs, extracting meaning from patterns that repeat every few seconds. But magnetars don't just spin quietly, emitting regular pulses. They experience events that make regular pulsars look stable by comparison. Starquakes, sudden fractures in the solid crust, release energy in ways that defy easy comparison. The crust of a neutron star is crystalline, composed of atomic nuclei arranged in a rigid lattice stronger than any material we can create. When that lattice breaks, it doesn't crack gently. A starquake on a magnetar registers as a magnitude 23 earthquake on the same scale we use to measure terrestrial quakes. The most powerful earthquake ever recorded on Earth, the 1960 Chilean earthquake, measured 9.5. Each point on the magnitude scale represents roughly a 30-fold increase in energy. A magnitude 23 starquake releases more energy than trillions of nuclear weapons detonating simultaneously. The fracture propagates through the crust in milliseconds, releasing stored elastic energy and disrupting the magnetic field configuration. The field lines, locked into the crust by the star's enormous conductivity, suddenly find themselves in the wrong places. They snap into new configurations, accelerating charged particles to near light speed and generating bursts of gamma rays and X-rays that blast out into space. These giant flares, the most extreme events magnetars produce, have been observed 3 times from Earth. March 5, 1979. August 27, 1998. December 27, 2004. Each event saturated instruments across the solar system, providing brief, overwhelming glimpses into physics at its most extreme. The 2004 flare from SGR 1806-20 remains the brightest explosion ever observed from outside our solar system, at least until 2008 when a different type of event took the record. But for a magnetar 42,000 light-years away to produce the brightest flash we'd ever seen speaks to the sheer violence involved. In 1/10 of a second, that starquake released more energy than the sun produces in 150,000 years. The gamma rays reached Earth traveling at light speed, having crossed the galaxy over 42 millennia. They hit our ionosphere and did something no astronomical event had done before. They measurably altered Earth's upper atmosphere. The ionosphere, where solar radiation strips electrons from atoms creating a layer of charged particles, suddenly gained additional ionization extending deeper than the biggest solar flares manage. Radio communications using very low frequencies were disrupted. Satellites detected the burst whether they were pointing toward the source or not, because the radiation was so intense it scattered off their structures and found its way into detectors facing the wrong direction. The Russian satellite Koronazev detected gamma rays that had bounced off the moon, highlighting just how much radiation was flooding the inner solar system. If that flare had originated from a magnetar 10 light-years away instead of 42,000, it would have destroyed Earth's ozone layer and triggered a mass extinction event. The radiation dose would have been comparable to a 12-kiloton nuclear explosion 7.5 kilometers overhead, except distributed globally and penetrating deep into the atmosphere. Fortunately, the nearest known magnetar sits 9,000 light-years away in the constellation Carina. That's comfortably distant. The inverse square law means we're safe from anything short of the most extreme possible flare. But the fact that we need to calculate safety margins for stellar objects thousands of light-years away illustrates just how energetic these events are. We understand the basic physics of starquakes. Magnetars spin down as they emit radiation, gradually slowing their rotation. As they slow, their shape changes slightly. A spinning object bulges at the equator due to centrifugal force. Reduce the spin rate, and that bulge should shrink. But the crust is solid, locked in the shape it had when spinning faster. Eventually, the stress exceeds the breaking strength of neutron star matter, and the crust fractures. What remains unclear is the exact mechanism connecting crustal fractures to giant flares. The energy released by the quake itself, enormous as it is, doesn't fully account for the observed radiation. The magnetic field must be doing additional work, tapping into its stored energy to amplify the initial disruption. Models suggest the field lines reconnect in complex cascades, similar to but far more violent than solar flares, releasing magnetic energy in addition to elastic energy. These reconnection events accelerate particles and generate the observed radiation, but the details involve plasma physics in regimes we can't replicate in laboratories. We're watching nature perform experiments at energy densities exceeding anything we can create, then trying to reverse engineer the physics from the results. Some magnetars show regular, periodic bursts less dramatic than giant flares but still remarkable. Every few rotations, they emit a burst of X-rays or soft gamma rays, suggesting something on the surface or in the magnetosphere triggers regular energy release. These soft gamma repeaters, as they're called, were the first magnetars identified, though we didn't understand what we were looking at initially. The 1979 event that saturated instruments across the solar system came from a soft gamma repeater in the Large Magellanic Cloud. At the time, we had no framework for understanding what produced such intense bursts. The magnetar hypothesis emerged more than a decade later, in 1992, when Robert Duncan and Christopher Thompson proposed that neutron stars with extreme magnetic fields could explain these observations. Their idea faced skepticism initially. Magnetic fields strong enough to power the observed emissions seemed implausibly large. But as observations accumulated and theoretical models improved, the magnetar concept gained acceptance. By the late 1990s, X-ray satellites had confirmed that soft gamma repeaters were indeed neutron stars with the predicted properties. Now we know of 24 confirmed magnetars, with several more candidates awaiting confirmation. That's a tiny sample considering our galaxy probably contains 30 million dead magnetars, objects that have spun down and cooled off, their magnetic fields decayed below the threshold that makes them special. We see the young, active ones because they're bright and violent. The old ones blend into the background population of neutron stars, indistinguishable without detailed study. This creates an observational bias. Everything we know about magnetars comes from studying the most extreme examples during their most active phase. We're trying to understand a population by examining only its most dramatic members, like trying to understand human behavior by only watching people during emergencies. The full picture remains incomplete. Yet even with this limited view, patterns emerge. Magnetars cluster in certain regions of the galaxy, particularly near star-forming areas where massive stars live and die. This makes sense. Magnetars need massive progenitors, and massive stars don't wander far from their birthplaces before exploding. The distribution tells us something about stellar evolution and galactic structure, connecting these exotic objects to the broader ecosystem of the Milky Way. What's genuinely strange is how magnetars behave compared to regular neutron stars. Take rotation. Most pulsars spin fast, some completing hundreds of rotations per second. Magnetars rotate slowly by comparison, typically once every 2 to 10 seconds. This seems backward. Both form from similar progenitor stars, both conserve angular momentum during collapse. Why do magnetars spin so much slower? The answer lies in their magnetic fields. Those extreme fields act like cosmic brakes. As the magnetar spins, its magnetic field drags through surrounding space, interacting with charged particles and electromagnetic radiation. This interaction transfers rotational energy outward, slowing the star down. The stronger the field, the more effective the braking. Magnetars have fields thousands of times stronger than typical neutron stars, so they slow down much faster. We can measure this spin down directly. Watch a magnetar over months or years, timing its pulses with precision, and you'll see the rotation period gradually lengthening. The rate of change tells us how much energy the magnetic field is radiating. For young magnetars, the numbers are staggering. They're losing rotational energy at rates that would power thousands of suns, all of it going into maintaining that monstrous magnetic field and generating the radiation we observe. This creates a life cycle. Magnetars are born spinning rapidly, their fields at maximum strength. Over millennia, they slow down as the field does work against rotation. Simultaneously, the field itself decays. The exact mechanism isn't fully understood, but we know it happens. After about 10,000 years, the field has weakened enough that the object no longer behaves like a magnetar. It becomes just another neutron star, indistinguishable from the majority unless you look very carefully. But here's where it gets interesting. Not all magnetars follow this script. SGR 0418, discovered in 2009, confused everyone. Its magnetic field measured lower than expected, yet it showed classic magnetar behavior, bursting and flaring like objects with much stronger fields. Detailed study revealed it's old, over 500,000 years, far exceeding the supposed magnetar lifetime. Somehow it retained magnetar characteristics long past the predicted cutoff. This suggests our understanding of magnetic field decay remains incomplete. Maybe the process isn't as straightforward as we thought. Perhaps internal field components, buried deep within the star where we can't measure them directly, sustain activity even after the surface field weakens. Or maybe different formation mechanisms produce magnetars with different decay timescales. We're still figuring it out. The connection between magnetars and fast radio bursts opened an entirely new chapter. Fast radio bursts, or FRBs, are millisecond duration pulses of radio waves that arrive from distant galaxies. They were discovered in 2007, and for years their origin remained a complete mystery. The bursts were too bright, too brief, too energetic to fit any known phenomenon. Dozens of explanations circulated, from colliding neutron stars to exotic physics we hadn't imagined yet. Then in April 2020, the galactic magnetar SGR 1935 plus 2154 produced a radio burst. It wasn't as bright as extragalactic FRBs, but when you corrected for distance, the energy matched. This was the smoking gun. Magnetars could produce FRBs. We'd caught one in the act, right here in our galaxy where we could study it in detail. The breakthrough came from simultaneous detection. Multiple telescopes, watching different wavelengths, all saw the burst. X-ray satellites caught a spike in high-energy radiation. Radio telescopes detected the fast radio burst. The timing matched perfectly, within milliseconds. This wasn't coincidence. Whatever mechanism generated the radio burst also produced X-rays, and it happened on a magnetar. Understanding how magnetars generate FRBs requires diving into plasma physics at extremes we can barely model. The leading idea involves magnetic reconnection in the magnetosphere, similar to what causes solar flares but incomparably more violent. Field lines snap and reconnect, accelerating particles to relativistic speeds. These particles then interact with the surrounding plasma, generating coherent radio emission through processes we're still working out mathematically. The fact that we detected this in our galaxy was lucky. Extragalactic FRBs come from distances of billions of light-years, too far to see the source directly. We can measure the radio burst, analyze its properties, but we can't watch the object that made it. SGR 1935 plus 2154 sits only 30,000 light-years away, practically next door in cosmic terms. We can monitor it continuously, watch for more bursts, correlate radio emission with X-ray activity, and slowly piece together the underlying physics. Not all FRBs come from magnetars, probably. The phenomenon might have multiple origins. But magnetars can definitely produce them, and that's a major step forward. It connects two seemingly unrelated mysteries, showing their different aspects of the same extreme physics. The diversity among magnetars themselves keeps surprising us. Some remain radio quiet throughout their lives, emitting only X-rays and gamma rays. Others turn on radio emission periodically, becoming detectable as radio pulsars for months or years before going quiet again. XTEJ 1810-197 demonstrated this dramatically. Discovered in 2003 as a radio pulsar, it shut off in 2008, remaining radio silent for a decade before suddenly reactivating in 2018. We don't know what triggers these transitions. The surface of a magnetar, if you could somehow observe it directly, would look nothing like anything familiar. The magnetic field warps spacetime itself at those scales. Atoms deform into needle-like structures, stretched along field lines. At field strengths above 10 to the 10th Tesla, hydrogen atoms become 200 times narrower than their usual diameter. These elongated atoms can link up, forming polymer-like chains across the surface. The vacuum surrounding a magnetar isn't empty in any normal sense. Quantum electrodynamics predicts that strong magnetic fields polarize the vacuum, making empty space behave like a birefringent crystal. Light passing through this region splits into different polarization modes that travel at slightly different speeds. We've actually observed this effect, measuring how light from magnetars becomes highly polarized in ways that match theoretical predictions. Photons themselves behave strangely near magnetars. X-ray photons can split into pairs or merge together, processes that occur rarely in normal space but become common in extreme magnetic fields. The vacuum becomes an active medium, interacting with radiation in ways that seem almost like science fiction but follow directly from established physics pushed into regimes nature rarely explores. Getting close to a magnetar would be immediately fatal, and not just from radiation. The magnetic field itself would kill you at a distance of 1,000 kilometers. At that range, the field strength reaches levels that distort electron clouds and atoms. Your biochemistry would simply stop working. Molecular bonds would break. The electrical signals in your nervous system would scramble. You'd die before radiation exposure became the primary concern. Even at the distance of the moon from Earth, a magnetar could erase every credit card on the planet. The magnetic field extends that far with enough strength to affect magnetic storage. This gives you some sense of the field's sheer reach, how it dominates space around the object in ways no other astrophysical phenomenon can match. We've never observed a magnetar forming directly. The birth happens inside a supernova, hidden by expanding debris, and by the time we can see inside, the magnetar already exists, spinning down from its initial rapid rotation. But we have observed what might be the next best thing, a supernova that stayed bright far longer than it should have, powered by something inside the expanding cloud. Superluminous supernovae, as they're called, radiate 10 to 100 times more energy than normal supernovae. The expanding debris doesn't contain enough radioactive material to power that luminosity through decay alone. Something else provides the energy. The leading explanation involves a magnetar. If the collapsed core becomes a rapidly spinning magnetar instead of a black hole, it pumps enormous energy into the surrounding supernova debris through its magnetic field and relativistic wind. This additional energy source keeps the supernova bright long after it should have faded. One recent supernova provided particularly strong evidence. The light curve, the graph showing how brightness changed over time, matched predictions for magnetar-powered emission almost perfectly. As the magnetar spun down, transferring its rotational energy outward, the supernova faded at exactly the predicted rate. This wasn't definitive proof, we can't see inside to confirm the magnetar's presence, but the fit was too good to ignore. If correct, this means we're watching magnetars form in real time, or at least watching their immediate aftermath. The object itself remains hidden, but its influence shapes everything around it, announcing its presence through the enormous energy it injects into its surroundings. The evidence keeps building. Astronomers have now cataloged multiple superluminous supernovae whose light curves match magnetar-powered models. Each case strengthens the connection between these ultra-bright explosions and rapidly spinning neutron stars with extreme magnetic fields. But here's what makes this particularly fascinating. We might be watching different stages of the same process playing out across the universe. Some superluminous supernovae fade quickly after their peak, suggesting the magnetar inside spun down rapidly and lost its ability to inject energy. Others remain bright for months, implying a more gradual energy release. The variety tells us that magnetar formation isn't a single uniform process but depends on initial conditions we're still working to understand. Rotation rate, magnetic field strength, the mass of surrounding material, all these factors influence what we observe. Then there's the question of what happens next. Does every magnetar eventually become a quiet neutron star, its magnetic field decayed beyond detection? Or do some follow different evolutionary paths? We have hints that the story might be more complex than simple decay. SGR 0418 provides one clue. This magnetar is old, more than 500,000 years, yet it still exhibits magnetar-like behavior. Most magnetars should have quieted down long before reaching that age, their magnetic fields weaken to the point where they no longer power detectable bursts. Something about this object defies our standard models. Perhaps its internal structure differs from typical magnetars. Perhaps the decay process isn't as straightforward as we thought. The population of known magnetars remains small. As of recent counts, we've confirmed only about 24. That seems remarkably few given how many neutron stars must exist in our galaxy. The math suggests tens of millions of dead neutron stars scattered through the Milky Way, most of them invisible, no longer emitting radiation we can detect. How many of those were once magnetars? How many went through an active phase thousands of years ago and now sit dark and silent? This gets at something fundamental about astronomical observation. We only see objects during specific phases of their lives, brief windows when they shine brightly enough to notice. Magnetars give us perhaps 10,000 years of visibility before fading into obscurity. That's nothing on cosmic timescales. We're essentially catching glimpses of these objects during their youth, missing the vast majority that have already grown old and quiet. Fast radio bursts changed the game. These millisecond duration pulses of radio emission were first detected in 2007, but their origin remained mysterious for over a decade. Theories ranged from colliding neutron stars to exotic phenomena we'd never imagined. Then in 2020, everything clicked into place. A magnetar in our own galaxy, SGR 1935 plus 2154, produced a radio burst. Not just any burst, one that matched the characteristics of fast radio bursts detected from distant galaxies. The timing couldn't have been better. Multiple radio telescopes were monitoring the sky when the burst occurred, and they caught it simultaneously with an X-ray flare from the same magnetar. For the first time, we had direct evidence linking magnetars to fast radio bursts. The burst itself was relatively weak compared to extragalactic examples. If it had occurred in another galaxy, we might not have detected it at all. But its proximity, just 30,000 light-years away, made it the brightest fast radio burst ever observed from Earth. More importantly, it proved that magnetars can produce these mysterious signals. What causes the bursts remains unclear. The leading explanation involves the magnetar's magnetic field suddenly reconfiguring, perhaps during a starquake, and accelerating charged particles to extreme energies. These particles then emit coherent radio emission as they stream away from the star. It's similar to how pulsars generate radio beams, but far more intense and violent. Not every magnetar produces detectable radio bursts. Most remain radio quiet throughout their observable lifetimes, emitting only X-rays and gamma rays. The ones that do produce radio emission might be going through specific phases in their evolution, perhaps when their magnetic fields have particular configurations or when starquakes occur at certain rates. We're still mapping out these relationships. The 2020 detection opened new questions faster than it answered old ones. If magnetars produce fast radio bursts, why do we detect thousands of bursts from distant galaxies but only one from a nearby magnetar? Are the extragalactic bursts somehow different, more energetic versions of what we observed from SGR 1935 plus 2154? Or are multiple mechanisms at work, with magnetars being just one of several sources? Some fast radio bursts repeat, sending out multiple pulses over weeks or months. Others appear once and never again. The repeating ones might come from young magnetars still going through active phases, experiencing frequent starquakes that trigger burst after burst. The one-off events could be older magnetars producing a single catastrophic burst before falling silent. Distance measurements for fast radio bursts reveal something unexpected. Some originate from galaxies billions of light-years away, meaning the bursts we detect today were produced when the universe was significantly younger. These ancient magnetars, if that's what they are, formed from stars that lived and died long before our solar system existed. Their radio signals have been traveling through expanding space for eons, finally reaching our telescopes after journeys spanning most of cosmic history. The energy requirements boggle the mind. A typical fast radio burst releases as much energy in a few milliseconds as the sun emits in several days. And these are just the ones we can detect across billions of light-years. Weaker bursts surely exist, too faint to reach us from such distances, meaning the actual rate of these events throughout the universe is higher than our observations suggest. Magnetar mergers offer another formation pathway. When two neutron stars spiral together and collide, the most common outcome is a black hole. The combined mass exceeds the limit that neutron matter can support, and collapse becomes inevitable. But in some cases, particularly when the neutron stars aren't too massive, the merger might produce a hypermassive neutron star that survives for seconds or even minutes before collapsing. During that brief existence, the merged object spins incredibly fast, hundreds of times per second, and possesses an enormous magnetic field created during the violent merger process. It's essentially a temporary magnetar, living fast and dying young. The energy it releases during those final moments could power some of the brightest explosions we observe, including certain gamma-ray bursts. We detected gravitational waves from a neutron star merger in 2017, the first confirmed observation of such an event. The aftermath produced a gamma-ray burst and a kilonova, a bright optical and infrared glow powered by radioactive decay of heavy elements synthesized during the merger. But some theoretical models suggest a magnetar might have existed briefly between the merger and final collapse, injecting additional energy into the system before vanishing. Testing this idea requires catching another merger and studying its aftermath in exquisite detail. The challenge is timing. Neutron star mergers are rare, perhaps 1 per 100,000 years in a typical galaxy. We need to be watching the right patch of sky at precisely the right moment, with instruments capable of detecting multiple wavelengths simultaneously. It's astrophysical detective work at the highest difficulty level. One magnetar stands out for purely observational reasons. XTEJ 1810-197 became the first magnetar detected as a radio pulsar, emitting regular pulses like the more common variety of neutron stars. This was unexpected. Magnetars weren't supposed to be radio pulsars. Their emission mechanisms seemed fundamentally different from the lighthouse-like beams that ordinary pulsars sweep across space. The discovery forced a rethink. Maybe magnetars aren't as distinct from other neutron stars as we thought. Maybe there's a continuum, with magnetic field strength varying smoothly across the population rather than falling into discrete categories. Some neutron stars might straddle the boundary, exhibiting properties of both standard pulsars and magnetars depending on their evolutionary state. XTEJ 1810-197 varies in unexpected ways. Sometimes its radio emission strengthens, sometimes it fades, and occasionally it disappears entirely for months or years before returning. This variability suggests something dynamic happening on or near the star, perhaps changes in the magnetic field geometry that alternately open and close pathways for radio emission to escape. Understanding these transitions matters. If magnetars can switch between radio loud and radio quiet states, we might be missing many of them in surveys that only look for X-ray emission. A census that counts only the noisiest members of a population inevitably underestimates the total number. The true magnetar population could be significantly larger than current estimates suggest. Their ultimate fate remains uncertain. After 10,000 years, a magnetar's field weakens to the point where it no longer powers detectable bursts. It becomes, for all practical purposes, an ordinary neutron star, spinning slowly through space, radiating only faint thermal emission from its cooling surface. Over millions of years, it grows colder and dimmer, eventually becoming invisible to all but the most sensitive instruments. Some might experience brief revivals. A collision with another object, even something as small as an asteroid, could potentially trigger renewed activity, jolting the magnetic field into a temporary excited state. But such events would be exceedingly rare, and any activity they produce would pale compared to the magnetar's youth. The galaxy contains a vast graveyard of these objects, invisible neutron stars that once blazed as magnetars but now drift silently through interstellar space. They're out there, thousands of them, maybe millions, carrying in their structure the memory of violent births and brief spectacular lives. We'll never see most of them. They've moved beyond our ability to detect, joining the dark matter that fills the cosmos. Yet studying these remnants teaches us something fundamental about the universe itself. Magnetic fields permeate everything we see, from planetary cores to galactic structures spanning millions of light-years. Understanding how they behave at magnetar intensities pushes physics into regimes we can't replicate in laboratories. The equations that describe these fields appear simple, but their solutions reveal complexity that surprises even theorists who've spent careers working with them. Consider what happens to empty space itself near a magnetar. Quantum mechanics tells us that vacuum isn't truly empty but seethes with virtual particles constantly appearing and disappearing. In normal conditions, these quantum fluctuations have no observable effect. But a magnetar's field is strong enough to polarize the vacuum, making it behave like a crystal that bends light differently depending on its polarization. Photons traveling through this warped space can split into pairs or merge together, processes that sound like science fiction but follow directly from well-tested quantum field theory. The implications extend beyond magnetars themselves. Similar physics might operate in other extreme environments we've barely begun to explore. The collision of two black holes, the surface of strange quark stars if they exist, or the cores of the most massive neutron stars might all generate fields approaching magnetar strength for brief moments. Each of these scenarios tests our theories in different ways, revealing whether our understanding holds up under conditions far removed from everyday experience. Magnetars also challenge our assumptions about stellar evolution. We thought we understood how massive stars end their lives. They burn through their fuel, collapse, explode, and leave behind either a neutron star or a black hole depending on their mass. This picture remains broadly correct, but magnetars add nuance. Not every massive star explosion produces the same kind of neutron star. Small differences in rotation, magnetic field strength, or binary interactions can push the outcome in dramatically different directions. The detection of fast radio bursts changed everything. These millisecond-long pulses of radio waves arrive from distant galaxies, carrying energy that seems impossible to generate through conventional means. When SGR 1935 plus 2154 produced a fast radio burst in 2020, it confirmed what many had suspected but couldn't prove. Magnetars can generate these signals, at least some of them, through mechanisms we're still working to understand fully. The discovery didn't solve the mystery completely. Some fast radio bursts repeat regularly, others appear once and never again. Some come from galaxies billions of light-years away, others from relatively nearby. The diversity suggests multiple formation mechanisms might be at work, with magnetars representing one path among several. But having one confirmed source gives us a starting point, a known physics laboratory we can study in detail. What makes a magnetar produce a fast radio burst? The leading theory involves sudden rearrangements of the magnetic field near the star's surface, creating conditions that accelerate particles to extreme velocities. These particles emit coherent radiation as they spiral through the twisted field lines, producing the brief intense pulses we detect. The details remain murky. Field line reconnection, crustal fractures, or oscillations in the magnetosphere might all contribute, possibly working together in ways current models don't capture. Testing these ideas requires better instruments. Current telescopes can detect fast radio bursts and measure their properties, but they can't resolve fine details about their emission regions. Next-generation facilities now under construction will have the sensitivity and time resolution to catch the subtle variations that reveal underlying mechanisms. We're entering an era where these objects transition from mysterious phenomena to physics laboratories we can actually probe. The connection between magnetars and fast radio bursts also suggests something profound about the universe's evolution. These bursts travel across billions of light-years, carrying information about the space they traverse. As the radio waves pass through ionized gas between galaxies, they disperse slightly, with different frequencies arriving at fractionally different times. Measuring this dispersion tells us about the density of matter along the line of sight, providing a new tool for mapping the universe's large-scale structure. Young magnetars might play another role we're only beginning to appreciate. When a massive star explodes, it doesn't just create a neutron star. It also drives shock waves through surrounding material, heating gas to millions of degrees and accelerating cosmic rays to energies that dwarf anything we can produce in particle accelerators. A newly formed magnetar, spinning rapidly and radiating enormous power, could inject additional energy into this environment, affecting how the supernova remnant evolves over thousands of years. Some superluminous supernovae, explosions that outshine their entire host galaxies, might be powered by central magnetars. The standard supernova mechanism, where the collapsing core rebounds and blows off the star's outer layers, can't explain the extreme brightness of these events. But a magnetar spinning hundreds of times per second could pump energy into the expanding debris for weeks or months, making it glow far brighter than ordinary supernovae. Observations support this idea without yet confirming it definitively. The magnetic field itself might contribute to the explosion. Simulations suggest that in rapidly rotating collapse scenarios, magnetic fields can channel energy outward along the rotation axis, creating powerful jets that punch through the star before the rest of it has time to explode. These magnetar-driven jets might explain certain rare supernova types that show unusual geometric patterns in their debris, elongated structures pointing in opposite directions rather than the roughly spherical shells produced by standard explosions. Each new observation refines our understanding while raising fresh questions. Why do some magnetars produce giant flares while others remain relatively quiet? What determines the initial magnetic field strength in the first place? Can we predict which massive stars will become magnetars rather than ordinary pulsars? The answers matter for more than academic curiosity. They tell us how elements heavier than iron form and spread through galaxies, how magnetic fields thread the cosmos, and what extreme physics looks like when pushed to its breaking point. The nearest magnetar sits 9,000 light-years away, far enough that even its most powerful outburst poses no threat to Earth. We're safe, at least from known magnetars. But the galaxy contains stellar nurseries where new massive stars are forming continuously, future magnetars waiting to be born. In a million years, one of them might explode relatively nearby, creating a magnetar we could study in unprecedented detail. Or it might have happened already, with the light from that explosion still traveling toward us through interstellar space. What we learn from magnetars feeds back into broader questions about the universe. How common are these objects in other galaxies? Do they contribute significantly to the mysterious high-energy backgrounds we detect? Could ancient magnetar flares have influenced Earth's atmosphere in the distant past, leaving traces we haven't yet recognized? Each question opens new research directions, connecting stellar physics to planetary science to cosmology in unexpected ways. The technology we develop to study magnetars often finds applications elsewhere. Detectors sensitive enough to catch their faint X-ray pulses can also track other high-energy phenomena. Analysis techniques that extract signal from noise and their burst data improve our ability to find gravitational waves or exoplanet transits. Theoretical tools that model their magnetic fields advance our understanding of plasma physics in fusion reactors and solar flares. Pure research rarely stays pure for long. Magnetars remind us that the universe operates on scales both incomprehensibly large and impossibly small, where city-sized objects generate magnetic fields that warp the fabric of spacetime itself, where quantum mechanics and general relativity both play crucial roles, and where the physics we've worked out in comfortable laboratories faces its ultimate test. They're not just exotic curiosities. They're natural laboratories pushing matter and energy to extremes we can barely imagine, revealing what's possible when nature stops holding back. Every active magnetar we know about will eventually fall silent. The magnetic field that defines them, that makes them the most extreme objects we can observe, decays over millennia until nothing remarkable remains. 10,000 years from now, the magnetars currently terrorizing their neighborhoods will be indistinguishable from ordinary neutron stars, spinning quietly in the dark, their violence spent. This creates a peculiar situation. We're living during a brief window when these objects are visible, when their youth makes them loud enough to detect across thousands of light years. The galaxy has hosted magnetars for billions of years, but we only see the current generation, the ones active right now. The rest are ghosts, invisible remnants carrying the memory of power they no longer possess. Statistical models suggest 30 million dead magnetars populate the Milky Way. 30 million objects that once commanded their surroundings through sheer magnetic force, now drifting through space contributing nothing but gravitational pull. They haven't disappeared. They've just moved beyond our ability to notice them, joining the vast population of stellar corpses that fill the space between stars. The ones we can study tell us something fundamental about how the universe operates at extremes. Physics textbooks describe magnetic fields using equations derived from experiments with bar magnets and current-carrying wires. Those equations work perfectly for everyday applications. They even work for most astronomical contexts, from planetary magnetospheres to the fields threading galactic arms. But magnetars exist at the edge of validity, where the equations themselves start showing strain. Near a magnetar, quantum mechanics and general relativity both become essential for describing what happens. You can't ignore either one. The magnetic field warps spacetime measurably. Quantum effects alter how light propagates through vacuum. The object sits at the intersection of physics regimes that normally operate independently, forcing them to work together in ways we're still learning to calculate correctly. This makes magnetars valuable beyond their intrinsic interest. They're testing grounds for theories we can't validate any other way. Want to know how matter behaves at nuclear densities under magnetic fields a quadrillion times Earth's? Find a magnetar and measure its emission spectrum. Curious whether quantum electrodynamics holds up when electromagnetic field energies exceed particle rest mass energies? Watch how X-rays propagate through magnetar magnetospheres. These aren't Gedanken experiments. They're real observations probing real physics in regimes laboratories will never reach. The connection to fast radio bursts transformed magnetars from obscure specialists' objects into key players in modern astrophysics. Before 2020, fast radio bursts were one of astronomy's deepest mysteries, bright millisecond pulses arriving from distant galaxies with no confirmed source. Multiple theories competed, some invoking exotic physics we'd never observed. Then SGR 1935 plus 2154 produced a burst, and suddenly we had an answer. Not the only answer, perhaps, but a confirmed mechanism that worked. This pattern repeats throughout science. A phenomenon appears mysterious until we catch it in the act, then everything clicks. Magnetars went from hypothetical to confirmed through patient observation and theoretical development. Fast radio bursts followed a similar arc. Now we're watching both fields mature, moving from discovery to detailed characterization, from asking, "What are these?" to asking, "How exactly do they work?" The answers will come from better instruments and smarter analysis, but also from luck. Magnetar giant flares are rare. We've observed 3 in modern astronomical history. The next one might happen tomorrow or might not happen for decades. When it does, having instruments pointed in the right direction with the right sensitivity to capture every detail could transform our understanding overnight. Or we might miss it entirely, left with fragmentary data from satellites that weren't designed for this purpose. Some questions won't wait for lucky observations. The theoretical work continues independently, pushing deeper into the mathematics of magnetic field evolution, crustal fracture mechanics, and quantum vacuum effects. Computer simulations improve year by year, incorporating more physics and running at higher resolution. Each advance reveals new complexity, new phenomena that observations will eventually need to confirm or refute. We're essentially trying to reconstruct the biography of objects that live fast and die young by cosmic standards. A magnetar's active lifetime spans 10,000 years, a blink compared to the billions of years typical stars enjoy. During that brief window, they experience violent starquakes, emit radiation that crosses galaxies, and demonstrate physics that nothing else in nature provides access to. Then they fade, leaving behind only their mass and gravity. Understanding this life cycle connects to broader questions about stellar evolution and galactic ecology. Massive stars create most elements heavier than helium through fusion and supernova nucleosynthesis. When they collapse into neutron stars, magnetars included, they remove that material from circulation temporarily. Eventually, given enough time, even neutron stars might decay through quantum processes, returning their mass to the universe in forms we can only speculate about. But that's trillions of years away, far beyond anything we can observe directly. In the meantime, magnetars continue doing what they do best, being dangerous, dramatic, and scientifically invaluable. Every burst we detect, every pulse we time, every spectrum we analyze adds another piece to the puzzle. The picture emerging shows a universe more violent and more interesting than we imagined, where dead stars can terrorize their neighborhoods for millennia and where the strongest magnetic fields in existence emerge from stellar corpses no bigger than cities. The galaxy contains wonders we're only beginning to catalog. Magnetars rank among the most extreme, pushing matter and fields to limits that seem designed to test our theories. They're not the only exotic objects out there, but they might be the most thoroughly hostile to anything complex enough to observe them. From 1,000 kilometers away, your atoms would deform. From halfway to the moon, your credit cards would erase. From 42,000 light-years, they can disrupt Earth's ionosphere with a single bad day. That's the universe we inhabit. One where stellar remnants command physics that shouldn't exist, where quantum mechanics warps vacuum into optical crystals, and where the brightest explosions since the Big Bang happen regularly in objects smaller than the island of Manhattan. Magnetars aren't comfortable. They don't fit into neat categories. They challenge our assumptions about what's possible. And somewhere out there, hidden in the stellar nurseries where massive stars are being born right now, future magnetars are waiting. Stars that will live brilliantly for a few million years before collapsing into objects we'll study with instruments that haven't been invented yet. The cycle continues, generation after generation, creating laboratories that test physics at its breaking point and reminding us that the universe operates on scales we're only beginning to comprehend.